How do I change my name? So I see Curtis.
If you right click on yourself in the top, you should be able to rename. That
I see
should
it.
change it.
Got it. I do like Space Disruptor. Don't.
That's the right name for you.
Yes.
Great to see everybody. Welcome. So I guess we will wait a few minutes. Diane, would you like me to wait a few minutes or do you want me to just get going? I know we've got quite a bit of time in this
Let's
segment.
launch. Yeah. Let's launch. Fantastic. Thank you, Anna.
Well, excellent to see everybody today. Thanks so much for joining Space Disruptors Day. And it's going to be an extraordinary day of bringing innovators together. We've got about 55 tech brief from Space Disruptors that we're going to be hearing throughout the day. So it's going to be roughly 1 hour segments. We're going to take it at a little bit of a more leisurely pace in this first segment because it's going to be a shorter government briefing, in terms of the welcome. And then we're going to be heading into semiconductors and biotechnology. So if we have our semiconductor and biotechnology folks ready, we'll probably be ready to roll into those segments a little bit earlier than expected, probably by around 9:30. But after Curtis and I give our welcome kind of keynote presentation, to the extent there are other government colleagues on the line who wanted to give brief comments, and welcome in terms of what's important in terms of disruptive space technologies, we would certainly welcome, those brief kind of under a minute type comments of why this is of interest and why it might be of interest either personally or to your agency. So, and I know that many of our government colleagues were not asked to do that previously, so they're often quite flexible, but some people might actually not be on the line yet. So that's probably going to be brief comments. So let me take the opportunity to share a presentation. Let's see here. Make sure I get the right full screen here. So this is really an ongoing body of work with the entire space ecosystem in terms of large numbers of companies in the private sector, and then also an interagency approach. And so over the past year, there's been more of a whole of government approach, and that is both, we've worked formally with a number of interagency, space economy, space commercialization, and a number of other interagency groups. But then through that work, there's very deep relationships amongst not only colleagues in the in the federal sector across the federal government, but also in those of us who work in the space economy spheres. It's very much about working day to day with industry, with startups and small business. So while I'm representative of the Small Business Administration as their senior investment advisor and partner in their venture capital programs, and also the National Science Foundation in terms of leading the commercial space technology portfolios, and also serving as the co-chair for space economy and commercialization in LEO across the United States interagency working groups, the materials that follow are really reflective of an interagency approach. So in terms of the call to action, I mean, the reason we come together, even, a time in December when people are busy, is that the space economy is expected to be one of the most important areas of industry in the decade, and certainly the decades ahead. So what we find is many people are really excited about space technology and the space economy. We also occasionally, it might be 1 out of 3 people says, why are we focused on space? Don't we have enough to focus on Earth? And they might appreciate exploration, but might say, why are we focusing on space? And what we see is there's both the tremendous potential to go off planet, Moon, Mars, and beyond. Certainly, they're the most bold private sector goals right now. So as we think of some of the leaders, and SpaceX, which has been funded by multiple. But 2028 to Mars cargo mission, and looking to get back to the moon very, very quickly. So there's certainly the exploration, there's bringing civilization and infrastructure off planet, but there's also what does space do for us terrestrially? And what we found increasingly is that space is a convergent area of technology that ties to all economic sectors. And for those of you that are focused on biotechnology, we're going to be hearing a lot today about advances in biotech, advanced computation, which leads to AI advantage. On the environmental side, for those that appreciate solar technology, that's something that actually came from space. Most of us are using space-based data on a day-to-day basis, and that extends well beyond GPS to much of the IoT and other big data and AI analytics with Earth observational data and ties to other data streams. So there's so much that ties to benefiting life on Earth, the resources that we can expand, and at large, this is expected to be a multi-trillion-dollar industry in the years ahead. So there's a number of estimates and projections that put this at 2 trillion. It might actually be considerably more than that within the next decade, but the reason why is that we see that advantage extending to some of the highest value sectors that provide solutions for the United States and the world. So those are typically multi-trillion or multi-hundred-billion-dollar sectors, such as biotechnology, chips and semiconductors, certainly implications for infrastructure, resources. So there's both the opportunity of leading and the abundance that leadership in these areas can bring, and then there's also the cost of not leading and having other nations really take the lead here, or authoritarians, in terms of what is built out and shared with nations across the globe. In the United States, we benefit obviously from working with people both who were born here and are citizens, and also being an attractor for some of the most creative and helpful people from around the globe. So we really welcome, both through Artemis Partners and beyond, that ability to work with leaders really across the world in this area. Next slide, please. And I'm the one leading the slides. So I would say, so I guess I would just also say, in times of change, in some markets, there's the question of, well, what's going to happen next? Are we going to see more? Or are we going to see less? And certainly in recent months, some markets, it's been crystal clear. For instance, I also co-chair the US Digital Assets R&D agenda, and the crypto and the blockchain markets have been quite clear that they expect it to be a very expansive market in those sectors. While it might not be always as visible in space technology, and there are many of us who have worked across multiple administrations, who've worked in space for many years. And when we're speaking to people really on both sides of the aisle, this is expected to be a tremendous time going forward. And certainly there's that interest that's bipartisan, and there's also been that leadership in the past from the Trump administration, both in the initiation of Space Force, in terms of the accelerating planning to return to the moon. So really seeing good things across multiple administrations, and the expectations that we're seeing people share with us is there's so many good things that have happened, across the past 2 years, and these are really expected to accelerate going forward. So today, we recognize that there's an expansive interest in space technology and investments, but not everybody has been supportive in this space as either as an entrepreneur, a researcher, or an investor, so that there's not always the same access to information in terms of what the opportunities are. Today is a distillation of, many of our colleagues across the line have spent, I know I've spent years trying to find where are some of the most compelling innovations. So we're sharing those insights. We've got researchers on the line and government colleagues that it's all they do all day, every day to find out what the opportunities are here. So today we're trying to condense that and learn from everybody's shared expertise at what is a very timely moment to determine how the United States and globally we can accelerate the space economy. So you know, as we think about space technology, and today you're going to see a lot of segments that are maybe more traditional in terms of, we say, how do we think about launch or satellites, you know, and many of these areas. And today what we see is that there's also just the framing of across areas of critical technologies. So we see that there are many areas of industry, and then there's also fields of critical technology. So there are lists, for instance, that the White House puts out and that the Department of Defense puts out. And we see that there is relevance really across all areas of critical technologies of space technologies. So on communications, you're familiar with satellites, space-based internet, position, navigation, and timing. So that's things like GPS and other forms of PNT. A wide range of advantages that we'll learn about today in terms of advanced materials. You'll see quite a bit on how microgravity conveys advantage to develop materials that, quite frankly, aren't achievable in 1G or the gravity we have on Earth. So many areas of advanced manufacturing, whether it's from rockets and launch to gravitational control, disaster resilience and sensing. So for those, whether it's figuring out what commercial opportunities are available from the wide range of things that you can do with Earth observational data, to how to prevent disasters, you know, such as forest fires. There's tremendous amount that can be done on the disaster resilience, comms, and sensing side. Certainly, cybersecurity is paramount, and then there are a number of companies focused on that. AI, there's tremendous advantages, both AI off planet and ingesting some of that data, but also some of the chips advantages that we'll learn about today can convey opportunities in terms of scaling AI and also achieving higher performing chips that can really lead to that critical AI leadership and expansive opportunity that so many people are focused on. There's a lot in quantum, both on the quantum energy side and the quantum sensing. And bio and ag tech. We'll hear today about how this is disruptive, the access to microgravity for many applications ranging from organ production. You know, today we'll hear a little bit about that, about tissue, about retinas. It's also worth noting that there's the potential to really turn the pharmaceutical model on its head in terms of ability to get to rapid aging. So some studies that would take years terrestrially, you can get that progress and that data in your pharmaceutical R&D within months. So what a competitive advantage. There's also the ability to iterate, do personalized medicine, opportunities in cancer research, cardiac health, you know, and also anti-aging, and then issues with neurodegenerative disease and how to improve those solutions. On the energy side, there's so many areas. Briefly, things like, I mean, we're familiar with solar, and there's also space-based powered ground that is being conceptualized, but areas such as fusion and other types of nuclear could really provide opportunity for build out and moving deeper out beyond our exploration today. Many areas with regards to infrastructure, materials, resources, critical minerals, platinum group metals. There's so much in space, and this is just touching the tip of the iceberg. This slide here just represents some of the early stage portfolio at the National Science Foundation. Many of these companies are also supported by NASA, DoD, Commerce, DOE, NIH, so many of the other agencies. So while this is kind of a snapshot of one portfolio, it's really interagency in terms of the number of collaborators and funders who have supported these companies as well. So just we'll quickly show you some examples. You know, as we said, there's many sectors of space economy, and there's some that are not fully covered here today. But both launch, I mean, it's incredible to see what the United States and US companies are doing in terms of leading launch globally. And obviously, there's so many things people are doing. And you know, as we look at, I'm trying to remember if it was Starship 5 I mean, this is a country that knows how to stick a landing, you know, so congratulations to the innovators who did that. And I know that was also something that some of that development, we actually have a colleague on the call who'll be joining later today from NASA, who is very active both at NASA and SpaceX in terms of developing their heat shielding for re-entry. You know, we have other companies as well that are focused on reusable launch, such as Stoke, and we've certainly got a range of platforms, many of the leading platforms and innovators who we are going to hear from today. So LEO destinations and other platforms, very important to have that infrastructure capacity and space to do the work. On the advanced materials, semiconductor and microelectronics side, the advantages, you know, in terms of yield, in terms of form factor, size, purity, materials and crystals that are not possible on Earth that you can create in space. That's something you're going to be hearing a lot more in greater depth and insight today from our presenters. In space biotech and manufacturing, we've talked about many of the areas, and you're going to be hearing from some great companies today. Curtis, before I flip this side, is there anything that you want to say briefly on the semiconductors and the bio or any of these others?
No, I'll address those in just a few minutes, and after you finish up, when I make some brief remarks, I would like to say real quickly for those of you that are panelists, if you could use a right mouse click on your picture and rename yourself from Space Disruptor Day presenter to your actual name, we may want to start the semiconductor session just a little bit early, and we can't tell who all's on right now. So if you would rename yourself, that would be most helpful to us. Thank you.
Thank you, Curtis. And today is going to be a day that it's going to be very fast paced. So we might, if we can, we might start off running a little early, and then we'll try to hold folks to time. But obviously everybody's welcome. Who's not a presenter is welcome to come in and out. And because there's going to be a lot of good things going on today, but it's going to be rapid fire. So on this slide, just wanted to share back to the in-space infrastructure, propulsion, power, energy, directed energy, mining. You know, this is just really the tip of the iceberg in terms of some of the companies that across the interagency we've supported. There are many here that aren't on this slide, but just to give a sense of some of those companies. There's a number of consortiums that are advancing the space economy. So we see in many of these cases, we might see hundreds of people coming together in an organization. And I can say that in areas that previously there might not have been as many people active, we're seeing inbound, you know, some of the entities that I work for where it's hundreds of entities want to come together to do types of research. So while there has in the past been, there had previously been more of a barrier to entry to space, this is something that a number of companies are working to make it plug and play and help, you know, this is the integrators, you know, and some of those with hardware, really make it so that it's plug and play so that you can, you know, if you're a biologist, rather than taking a couple years to become space capable, you work with space capable partners and they can plug you into an existing system, experiments, R&D, you know, whether you're a startup or whether you're a corporation. So that's something that as we look forward and we see the advantages in this field, we see the potential that if microgravity, as we are going to see today, conveys advantages for biotechnology, for semiconductors and advanced materials, we expect that there's a point that just like everybody wants access to a computer or wants access to AI or other advantageous capabilities, that we're going to find a significant percentage of all biologists are going to want access to microgravity. Those that are developing advanced materials, if you get those advantaged material properties in space, we're going to see a wider range of researchers, startups, and industry that are going to require that access. So a little bit of a canary in the coal mine on that, but it's happening quickly and we need to scale. Space communications and data, I mentioned that earlier, you know, across various areas, the communications, the internet, the position navigation and timing, the IoT implications. We talked about catalyzing launch, transport, and fuels. So, as the cost of launch goes down, space is becoming increasingly accessible. Reusability is expected to be a major unlock. And as my colleague Kevin Engelbert, who's on the line and might offer a few brief comments later, shares many times, space is a place. So expect to see ourselves doing more in space when there are those advantages. So this is a blank sheet intentionally, which is we're already seeing hundreds of amazing things, and we're sharing some of them today. But envision your boldest approach and your most exceptional advantaged opportunities and the things that we're going to build together. We're at that point in the scaling curve where we're seeing these 10x increases in participation. And then how do we scale to get the access? So in terms of scaling to get to the access, one of the things that we need to really do together as a community is bring that infrastructure grade scale. So when we talk about in-space manufacturing, when we talk about space-based power, we talk about global launch and satellite communications and bringing internet around the world, some American companies have done, we really need to recognize that today, the great things that we're seeing are coming from a significantly underfunded environment. So there's very little capital that has currently gone into the R&D in startups in this space. So, there's opportunity for orders of magnitude increase into the startups in the early stage. And then for the later stage companies that are looking at infrastructure, there's potential here to build out high value infrastructure. We're talking about bringing abundance and resources and resilience to Earth, right? So think of all the resilience you have from off-planetary assets, being on the moon, Mars, Leo, all these different places. But to do that, and if we look at the value, and I don't know the exact numbers, but I did the quick kind of internet searches a while back, the value of our pavement, of our roadways, is trillions of dollars. The value of our electric grid is well over 1 trillion in the US. It's trillions of dollars globally. If you think about the cost of hospitals, of stadiums, when we build things on Earth, we have access to all of the terrestrial tools. When we talk to people in space, they talk about grants, they talk about contracts from the government, and they typically talk about equity. Those are all good things. But when you build a power plant on Earth, what you're often doing is you might go up to 80% debt to equity. So you turn every dollar that you put in as an investor into $5 going into a space. So when we look at some of the budgets that have been deployed towards space, these are exceptionally small compared to our terrestrial infrastructure. So if we look at the ESDMD budget at NASA, that's about $7 billion. We've got programs across the federal government that put 10 billion into a single automotive company, or 7 billion into another single automotive company in terms of debt. Great tools to have terrestrially, shown to be advantageous to our industry, whether it's in automotive, energy, and these other sectors on Earth. But to reach these same levels of success in space, we need to open up these terrestrial financial tools. There are hundreds of billions of dollars of debt capacity in our existing US loan guarantee programs. Some of those loan guarantee programs could potentially work to make that capital available to space, because as Kevin Engelbert says, and as we say, space is a place. So you do energy in space, you do infrastructure in space, you do biomanufacturing in space. So some of these allocations, be they in the private sector or in the public sector, could be leveraged, upon the appropriate financial structuring to get these tools. The regional development financing, the tax incentives. Tax incentives have been so critical in terms of catalyzing large-scale investments into terrestrial industry. We need to open that up for space. Export credit agencies, private capital, foundations, prizes, and grants. We've been talking about this, but it's it's not meant to be an idea, and it's not something that a single person and a single agency does. It's not something that a single agency does. If we want to open up access to the terrestrial financial tools, this is something that needs to come from the broader ecosystem. So if you want that access to capital, go figure out how to build it. And of course, we're supportive. And just by the way, one of the active nations in space that well, I'll say who it is. It was China. We actually had China. A presenter from China had been invited. One of their space leaders had been invited over the past year to the National Mall. And, we were asking some questions about what they were doing, and there wasn't a whole lot of flow of information. Oftentimes we were met with, well, we're a new spacefaring nation, we can't share. But when we pushed on some of these areas and we were asking about budget and capital allocation, the person turned to us and said, well, when we think about a space station, that we just look at that like that's the cost of putting down a kilometer of metro. Basically, why wouldn't you do that all day, every day? And there are many in the US who have long felt that way. We've felt that way long term. But I guess the point is we need to get those capital tools in place, and others are doing so. The UK also has project finance tools that they're putting in place for their space sector. So this becomes a point of competitive advantage or disadvantage. And of course, the ability to bring that abundance and that growth both to the United States and then globally, with our partners and those with shared values around the globe, make it better for humanity. So just in closing out this presentation, all these large-scale businesses, they typically do in the United States start as small businesses. And in this sector, right now, we're seeing so much transformative innovation, and the opportunity is really to see what is the art of the possible and challenge the art of the possible. I've had the opportunity over the past 8 years to fund several hundred companies in early stage, in energy, in space technology, in data, AI, blockchain, DLT, and a number of other sectors. And from having gone through that process, what I can say is the most disruptive innovators, including some of the ones that they're the fastest growth, what they're finding, some of the fastest growth companies that you just couldn't even believe, how fast they go from zero to billion plus valuations. We hear from them that they went through 100 no's before they get to the first yes from investors. That's the fastest growth ones. And certainly there are many tremendous projects that are not actually even moving forward because they're not having that 100th conversation, or they're not as good as speaking to investors. What we find is these disruptive approaches at the early stage, it is most common that most experts, most investors, most technical folks will say, here's all the reasons this won't work. Here are all the challenges. And so we say, so if somebody says, how do we get to Mars instead of 6 months? We want to go much faster. Do they want to say a month? Do they want to say 2 weeks? Do they want to say a lot faster than that? And so it's common that if it's such a stretch, you say, well, don't bank your reputation on that. Maybe it's not going to work. This is the analogy of, this is very normal in the early disruptive stages. We say, if you had been on the beach in North Carolina and you had gone to your most eminent technical experts or your most eminent business people, there are many people said, it'll never happen, it'll never happen. And you say, so the Wright bicycle brothers, they had a bicycle shop, which was technically sophisticated at the time. Bikes were interesting, but they were a bicycle shop owners. They're going to fly. They say they're going to fly in the sky like birds. Thumbs up or thumbs down. Most people are going to say, not sure it's going to work. No, or you see him and you say, okay, you're going to go, you're exposed. You know how it went, and you can say, does your family know you're doing this? This looks a little bit dangerous, right? But so it's normal in those cases that if you ask 4 or 5 people, almost all of them are going to say never going to happen. Maybe one says, not sure, but there's something to learn here. Let's find out. At these early stages, sometimes it's a very small amount of capital, they can provide the difference between getting those proof points that lead to subsequent investment and really challenging the art of the possible. So I just want to open it up now, take down this presentation, or we can stay. Oh, yeah, we can stay, and then I'll go back to kind of overview of some of the day. We will be discussing some of the most disruptive approaches. And so there's all these fields that we typically talk about. And then across the interagency, we say this is a disruptive technologies day. So we also bring to you things that many of us are having hundreds of conversations on, but you might not have been involved in. So we've been increasingly hearing from experts in fields such as quantum energy, advanced human capabilities. And then also in space technologies, we say, what are the highest performing craft that people have reported as observed or who have shared they have worked on them? And so that brings us into the UAP topic. So these are areas we take seriously. We are open to all areas of innovation. We discuss them. We share the science, the industry, the development only moves forward when we iterate aggressively and when we bring resources to the table. So the types of things that we're going to be able to build by having the conversation and putting the funding in, it's a tremendous difference versus just projecting the line off of where we've been yesterday. So I would just share, got a tremendous group of dozens of interagency colleagues who are active in supporting the wide range of deep technologies, disruptive technologies, innovations. I realize most of them probably aren't on the line right now, but I did want to open up for the few that are for comments. Curtis, you're going to do an introduction as well, I think.
Yes, let me jump in for just a few minutes. And I wanted to share just a few comments, but then I wanted to talk a little bit about an overview of our agenda today so everyone would have an idea of kind of what's going on. Anna covered most of these areas already, so I really won't go into a lot of comments on them, but let me see if I can share I have a little bit more detailed agenda. It's not completely cleaned up, but it'll be good for you to see. Hang on just one second here. All right. This is a working document, but you can see our order of presenters in here. We have put into the chat approximate times for each one of these category sessions to occur. But if you want to make some notes here, this will give you an idea within those sections of approximately when the individual presenters will be up. Just in terms of personal interest and some comments here, obviously from my perspective, I'm with NASA Marshall Space Flight Center, and I lead the commercialization of semiconductors for our INSPA program, as well as the development of microelectronics and sensor technologies. So I'm sort of particularly interested in the first one, but we enable a lot of the other programs as well, as Anna said, through interagency funding and through some of our INSPA funding, which is, again, NASA's commercialization program. In semiconductors, you'll see a pretty wide range of participants there. For those of you that aren't familiar, I'm not going to go through all these companies, but just to give you some ideas, Flawless this year set a new world record for the amount of optical fiber that they fabricated in orbit on the ISS. So you're going to want to hear their presentation. We have some really high level, national, world level experts from Astral and United Semiconductors that are on here. We have some materials that you won't be familiar with, like 2D materials, which is the very latest transistor research that's going on here in the United States. I bet you didn't know that diamond is the ultimate semiconductor material in terms of wide bandgap high performance materials. And you'll hear from a company that's going to make diamonds in space. So that'll be interesting to you. And then we'll wrap up that session with one of the major companies here in the United States that's making memory chips. They're leading the fabrication or manufacturing of memory chips, which is Micron. And then Arizona State and Intel making comments about how we're going to be fabricating memory chips in space. Again, in biotech, wide range of technologies there, all the way from stem cell research to biotechnology research in rapid exchange of different materials in space to evaluate and gain microgravity data on many different materials. We have retinal implant manufacturing through Lambda Vision that'll be talking about that. I want, again, I didn't want to go through all the companies, but I wanted to mention to you there's some really compelling presentations that you're going to want to see in there. EED, for those of you who don't know what that is, that's extended electrodynamics. And those are things like an extension of Maxwell's laws and what we're doing in space research to create new fields of energy storage, new fields of sensing, new fields of power and propulsion. There's some incredible things going on right now, and the EED session will be very different for you. That's one you won't want to miss. Digital assets and human performance. We've got a fairly wide range of content in that particular category. We have the financial aspects of it through DigiFoundry and blockchain, but we also have human capabilities, remote viewing. I know many of you are going to want to see that. Entangled, Enigma, some of these companies that have technologies and are evaluating technologies that are at the tip of the spear and are very interesting.
Curtis, just to add to that, because I know, in the extended electrodynamics, so that has electromagnetism, that is one of the segments that'll have an emphasis on, if you look at some of the highest performing craft, if you see what would a UAP like performance propulsion phenomena look like, extended electrodynamics takes a cut at how you might build some of those technologies, but you'll also see some of that UAP style observation tech across other sectors as well today.
Okay. And then I'll keep going quickly here so we can get into our presenters. But the 2 p.m. session is really infrastructure, both moon infrastructure and LEO infrastructure and the associated energy and resources. So you'll see companies in there that are developing capabilities for moon research and habitation. And then, of course, our LEO economy that we're building out right now. Infrastructure is really where we are in terms of most critical needs right now. So we'll talk about that in that session. Associated with it really as infrastructure are platforms and launch. And you'll see all the big names there, many big names there in platforms and launch that you'll already be familiar with. Each one of those companies will be presenting, and I highly recommend that you listen in on that session to find out the latest in regards to what's happening with these launch and launch platforms. And then our last 2 sessions on communication and quantum. In communication, these are tip of the spear type communication technologies that you're going to want to see. I won't really talk too much about them other than the fact that they take advantage of the space environment, and they take advantage of electromagnetics that we talked about before through the EED session, and are developing some really unique approaches to communications that will probably be part of our norms going into the future. And then finally, quantum. And I'll just say a note of thanks there to Rima Huid from the Department of Energy, who's helping us set up that session. Under quantum, we're going to have quantum energy, quantum sensing, and some of the latest of quantum technologies that are being developed and enabled through our space technologies. So unfortunately, that's the last session, but in a way, that's good that that's the last session, because it's an extremely compelling topic, and I feel like many people are going to want to hear that. Now, just a quick word about timing. We are going to be rapidly going through these sessions, 5-minute. I think Anna said there's 55 different presenters here. So we're going to be holding you to 5 minutes. When you get close to 5 minutes, one of us will let you know you got 30 seconds left. And then at 5 minutes, we'll tell you that's time, and we'll start switching to another presenter. So please be aware of that. We're not going to be able to go long because there's just not time for it today. There's too many other presentations. So we're not being rude to you if we cut you off at 5 minutes, but please be aware that if you get close to 5 minutes and you still got 3 slides left, you better talk really, really fast. Okay, so I'll turn it back over to Anna, see if there's any other comments. We're getting close to the 10 o'clock hour.
Curtis,
where
do
we'll
we
begin our
have,
presentation.
because I know these first 2 segments have a lot of presenters. Do we have some of our semiconductor presenters ready so that we'd be able to get started right after a couple quick government comments if
We
Rima?
do.
So Rima, thank you so much for all your collaboration and partnering across all these areas. Do you want to share some brief comments?
Oh, sure. Good morning. Thank you all for having me. Many thanks to Anna and Curtis and the team behind all of this, pulling this together. Extraordinary day. I just wanted to point out that, for the Department of Energy, obviously, a lot of the topics here are of great interest. Semiconductors, materials, sensing technology is very much core to some of these activities. And this is where I think quantum is really going to shine. We're looking at quantum technologies, both quantum computing, quantum sensing, and quantum communications. I don't know if I'll be introducing anything at the quantum section, so if I should reserve some comments for that, but nevertheless, I just wanted to say that I think this is an opportunity for us to learn quite a bit and essentially pretend to be polymaths, because I think that when it comes to innovation and disruptive innovation, as Anna's been pointing out, being able to connect the dots between things that may on the surface appear esoteric, at the end of the day, there is some connective tissue there, and we need to pull on those threads to the extent that we can see synergies between these things that seem disconnected on the surface, but actually in the end makes sense. And this is how quantum kind of got pulled into this arena, because we realize particles act and behave differently in microgravity. And so there are benefits, and this can actually really accelerate some of the areas that we're trying to research and commercialize. So thank you all for having this extraordinary day and for letting DOE be a part of it.
Oh, great. I'm seeing it's so great to see you, Rima, and I'm happy to see that some of our other colleagues were able to also get out of whether it's the attendee side of the house as well. I just saw Dan's video came on from NASA. So Dan was the one that I was talking about, really led a lot of very important development relative to reusability, both at SpaceX and others in industry. Dan.
Morning, Anna. Yeah, I was able to navigate the Zoom retagging, so I got that done. So, yeah, thank you very much, and yeah, welcome everyone. And the one comment I wanted to make, everyone online, if you haven't, there's some really good videos and interviews of Jared Isaacman, okay, who right now is set up to be the next NASA administrator, and he has got quite a profound, I believe, vision for what space can become. And he makes a number of really relevant points, including the likelihood we're going to see the cost drop dramatically for getting payloads to orbit and back. And so it really is a change maker extraordinaire with the new rocket systems, Starship being chief among them, but there's others as well, New Glenn and Vulcan. And I think what Anna has kind of laid out is what we call the innovation frontier that we believe that we are now, opening up. And so there could be a large number of innovations, I believe, in a whole range of different technologies and disciplines. And as Anna also mentioned, we really want to be the ones opening that frontier rather than letting someone else do it and having to come in buy products from them. But yeah, thank you very much, and I really look forward to further discussion. When it's time, I can get into more detail of work that I've done with SpaceX and other space companies, and how pleased I am that some of the contributions that I've made are having impact as we go forward in space and opening this new frontier. Thank you, Anna.
Dan, thank you so much. And your work has just been, such a game changer for the space economy, as a whole. So it's really it's extraordinary what you've done, and that's something that deserves an hour or more to itself. So I'm wondering if we can get a podcast going with Diane. Diane, who is helping on the co-hosting, managing of the recording and participants today, leads Shoshin Ecosystemic Futures, which is a NASA podcast, and she's been very innovation forward in making sure we get some of the most disruptive and high performing technologies featured. Diane, would you like to make some brief comments?
Absolutely, Anna. Thank you. And thank you for the opportunity to collaborate on this event. What an amazing lineup. I'm super excited. And it's been, Anna, as you mentioned, such a pleasure to collaborate with you on the Ecosystemic Futures podcast as well, and many of our disruptors here today. SpaceWERX has been honored to collaborate with NASA and support the NASA Convergent Aeronautics Solutions Project in their futures work, their aerospace futures work. And a big part of that has been convening disruptors like this in order to showcase that work in a podcast series. So we're grateful for the work that you're leading and appreciate the opportunity to support it. We're also we're collaborating with the SpaceWERX team, many of whom are joining us today. And
Diane,
supporting.
we've got some tremendous colleagues, and I know you work very closely with both Space Force and Air Force. I'm seeing some of our DoD colleagues on the line. I think they might be on the attendee side as opposed to the panelist side. So I don't know that somebody who's on, they might be muted on the attendee side, but we appreciate that, we know that Air Force, Space Force, Navy, Army are in attendance at some point during the course of the day. So we're grateful for their leading work in space technology.
And many of our
course.
innovators as well. Our cohort companies are on the agenda as well. So we'll be hearing from them throughout the day as well. So thank you,
Tremendous
Anna.
portfolios at Space Force, Air Force, and others within DoD, DARPA. So grateful for their leadership in these spaces. So everybody on all of our government attendees, I think we're wrapping up the government point anyways, but the attendees can't come off mute, right, Diane? So we just say that we're glad they're there. We see
They
Noah and
can
others.
if they raise their hands, I can unmute them if
Okay, so
with confirmation.
yeah, so if anybody else on the government side wanted to say like brief comments, they're welcome to raise their hand. If not, we can move into.
I'll just say briefly that I appreciate Anna, you and Curtis putting this together, and within NASA, we've been investing in these amazing researchers and entrepreneurs now for 6 years, 7 years, and we're really picking up steam. That the companies are doing awesome work on the space station to prove what a tool microgravity is to enable these new technologies, these new materials, better products, and we're really excited for what's to come. And we also see that the ISS, wasn't designed for scaled manufacturing, so we really depend heavily on the commercial platforms of the future that are in development now, and we're anxious to see those become operational. We're anxious to see the launch providers increase cadence and support what's going to be an amazing industry in space for the United States that benefits everyone on Earth.
Thank you, Kevin, so much for your leadership in space manufacturing and these other areas, and for your co-chairing of the space economy over much of the last year. It's been great to work together. All right, so do we have anybody else with their hands up? I don't really see any. And I think we can move into, do we see hands up or? Okay, I think we've acknowledged some of the other agencies that are present, although there might be opportunities later in the day to say hello as well, because I know many folks are joining later. All right, so Curtis, do we have the presenters to get started on the semiconductor side of the house? Moving to our first session.
Who's the presenter for flawless photonics? That'll be first up.
That's me. Hi, Curtis. Hubert Moser.
Oh, good morning, Hubert. All right, so Anna, we're ready as soon as we can get. Are you going to bring the slides up?
Yes, I can. I just want to make sure I put up the right ones. Is it the same as the ones from last night? Were there any
Yes.
differences to that deck? Okay, so I'll just put the deck that I
Bio.
put out.
Yeah.
Okay. Let's see here. All right, so I've got this, and there were a couple changes. I wasn't expecting to flip the deck today, so I won't be able to do any. I won't be able to do any of the organizing in the background. Okay, so let's starting with Flawless. Flawless, take it away. Welcome.
Thanks a lot, Anna and Curtis, in general, for organizing that great event. It's quite an honor to be first of those who were enjoying the support, as Kevin mentioned, since a couple of years. We at Flawless Photonics, we are doing everything around a material that you might have heard, Zeblan, a crazy mix of fluoride glasses, fluoride powder that don't want to be a glass. And as soon as you heat it up, it wants to crystallize. And contrary to the others that we will hear today, we don't like crystals, because crystals mean lower strength of our glass fibers and higher attenuation. What we've proven with the support of a lot of agencies across the globe, actually, is that production of a commercial length of this fiber is possible. Production in space is possible. On the right, we see one of the great colleagues that helped us up there, Laura O'Hara. She did a super fantastic job in helping us to install our machine together, and also helping us to exchange raw material, little glass sticks, and removing spools full of fiber. Several kilometers, I think in total, more than 11 kilometers, pieces on average 700 meters long. And we got them back in early May and started quite a extensive measurement campaign together with the 5 international organizations across 3 continents. But all in all, what we could already say before we started to look at the fibers is that this was full mission success. On the next slide, there's a little more data on what it means when we look a bit more in detail onto the fibers, exactly that one. So what we did is we used our machine here on Earth, produced some fiber from similar preforms, and we compared fiber that was drawn here on Earth with fiber that was drawn on the International Space Station in the MSG. 3 takeaways. The fiber that is produced in space is stronger, up to 2 times stronger. You even feel it when you're handling it. It breaks much later than when you have a Zeblan fiber that is produced on Earth. And we have significantly lower attenuation, up to 10 times. We had a couple of outliers in our measurement data that went up to 30 times, but 10 times is a good average. and we have higher uniformity. That means that we get longer continuous length, not only 10-meter pieces that have a good attenuation, but up to 300, 400 meters of, we call it usable fiber, with a decent attenuation when we're producing in space. We also started to investigate the performances in terms of lasing, when the fiber is lasing, so for free space optical communication purposes, for instance, in wavelengths, where CBLAN is a key material, particularly in the mid-wave infrared. That's where we see applications as at free space optical communications. But there's another line of, I saw in the beginning, we were listed under communication. Our, we call it moonshot. We have it on the next slide, is producing fibers that are at a much different scale, at a much different length. Right now we are producing, we call it short format fibers that are going up to a kilometer length. And we are selling them in pieces between, say, 5 meters to 50 meters, roughly. But what we want and what we are starting to work at is to produce thousands of kilometers of fiber. And as Kevin said, this is the point when we might reach really the limits of what the ISS is giving us. On the next slide, if you could maybe go one slide further. I listed a little bit the next steps that we have in mind. First of all, producing more short format fiber, new types, new fiber types, new designs, hopefully in, say, first, second quarter next year. So resupplying our machine that is up on the ISS and getting fibers back. And then another project that is pretty important is somehow with the fibers that we've produced up there, we saw that the quality of the preforms is what determines the quality of the fiber to a certain extent. Improving the quality of our preforms is one of the key elements that we're working right now together with NASA, ISS National Lab, and NSF. And that's going to be a key element in our production chain, that we can, first of all, automate also that portion of the process. Fiber drawing and preform making is considered an art here on Earth, and we automated it because it was a necessity. And with those two elements, and the first two bullet points, we're going to go forward to long format fiber, which we will very likely have to do in a dedicated autonomous or even human-tended, but commercial LEO platform. So that's the future that we're looking for. Point 4 means after ISS or in parallel, the earlier the better, as Kevin said, and producing short format fiber and also long format fiber for use, first of all, here on Earth, and then also for the short format fiber, of course, when we talk about free space communication, that's also going to be an application case for spacecraft, aircraft, down to Earth. Thanks a lot.
So much, Hubert. And this is obviously a huge growing market, you know, that could be even larger with these low price points. And certainly we're going to hear many examples of where a kilogram can really be, okay, there's a cost of getting a kilogram up and down, but the value of the product produced is just, you know, across some products can be hundreds of thousands or millions of dollars. So per, you know, some of these lower mass quantities. So I think we're at time, but thank you so much. And do we have Curtis, do we have Jessica on? You're on mute, Curtis.
Yes, Jessica Frick with Astral Materials is next.
Great.
Jessica?
Yep, I'm here. Thanks so much.
Okay, next slide.
Welcome.
All right, awesome. Well, I'm Dr. Jessica Frick, CEO and co-founder of Astral Materials. And we manufacture materials that cannot be made on Earth at a quality and a consistency. And we are a new company, just started going this year in April, but we're not new to the field. So my background is in semiconductor crystal growth. And during my PhD, I realized that gravity was a wall. I could not achieve the quality, size, or consistency because I was on Earth. And so in 2019, I joined Professor Debbie Sineski's group at Stanford as a postdoc, and we moved our research into space. And it was from that research that we realized the commercial potential of moving crystal growth off Earth. And so let me just introduce the leadership team briefly. Professor Debbie Sineski is our co-founder. She is a world expert in beyond silicon electronic devices for extreme harsh environments. She's an associate professor at Stanford University in aeroastro and electrical engineering. And Jaya Janowitz is our CTO. He's also an alum of the Sineski Group, and he brings a wealth of knowledge in microgravity hardware design and building that he has put up into orbit and onto the ISS. And together, our team has over 3,000 hours of in-space experiments. So next slide, please. So I really like the distinction that's been going on during this call about space as a place, as Kevin would say, because it's not space that we care about. It's microgravity. If we could access microgravity on Earth, then we'd be an Earth-based company. But this slide here really shows what microgravity truly is. We see microgravity as a manufacturing tool that will define humanity's next age. Just as temperature enabled smelting, which enabled the Bronze Age, pressure is a a manufacturing tool that enabled steam power, which enabled the Industrial Revolution. Vacuum is a manufacturing tool where removing air and oxygen enabled the digital age. And of course, microgravity, we're not really sure what it's going to enable, but it will enable the next age because gravity is no longer a constant, but a variable. Next slide, please. And so what I mean by gravity on Earth is the way in which gravity manifests itself as physical phenomena. So on the left here, we have physical phenomena that are detrimental to crystal growth on Earth. So container interactions, flotation and sedimentation, thermal convection, hydrostatic pressure, all of these lead to a low quality, inconsistent crystal. Whereas in microgravity, we can do contactless processing, diffusion-driven mixing, there's no natural convection, and we can have homogeneous pressure that gives ultra-high quality, consistent crystals. And so specifically what Astral Materials is doing, which has been funded by NASA SBIR Ignite, and we actually have our program manager, Dan, on. Hi, Dan. We are building a crystal growth furnace using microgravity as a subsystem. And so just like furnaces on Earth and many other technologies use gravity as a subsystem, we're using microgravity. And that allows us to simplify heating, mitigate impurities, circumvent weight, and get homogeneous mixing. And all of this is to say, we can grow crystals that can be grown on Earth, but of a much higher quality and consistency. And then in the future, what this is going to enable, it's going to enable us to discover new materials, to discover new types of metastable phases and isolate those, because not only will we have the variables of pressure and temperature to manipulate, but we have acceleration to manipulate. And we can go into the third dimension of phase diagrams for materials. And so I think my time is almost up. Please reach out. I have my contact information lower left. And thank you so much for adding me to today's agenda, guys.
So much,
Thank
Jessica.
you. Hey, Jessica, I just wanted to say thank you very much. That was excellent. That was a particularly novel chart you had in there on the timing of temperature to pressure to microgravity. I hadn't seen that one before, and that's pretty cool. But it really shows where we are, and as you say, if we could do microgravity on Earth, we would, but we can't. Thank you. That was an excellent presentation.
Very much appreciated that insight and that vision, Jessica. And I guess it also lies with what I suspect she and many others are seeing, which is that this really is it's the next industrial revolution, which ties to many of these earth industries as well. So really appreciate that historical tie-in to the major value drivers. Okay, United Semiconductors. We have Partha on the line.
Yep. Good morning, everyone, and thanks, Anna, for this invite. It's a wonderful program all throughout the day. I want to be presenting the United Semiconductors focus. So we are a company making substrates for the last 20 years, and we meet critical national needs for US DoD as well as some commerce. And we have this integrated platform that we are developing. So we have been doing terrestrial crystal growth for the last 20 years in the company, but of late we have been trying to integrate our mission is to integrate the terrestrial and in-space semiconductor crystal growth manufacturing process in a way so that we can leverage the lessons that we have learned terrestrially for the last 20 years for space manufacturing, and then enable materials that cannot be manufactured on Earth. So like Jessica mentioned, there are certain materials that cannot be manufactured on Earth, and we have identified those applications and materials that requires microgravity for manufacturing them in quality and volume that's required for end applications. So within the company, we have different applications that we serve for our customers, all the way from radiation imaging, which is the longest one, then getting into augmented reality, neuromorphic computing, of late, wide bandgap semiconductors, and full spectrum solar cells. We also do an intense workforce development for school and college students at our facility here with local colleges and universities, giving them the real world experience, hands-on experience in our state-of-the-art facility. Next slide. And I forgot to mention that we have good funding agencies and sponsors and customers who actually have enabled these development over the last 20 years with the state-of-the-art crystal growth facility that we have today. So specifically, I like to show you some of the things that we do in our facility. So the bulk crystal growth, and we are a small bulk crystal growth and substrate foundry, focusing on niche materials. We don't do silicon. We are non-silicon based foundry. We do 3-5 compound semiconductors, which are used in many applications in DoD. Specifically, critical electro-optic and infrared optical components are the kind of products which have reached a TRL level beyond 8, used in systems these days. We are the only domestic supplier for 3-5 optical grade binary substrates, and we are the only global source for 3-5 ternary semiconductor bulk substrates. So these substrates are not available anywhere in quality and volume that's required. On this chart, you see our facility with large number of furnaces that we have running in parallel for doing crystal growth, up to 6-inch diameter, and these are very large crystals for these kind of compounds. And you can see also some of the optically clear parts that have been developed from these crystals that are used in systems. We are vertically integrated all the way from compound synthesis, purification, crystal growth, and substrate processing. So we do everything that is required for the end substrate that is required for the real world application. And then the customers use these for different applications in different form factors. Next slide.
Am I sharing your image, Partha, or am I sharing this? Do you see the PowerPoint or do you see yourself? What am I projecting?
The PowerPoint.
Okay, good.
Yeah. I would have mentioned to you otherwise.
I'm seeing you in my full screen, which is nice as well.
Yeah. Okay, so let's get to the next slide, Anna.
Okay, did that flip over for you?
Nope.
I'm going to stop sharing, then I'm going to share again. A second.
Okay, so today I want to talk a little bit about the future of in-space production applications. I'd like to thank Kevin Engelbert from NASA, Curtis Hill, Anna Brady from NSF for really supporting this work so far. Our first payload experiment started 2 weeks ago at the ISS. That was amazing to see the crystal growth ampule getting into the furnace, subsea furnace. And I would like to talk about what we want to accomplish with the first experiments that we are scheduled, that is happening at this time as we speak in the ISS. So we are growing this compound, which we call a semi-metal semiconductor composite, which we have manufactured terrestrially for many, many years, and we supply to our end customers in the DoD world. And this is used in magnetic sensors. And the issue with that is the volume, the yield of this material terrestrially grown is really low. It's less than 2% from materials synthesized to end products. And we anticipate that microgravity is going to enable the higher yield of this material. And by the virtue of absence of gravity and buoyancy and other effects, we're going to be getting materials which we can grow these materials in higher volume. And this material also has microstructure that is important for the end application performance. We call it the figure of merit for the magnetic sensors. And we anticipate that with microgravity, the figure of merit also is going to improve by a factor of 2 to 6. And that will enable this kind of devices in large number of systems, both in the DoD world as well as commercial applications. And that's just the starting point. So with semi-metal semiconductor composite, these materials, they are unique materials that is a good example of where microgravity can enable materials crystal growth in microgravity in the form factor that is required for end application. These kind of materials, they've got many other applications. We are starting off with magnetic sensors, but all the way from quantum computing, energy storage to detection and photovoltaic power and thermoelectric power. So these are all different applications that we are going to anticipate going forward with these kind of materials. And space really enables a new platform for manufacturing these materials in large volume and figure of merit that is required for end applications. In parallel, we know that for space crystal growth, we need to design and use systems that are very different from terrestrial crystal growth furnaces. So we have a NASA program right now where we are designing an ultra high temperature furnace for wide bandgap semiconductor materials growth. We also have container design that is funded by NSF. Thanks, Anna, for this wonderful funding, which enabled universal container design, which can do different kinds of materials using the same basic design. So we can do 3,5 compounds, 2,6 compounds, silicon carbide, you name it, with the same design, except swapping the materials that are compatible with the material that we want to do for crystal growth. And this can be done in large volumes. So we have this universal container design that we can do. And the third part is when we have these materials, which are premium materials from space, we also have to have the right kind of processing infrastructure for making device quality wafers. And because right now, terrestrially, we use things like wire saw and blade saw that literally waste a lot of material. And we are developing with the NASA funding a wafer processing tool that's going to translate the space grown materials into end device product with minimum amount of loss and higher yield, so that we can utilize those materials much more effectively and also bring down the cost of space grown materials. So that's pretty much in a nutshell what we are doing with the in-space production applications. And we look forward to the exciting future of microgravity crystal growth and materials production, and with the end applications in mind that are unprecedented at this point, that as we see.
Thank you, Partha. And we appreciate both the material advances, but also this point that you have about really accelerating this high throughput. So this was one of many projects that really fit into an interagency initiative with the private sector, more shots on goal. How do we do a lot more innovation, in the capacity and the infrastructure and the throughput we have? And Curtis and others have been very active on that as well. Curtis, do you want to add anything before we go to the next presentation?
Well, I just wanted to mention here for the audience, which is pretty substantial, Partha and United Semiconductors has an experiment that's just come down with SpaceX flight. It might be if you could just take a moment to mention that. And I would encourage those that are coming later that have experiments that are flying now or just flown to mention that, just so that you know how current some of this research actually is. So go ahead, Partha, just real quickly mention that, and then we'll move on.
Yeah, so as Curtis mentioned, SpaceX 31 was launched our payload into ISS. We have 4 payloads that are going to be used for crystal growth, and they are going to be back via Crew 9 in mid-February to late February. And then we are going to process that material and compare them with terrestrially grown microstructures. And that's going to really accelerate the development of, and based on those understanding, it'll help us design manufacturing scale processes to grow large volume crystal growth in space. And as Curtis mentioned, we also have discussions with other space industry partners, commercial partners, to develop processes that are large volume, high throughput, and that can be done on different varieties of materials, not just one specific material. Again, this particular payload that is the crystal that is growing right now in ISS is a good starting material. It's a good model material. But the future is unprecedented with a large number of things that we see needs to get done in the next future.
Thank you, Partha. We'll talk a little bit more when we get over into launch platforms, some of the things we're doing on external platforms and doing experimentation development for those new external platforms and launch vehicles. But thank you for sharing that. And now we'll move to David at Gopert.
Hello, everyone. Can you hear me?
Before we dive in, I just want to share, we obviously went a little bit longer on Partha's. If we're doing well on time, because we were earlier in the last one, to the extent we have the ability that biotech presenters are online, we'll probably start that a little bit before 11, because I know there's a lot of bio presenters, there's a lot of EED, UAP presenters coming in. But we're not going to run a half hour or 40 minutes, ahead of time. So it's also possible that we might spend a little bit of that time after presenters with some light, kind of talking vision and some of your other bullet points for space for the presenters that are in this group. Okay, great to see you.
Hi, thank you. So thank you, Anna. Thank you, Curtis. My name is David Nedzwicki. I'm a senior scientist at Gopert LLC. We're a Philadelphia-based company, and we work on advanced semiconductor materials. So today I'm specifically talking about two-dimensional materials. These are materials that are atomically thin. And I'll be talking about molybdenum disulfide. So this is MOS2. So when I say MOS2, it's molybdenum disulfide. So what we've been working here at Gopert is a furnace that is able to grow this MOS2 material at atomically thin layers at low temperatures so that it can be CMOS compatible. This is technology that was developed originally at MIT that we've adapted and are now trying to adapt toward microgravity research. So I'm excited to tell you about how this kind of MOS2 could be adapted for microgravity and what kind of benefits that might have. So just as silicon revolutionized electronics in the 20th century, two-dimensional materials are the kind of forefront of new semiconductor materials. They're atomically thin, and MOS2 specifically has a direct band gap. So there are a lot of advantages to these materials, specifically in miniaturizing transistors, but also for flexible electronics and for valleytronics for quantum computing. There's a lot of research that's actively being done for this material. So why is microgravity important? We've had some great presentations that explain that, but specifically for our furnace development, there are a few particular things to keep in mind. One is the effect of buoyancy and temperature on the quality of the growth. So there are several gravity-driven convection that creates turbulent flows, and this can disturb precise mixing of precursor materials. There's sedimentation that can cause uneven distribution of reactants. Thermal convection can lead to temperature gradients and result in non-uniform growth. So these aren't just minor inconveniences, they're pretty much fundamental barriers to achieving material quality that's needed for next generation semiconductors. What we're really aiming for here is growth quality where we don't have defects in these materials and we have single crystal growth over large areas. So even the most advanced terrestrial processes can't fully overcome these limitations. But when you get to microgravity, all of these constraints just simply disappear. You can create far better control over vapor transport and mixing and better temperature profiles. So GoPRT's been working with NASA support and recently support from the NSF to adapt our furnace to in-space flight. We have several designs for adapting our MOCVD system so that it can perform on ISS. You can go to the next slide. This is just some pictures. So, right, for microgravity synthesis, there are several things we have to take care of. For our in-space furnace, we've designed it so that all of these precursors are well maintained and safely stored. And we have heating elements and insulation with water jackets that could properly maintain the thermal process. I have some pictures of MOS2 growth in the upper right there. So these are atomically scaled images from a TEM of some of our growth here on Earth. And you can see probably that there are little defects in the sulfur vacancies here that can create problems for the electronic properties. But we're hoping to overcome these defects when we move to in-space growth method. I see I'm running a bit out of time, so thank you for allowing me to present, and I'll stay on the line.
All right, thank you very much, David. Just as a wrap up here, the particular interest in this material, this 2D material, ultimately will be to be able to make much thinner devices and to be able to push Moore's law for the density of transistors in an integrated circuit to a much greater amount. So we're very excited about this potential and what space and microgravity science can do to enable these capabilities. So thank you again, David. Next, we're going to be moving to single crystal diamond, and I think Bill will be our presenter there.
Yep, just coming off mute here. Very good. Hold on. Just coming off mute. My apologies. Had a camera issue.
Okay,
there.
You're good. We can hear
All
you.
right.
Great to see you.
Thank you. So thank you for allowing me to speak today. My name is Bill Drumishauser. I'm one of the founders of Single Crystal Diamond. I'm here today to discuss the promise of diamond and the potential importance that it could have on improving many elements of our society. And we'll also discuss collaboration with NSF, NASA, and the commercialization path of semiconductor diamond utilizing microgravity. It's been widely known amongst the scientific community that diamond presents tremendous promise for an array of optical, electronic, and semiconductor applications. This is due to the superior properties of diamonds such as hardness, thermal conductivity, resistivity, and optical properties. So why hasn't it been fully exploited? The short answer is it's very difficult to grow and fabricate. And as a result, there's no large substrates to allow commercialization of devices. And frankly, sufficient investments have not been made by the private sector and or by the government. So let me provide a little further context as to why single crystal diamond's here to talk. We began the diamond journey 25 years ago at a company called Apollo Diamond. We invented CVD, single crystal diamond growth. Our core team were prominent semiconductor scientists who were responsible for advancement of cell phone and satellite dishes utilizing gas, and were the core people at Apollo. So since that time, however, Al Jenis, our CTO and founder, has received 21 patents in diamond growth, fabrication, as well as device work that is foundational to making diamond semiconductor material reality. Second slide there. So let's talk about some of the foundational elements that have been accomplished by the team. The pictures illustrated on the slide here are some of the technologies that have been developed. Large single crystal diamond growth up to 1 inch. We have a path to 4 inches. Laser separation technology necessary for large diamond production. We have high purity material for quantum technologies. We've developed fabrication processes to create surfaces smooth enough to achieve bonding for heat sinks. Diamond conducts heat significantly better than other materials. Some of the other critical device areas include those listed on the slide. Diamond has 10x the power handling for high frequency devices, enabling better communications. The superior power handling of diamond can improve automated AI smart grid switching. A diamond the thickness of a hair can stand off megavolts. In the upper left, you'll see a picture of a proton irradiation dosimeter that was developed. This could be used across over 2,500 hospitals across the country to prevent radiation overdosing of their patients. High-powered lasers can be manufactured due to the optical properties and the ability to withstand heat. Water purification, electrolysis using diamond plates to getting nitrates from water to make our water more pure. The work we are currently embarking on with NSF, with the cooperation of national labs, is foundational to ultra-wide bandgap semiconductor. Our phase 1 initiative is developing a nitrogen matrix from 12 separate growth runs to determine levels conducive to producing photonic diamond and active diamond layers. We see this as foundational and synergistic to the work with NASA. The terrestrial grown diamond can be used to further optimize material grown in space. Slide 3, please. The goal of NASA initiative is to develop CVD single crystal diamond platform that can be utilized in manufacturing of diamond in space. So why space? Much like Jessica and David just mentioned, microgravity provides a much better environment for diamond growth. We have the ability to control nitrogen and other dopants that allows us to create uniform active layers that are essential to a variety of applications. We have a commercial path. It's 3 phases. The first is to create a prototype, or the design is underway today, to grow 7 to 10 millimeter diamond in space over the next 3 years. The second phase is to create a pilot, which would scale this diamond production to 2 inch. And in conjunction with Axiom and other partners, we'll achieve commercialization in the phase 3. In closing, the program at NSF and NASA will advance diamond semiconductor. The material that we grow in space can be used to replicate devices on Earth. One grown diamond will allow us to produce hundreds of device layers, making these diamonds in this process commercially viable. I want to reiterate, diamond is a game changer, and the U.S. can be a leader in the advanced material, but there needs to be organized attention and commitment. It's a great opportunity for us to be leaders to develop this technology. We believe single crystal diamond is a cornerstone of making that happen with the government's assistance and commitment. We look forward to making this a reality so we can improve many problematic areas in our society.
Thank you, Bill. This is an area that we're just now beginning, as Bill mentioned, as I said earlier. and we're really excited about what may happen with diamond growth here over the next few years. As Bill mentioned in his application area, he just touched the hem of the garment. There's so many areas in wide bandgap diamond that can be utilized. And of course, occasionally people like to wear the thing. So that will be of interest too. The gemstone quality diamonds as well obviously has commercial potential. But thank you very much. And we're again excited about the potential of this project. As we transition, we have one of our major
Bill, thank you so
manufacturing.
much.
Oh, yeah. Thank you, Anna. I wanted to mention, just by way of quick introduction, we have Fabio here from Micron Corporation that will be presenting next. Fabio is a fellow at Micron, and we were very excited about adding Micron to our presenters because they represent the large commercial manufacturing segment that many of us will ultimately see as a target for the in-space application of some of these technologies that we're developing. So we look forward to your presentation, Fabio.
Thank you, Curtis. I hope that you can hear me and see me fine.
We can.
Okay, thank you. And well, it's really an honor for me to be here today in this very nice and great event for the Space Disruptors. And if Anna, you can go to the second slide. I just would like to give all of you some information of what Micron does and who we are in the semiconductor arena, if you don't already know. So we are the only US producer of DRAM and NAND technologies. You may know these two technologies, but they are really in all the electronic instruments that we are using, PC, phones, wherever you can imagine, data servers. In particular, DRAM that you see at the very top of the slide is at the core of all the random access memory, the fast memory that we have on our devices. As you can see, 1 alpha and 1 beta refer to the dimension that we are printing today. So we are printing dimensions that are sub 20 nanometers. So 1 alpha, 1 beta, that's the meaning. And we are, as Micron, we have been the first to market with the 1 alpha, and we are again the first to market with the 1 beta. We have been doing that technology leadership for both DRAM and NAND over the last 4 technology nodes. So you can imagine the scale of our economy and how much effort we need to put into the development of our technologies. And as you can see at the very top right, these DRAM components go into the low power double data rate devices, the double data rate devices, and last but not least, and very fast growing, the HBM, so the high bandwidth memory that maybe some of you heard being the core of the AI revolution and be used extensively by NVIDIA for all their AI-based training systems. And beyond the DRAM, we have also the NAND devices. Those are the devices that typically go into the solid-state drives that or into the USB keys where we store our information. So these devices are not volatile. So if you remove the power, they keep the information for a long amount of time, also in extreme conditions. And as you can see at the very bottom, we have been through 9 generations of these devices. And maybe the picture doesn't give the idea, but that skyscraper that you see over the G9 number is built with more than 200 layers of memory built on the same silicon wafer. And also on this, Micron has been at the very front together with Samsung, Hynix, and other companies of the production for these solid state memory and storage devices. So this just to give a picture of what we are, and our economy of scale, as I said, is pretty big. We are talking about revenues between 4 and 8 billions every quarter, depending on good versus bad years. This is a particularly good year because of the AI revolution coming with the HBM and with the NVIDIA devices. And if you go in the next slide, maybe there we have the part that may be more interesting for all the people also connected to this conference, because this is where the research is going, and actually where I do most of my work. The previous slide is the work that we are doing for our production. Here is the work that we are doing for our research and for our future. So as you can see on the very top right, there is a pyramid of memory devices that goes from the top, super fast but very costly devices. At the bottom, slow, non-volatile, but very cheap devices. The very bottom is the old hard disk drive that you may remember, magnetic built. In the middle, between the DRAM and the NAND, there is still space, both in terms of cost, a huge space in terms of difference of cost between the two, but also in terms of performance, so the speed at which the device operates. And in that space, through the last, I would say, 20 years, there has been a lot of research trying to find the perfect memory to fit that space. At the bottom, you can see some of the candidates. Some are past candidates, some are still there today. You have the FERAM, the ferroelectric random access memories. You may have the PCM, on which I worked for several years, the phase change memory. So memories that are based on the change of a phase from crystalline to amorphous of the material. You have magnetic RAMs. You have resistive RAMs that are based on filaments, either metallic or oxygen filaments. You have also the very bottom right, what we call the 3D crosspoint, that was an evolution of the phase change. And it is a very dense and very fast and relatively cheap memory that can really fit in that storage class memory region that you see highlighted between the main memory, the DRAM at the top, and the mass storage that is the NAND at the bottom. And our industry, our company can look at all the very nice and beautiful advances in the microgravity from 2 points of view. From one point of view, obviously, development of new material may be important, if not critical, for this new technology that we are trying to develop. But on the other side, we are also able to supply materials and solutions that are useful for the space application, radiation hard applications, for example. As you may understand, our typical interest is into our production. So we typically look at very large scale solution, but we are still involved into small projects also with DARPA and other agencies to find, even if small solutions that could be for devices, but also for AI applications. Those are really exploding, I would say, in the near term. In particular, if we can find solutions that are power sensitive, because the real new frontier that is emerging for all the semiconductor production is the reduction of the power. Now we have very fast devices, very cheap to some extent in terms of dollars per bit devices, but power is becoming more and more of a concern, in particular into the AI. And I can imagine that in space, it's even more a concern given the small, let's say, space and that you have and the need to stay very power limited. So just to conclude, I think that our research and our future research into these alternative technologies can really find synergies with all the work that you are doing and enabling with the space evolution. Thank you. Thank you very much for your time.
Thank you, Fabio. That was just for context for everyone. The semiconductor memory market is hundreds of billions of devices a year, and so from a standpoint of a market entry and target for microgravity devices and the advantages they may bring, we're especially interested in that, and we really appreciate you coming, Fabio. That helps a lot in terms of information and background. So thank you for joining us today.
Thank you. It was really an honor. Thank you, Curtis.
And we'll conclude our semiconductor session with Dr. Daphne Chen from the Arizona State University. She is representing the Intel team and what we call our SEEDS team, and she'll explain that in just a moment.
Hello. Thank you, Curtis. Thank you, Anna, for having me on this great event. And can everyone hear me okay? Okay.
Yes.
So yes, thank you. So I will start really quick. And first of all, I want to thank you, Fabio, to be able to attend this event to give an introduction about memory. And so I'm Daphne Chen, and I'm currently the professor at Department of Electrical Engineering, as well as ASU Center of Semiconductor Microelectronics. And today, I would like to talk about the space-enabled semiconductor microelectronics for the future manufacturers and manufacturers in space. So as we know, that recently has the semiconductor manufacturers has the opportunities, but also the shortage of the domestic manufacturers, and that's really the focus point that moving forward for the technologies, not only included memory, but also the transistor and all the logic circuit. But today, why I'm here to talk about the memory, why we choose memory as a key technology to moving forward, because the short answer is memory can be shaping the next decades of semiconductors, not only storage, but also computing and security. So due to the time limit, I will not be able to go through each of the bullet points for the applications for based on the new memory. But as I listed here, so there's main categories that memory can be touch base on. And for C's team, that we included, we are the team that with the 4 universities from Arizona State, Iowa State, Oregon State, University of Wisconsin, and also the industries, 7 industries participation. So thank you very much. And thank you, Anna and Curtis, for the generous support on all the research. So I really appreciate that. So can you go to next slide, please? Okay, so this is a slide going to be explained what SEES is about, space-enabled advanced devices and semiconductors. And I will split into 3 directions on this roadmap. One is materials and printing technology. And second will be device and process design kit towards the circuit. And the third one will be the roadmap and what's the current status of this. So as I mentioned, the technologies and for the memory is the key because it can serve not only the storage but also the computing based on, for example, neuromorphic computing, logic computing for the future. So that's the reason why we're focusing on memory. And as well as that, we know that there's a certain space limitations in the space region. So we want to realize high volume manufacture, but as well as we want to make it into more compact facilities setup. So the technology we are using is electro-hydrodynamic printing, EHD system with a real-time monitoring, as well as the AI automation, as I show in the left-hand side. And then we're moving into a oxide-based ink because we realize that the oxygen distributions in these ReRAM systems will be able to enable to enlarge the memory performance. So I will talk about on second category, but I mean, in this kind of materials and inkjet printing technologies, we will be able to make not only 2D planar devices, but moving to 3D. So we found that the inkjet printing has a very good enhancement and also be able to implement it onto the sidewall of the trench and also make it to 3D. So when we're making the device to 3D structure, we can highly compact all the devices into the trench structures, and that will be enlarged a huge amount of the memory densities, and that will be enabled to have a much more higher performance of the storage and as well as the computing. And the second perspective will be talking about the device and device PDK that each of the companies will be looking for. So Intel, TSMC, Samsung, Microns for the circuit design, that's all based on the PDK. So we are building up the PDK on the basis of DCIV as well as AC response. So time zero performance as well as known as the memory window, voltage area dependency, thickness dependency is under investigation. And also the AC response for the pneumorphic computing, LTP, LTD, STDP, fast IV, and action potential for mimicking ion channels in human body. Those are also under investigation. And moving forward, we are also caring about moving to the high volume manufacturers, the reliability. So retention and also defect modeling are included. And moving forward, we'll be targeting on the transistor and memory hybrid design for back-end offline integration, leveraging the microgravity. So we realize that the current status, we compare the flight sample to the ground sample, we found the power has been dropped 12.59% based on the voltage drop, and as well as still remaining the memory window for the 2 order magnitude. So this is very exciting, and we are still investigating the science beyond that, because we thought that oxygen vacancy play a role differently in microgravity, under the microgravity environment. And moving forward, after we have been developing devices and with a reliable manufacturers, we will moving forward using the PDK to realize the small circuit of memory circuit, and also using the 2D and 2.5D wire bonding technology for packaging product. So due to a time limit, I will not go through each of the details, but less of the aspect by third aspect will be the roadmap. So we are here at the point that at 2024 for materials and device development, we have been completed several very good successful parabolic flights, so we can be able to compare the performance of memory devices with the groundwork. And we are putting a lot of efforts and devoted the efforts into the modeling as well as the manufacturer's optimization. So please allow me to echo again why resistive random access memory. We can do storage, we can do computing. It's simple structure, cost efficient, low power, and most importantly, is physically secured. So we are not relying on software algorithm. We are actually secured all the customers' information into based on the microstructures, and that is thanks to the microgravity's effect. So I will stop here, and we will be love to collaborate. And thank you for giving me this opportunity to speak on this exciting event. Thank you very much.
Thank you so much, Daphne. We appreciate it. There's a lot of data packed into a slide there, and so we appreciate you taking the time to explain that. This wraps up our semiconductor session. As you can probably tell from listening to these individual presentations, we could have gone for hours just on semiconductors and still had plenty to present. But this is sort of whetting your appetite. You can see the technologies and the activities that are going on, and we'll be doing the same thing as we move into these other technology categories. So our next transition will be to biomanufacturing, which has been a long-term focus of our research on space shuttle and later on the ISS, and continues to be a target of research. Not only for commercial needs, but for human benefits as well. And we'll have many presentations here that will be talking about the benefits to each one of us that can be enabled by space research and microgravity benefits. So Anna, comments on the transition?
Just wanted to say that deep appreciation for all of our colleagues working in this field, in the private sector, and just driving this from industry, leading semiconductor microelectronics corporations, high growth startups, researchers at university. We really had enough to do a full day on in-space semiconductors. This is one of the areas that there's tremendous interest and relevance across the interagency. Many agencies have been asked to really help fortify the U.S. positioning and build towards new leadership in semiconductors that is U.S. based as opposed to overseas. So that's a major opportunity, and I just would encourage the community and the ecosystem to work together to find out how we can do this in a bigger and more aggressive manner. And, to be specific, there are major national initiatives. So figuring out where there might be relevance or carve-outs, whether for existing initiatives or new initiatives, be they in the private sector or in the government. Obviously there's been tremendous CHIPS funding. Many agencies are active in that. And as we transition over to the biotechnology segment, my colleague Rima has offered to flip the slides, which would be very helpful because as you see in the chat, there are some amazing people amongst them who kind of got us with some slides that we're iterating from last night. So Curtis, I don't know if you could even just start off presenting the slides that if Kat Jameson is on yet. Is Kat on yet, or will we fold her in a little bit later? Because I know she was ready to go right at 8. But let's make sure, so if somebody, Diane, if you could send that bio slide to Rima so that she can flip the slides, then I can help integrate some of the presenters into the other segments, but I can't do that while flipping slides.
Yeah, absolutely.
Rima,
We sent it.
Okay, great. So Rima, are you ready to start flipping those slides as we open up the bio section? And we're happy to continue emceeing, but it is helpful to be able to parallel process as we pull people into the conversation.
Yes, I'm pulling them up now. So
Thank you.
give me
And do we have Kat Jameson? Because I think we were thinking that it would be probably easiest to pull her in either at the beginning or at the end because we're integrating her into a deck. Or do we want to forward? Is Kat on yet? She might be coming in right at 8 a.m. PST, so which is 11. I'll just forward you her slides as well, Rima, so that you have them. Because you'll probably when she comes on at 8, we're gonna put her in because I know she had patients today that she's working around a patient schedule. So the patient is first when we do biotechnology.
So I'm pulling up the slide deck that I got from you earlier this morning. Does that make sense to start off with that? Or Diane, is there another version that's more comprehensive that I should be pulling up?
Yeah,
Sorry.
Go ahead, Anna.
I was going to say, I just sent Kat Jameson slides, but we can pull that down and present that when she gets on. So I think we can just go back and forth, Rima.
Okay.
So you can start with the slide that I sent on.
Hey, Anna, I don't see Kat in the list of panelists online unless she's under one of those Space Disruptor Day,
She might
anonymous
be
titles.
She might be joining at right on the hour at 11 because we're running a little early.
Yeah.
So I
I
think
see
we'll just
SachiBio and Rhodium on.
Yeah, so let's go to the first in that deck that Rima has. And then Curtis or Kevin, if you have the ability to just ping Kat, that'd be great. We're running early, so that's probably why. But there may be other presenters who are either on or not on. So do we know if we have the full list of our other bio presenters on?
I see Anushree from SachiBio and Olivia and Heath from Rhodium Scientific. And I don't think Ken Saban from Redwire presented in the other group, right? So he would still be available.
He'll be in this group.
I'm here.
So excellent. So let me just read through who we're expecting to have in this segment. So, and this was going to be the rough order, and we might fold Kat in a little bit later, but we were going to go with Kat Jameson, Radiant Space Systems. Is Radiant on the line?
Yes, I'm on the line.
And then
Okay.
Redwire is Red. Yes,
Ken
we have
is there. Mhm.
Redwire is here, and then National Stem Cell Foundation. So we might still be waiting for National Stem Cell Foundation. We've got Sachi Bio on. Do we have Lambda Vision on?
Nicole,
And then we've got, sorry, you say Nicole is on or she's not?
she was on.
Okay, so we'll probably get Nicole back, and then Exonus. Do we have Shane on? Or anybody from Exonus? And then Encapsulate. So it looks like we're still trying to get Cat, National Stem Cell Foundation.
National
And
Stem
then-
Cells, Paula was emailing, she was asking what time to start. I told her 11, I thought maybe 11:50.
Okay, that's great. No, that's perfect. So,
Running a little early, maybe tell her closer to 11.
okay, great.
I messaged
So-
all of those folks.
All right, so let's open up that deck, Rima, and I think
Do you see it?
is
I'm
Radiant first
sharing.
on that?
Do
Okay,
you see it? I'm sharing.
We can see
Okay,
it,
great.
Rima. Thank you.
Great.
All right.
oh, and I see that Kat's on as well. So do we want to just stick to, would it be easier to stick to the original order?
I think so. I would just
Yeah,
go
I
back
think let's
and
just stick
start
to the
from
original
top.
order. So I think
Yeah.
we'll do this we'll just take a moment and we will go into Kat's. I'll just open up Kat's presentation directly because that'll be easier.
Do I have it already open, I think?
It's
Do you have
it's
Kat's? Oh,
open.
you do, great.
Yeah, I can see
Excellent.
it
It's
being
open.
shared there, Anna. So thanks so much. I'm in clinic here, as you see, so I'm ready to go. Patients are lined up, so I really appreciate being able to go on time.
Thank you for making the time. We appreciate it. And the patients, as we were saying, are first.
All right. So I can go whenever you like.
Kat, I just want to say, I mean, obviously you've done so much as a researcher, as somebody who's providing care to patients, but then also as a very successful founder and businesswoman. So, really appreciate your work in all these areas of the space economy.
Well, I appreciate everything you've done to bring us together and your leadership, especially at the White House just on Monday. I think everybody
Great
was
seeing
moved
you.
by your talk. So congratulations on that. You showed that it is a thriving ecosystem and something we need to do more of, and microgravity has value. So I really appreciate being involved in this. I think there's a lot more to be done. What we've done on the International Space Station in 7 missions so far, with 3 upcoming missions, is look at stem cell aging, precancer and cancer stem cell generation through a blood lens, a hematopoietic stem cell lens. So I'm a hematologist. As we know, stem cells in the bone marrow actually reside in a niche or microenvironment that is their happy home. And what happens as we get older is we tend to mobilize those stem cells out of the bone marrow niche in response to stress or other macroenvironmental toxins. So think about how we're stressed. How do you model that? Well, it turns out the International Space Station is a great place to do this. We knew that from the NASA twin study with Scott Kelly coming back 2 inches taller than his identical twin brother after 340 days in space. But there's a big but. He had inversions and translocations in his chromosomes, which to me are pre-leukemic changes. As a hematologist, that's what I look for. But he also had telomere changes and also inflammatory growth factors that we know fuel base deaminases. So you've all heard about DNA and RNA editing as a good thing, but it's part of our natural defense system against exogenous viruses as well as endogenous retroviruses. And when they're activated too long, particularly DNA editing APOBEC and RNA editing ADAR, we go from precancer to cancer. So what we've seen on the International Space Station is accelerated stem cell aging and the activation of APOBEC when they come back. Wondering if you can advance to the next slide. I just can't seem to advance it. So what we decided to do is build a canary in a coal mine strategy. So my dad was a coal mining engineer, and he said, when you go into a coal mine, there's one thing you can't detect, you can't smell, it's carbon monoxide, but canaries actually die with very little exposure to carbon monoxide. So we wanted to see, can we build a similar system, of course, without the birds, to really understand cancer and aging stem cells in a nanobioreactor that we developed that has artificial regenerative intelligence enhanced systems, canaries. So we can put our stem cells from our bone marrow in these nanobioreactors and see if they age under conditions of stress terrestrially, but also on the International Space Station. So we have a fluorescent reporter of cell cycle. If our stem cells go from being happy and red dormant to green, that means that they're really getting stressed, and if they're yellow, they're dividing. So what we saw in this nanobioreactor that is in the Cube Lab developed by Space Tango is that stem cells accelerate their transition through the cell cycle. They activate splicing, and then when things go from bad to worse, they activate ADAR, that cancer cloning gene. So these are longevity devices that we've made. We can use them terrestrially. They have a lot of rewarding results that we've got that are now under review at a major journal. But the important part is we can make these for all of us. The next slide is the final slide. So what we thought is, if normal stem cells become pre-malignant in space, what happens to cancer if we send it up? So it turns out tumor organoids triple in size in just 10 days in space. We saw this in Axiom 1 and 2 missions. And then on Axiom 2 and 3, we decided to say, can we block cancer's capacity to clone itself? And indeed, we found a cancer kill switch with the Axiom 2 and 3 crews. This is because tumors triple in size in space in just 10 days. They reveal themselves as being dependent on ADAR1. Rebexinib is the world's first ADAR inhibitor. We founded a company called Aspera Biomedicines, Paraspera ad Astra, through hardship to the stars. Patients shouldn't have to go through hardship to get the therapies they need. We should do that first for them. So this got into Fortune magazine. We're accelerating the development thanks to NASA, thanks to INSPA Phase 2 funding. So we're the first in the US to get INSPA Phase 2 funding, and Igniting Innovation is helping us understand the cancer stem cell niche. So this will be the first drug to have its development path accelerated by space. So as you pointed out, Anna, there's a value to microgravity. This has been tremendously valuable, and the first time I've ever seen something so clear. So we're thrilled to be able to work with NASA, NSF, partners that are determined to use this unique environment to really help humanity on Earth.
Yeah, I mean, this is really amazing work, but just wanna, I mean, you bring such a powerful voice to this, and just to have that stop of saying, you know, you're highlighting what a tremendous opportunity this is, and that when we think about how many families, is it every family that is impacted by cancer? And so then when we move from saying, well, you know, there's just all this tremendous exploration going beyond Earth happening, to here are the real solutions in microgravity, in LEO, and beyond, that can transform cancer treatment and other treatments. So I know we're going to hear a lot of that from our other colleagues who are doing amazing work in this sector as well. But what you just said is big. And so if there's anything else that you want to just state with regards to how important microgravity is for cancer, I know you've covered quite a bit, but we definitely want to hear you out on that.
Yeah, I think because we had to work in such a difficult environment, we de-risked a lot of the experiments, not just from the nanobioreactor side, but we studied the Axiom 2 and 3 crew blood stem cells before, during, and after launch, and discovered changes, clonal mutations, but also the dark genome was unleashed. That also occurs under conditions of stress. So those retrotransposons can be inhibited. So that's a precancer signal that we can detect in response to stress, and we can detect it in all of us now at the single cell level because we worked in space. So the good news from space is that we can detect cancer before it's even cancer, at the pre-cancer stage, at least in blood. We can also test and look for accelerated aging and see if we can predict, prevent, and reverse. So I think there's a moral imperative here to work together to make sure we use microgravity to understand these facets of stress-induced aging, pre-cancer and cancer stem cell generation, so we can develop countermeasures. we have to do this. And I think you were so effective, Anna, at our White House Microgravity Summit in really showing us the path forward. We have to work with all of the agencies to make sure we take full advantage of this environment. And as I step in to a patient's room, you know, I wonder if, can you wait 30 seconds? Can I introduce you to somebody?
Yes, yeah, it would be
Yeah,
great
1
to
second.
meet. And Kat is really just so focused on really tying back to the needs of the patients. And, you know, when we were at the White House Summit on Monday, she did bring a patient with her very much to speak to the importance. So, you know, we certainly speak to the commercial side and the value. You know, on the biotech side, we're talking about markets that, you know, globally as a whole are trillion-plus markets, but there's also the ability to lower the cost of care and to improve health
Okay.
outcomes for people,
So if
improve
you
lives
sit
and save
here.
lives.
So Anna, I wanted to, if you can sit here, Vivian, you probably need to take your mask off just because. So here's my friend, Vivian.
Vivian, thank you
Hi.
so much for joining us.
We're talking about the drug rebexinib, the ADAR inhibitor that we've talked about, and how microgravity has accelerated the development of this drug. So we're trying to get to IND. Vivian is a transplant candidate, has a disease called myelofibrosis that scars the bone marrow and can blast off to acute myeloid leukemia. We're trying to stop that process. The people on the call are the smartest people in the country.
Oh, wow.
You work with rocket scientists to get things done. So can you explain just in a 30-second soundbite why it matters to get new solutions for these difficult malignancies like myelofibrosis?
Because it's just getting worse. It doesn't get any better. And I'd like to feel great again.
So Vivian is a tennis player, a pickleball player. Her family's waiting in the other room. They're extremely supportive. A grandma recently.
Yeah, 6 grandchildren. The youngest one is
Congratulations.
7.
So this is what you're doing, Anna and the team on the call. You're helping this whole family. This is why it matters. And as you mentioned, Anna, it's about all of us. None of us are going to escape cancer, whether it's personally or in our families. It affects 1 in 3 of us. Every single one of us is going to be personally affected. So we need to start now, maybe yesterday, in doing this. And we have professionals here like Vivian telling us when we're getting it right, but also when we're not, and how we really need to work in lockstep to eradicate the scourge of cancer and really get it back to a pre-cancer stage and hopefully even not cancer.
Yes.
And one of the things that we're trying to do, because there are these tremendous innovators, you know, on the call who are doing this early, started it yesterday, you know, as Kat has and others, you know, in this segment research. But we're also looking to, there are a large number of doctors, hospitals, biomedical engineers, biologists, you know, people working with data and AI in the health spheres that have not unlocked the capabilities of microgravity. So part of what we're doing here today is this is one part of a journey of bringing more of those leaders terrestrially in to work with the space capable leaders so that we can accelerate these solutions that you need and that we need. We all need these solutions. And I really appreciate your your generosity in speaking to how important this is.
Also, Vivian has given her blood and bone marrow so we can study the real disease rather than something we just kind of make up on the fly, pun
Yeah.
intended.
Yes.
So that's what we're flying with ISS National Labs cases. That's what we're looking to target with the oral formulation of rebexinib and the IV formulation. So we're trying to get into that clinical trial Q2 of next year.
Thank you so much. Well, much appreciated. Curtis, do you have anything you want to say before we
No,
move
I
to
was
the
just
next?
going to say a special thank you to Vivian for speaking to us and to Kat for bringing her in. Thank you, Kat, for your presentation. We're so appreciative of the work you guys are doing, and we see the impact with people like Vivian. So thank you for bringing her.
Thank you so much for this opportunity. We'll get back to
Yes.
work, right?
Yes, definitely.
Good to see you.
Get onward towards a cure.
There you go. All right. Thank
Right.
you.
Thank
you.
you.
Have a good day. Bye-bye.
Bye.
All right.
So there's that meaningful call to action that so many of you have heard from so many of the people whose lives are impacted by your various research. Rima, are you able to move to the next presentation? And this is Radiant, and very excited to have Radiant on today. Radiant, while building out more of the platform and places and infrastructure and capabilities to do the research, has done quite a bit of work with biotech. So it's both that intersection between the place and the infrastructure to do it, and also supporting some of those researchers. Lee?
Thanks, Anna. And wow, that's a hard act to follow. So, I'm Lee Wilson, the founder of Radiant Space Systems, and our goal is really to help enable in space research and in space manufacturing, and then eventually, further down the line, really boost the economic sustainability of human presence in space. And biomanufacturing is, really a key part of this. So one of the products we're developing is an orbital robotic platform designed for hosting biomanufacturing equipment or research equipment to help enable, this nascent industry. So how does this platform help turn the sort of science fiction sounding vision into a reality? Well, to start with, the plan is for us to be the innkeepers in space, the place for payloads to live while on orbit. This research is fantastic, but it needs somewhere to be performed. So payloads would be launched and dropped off in low Earth orbit by our partner companies. And then for the next leg of the payload's journey, it would catch a ride with an orbital transfer vehicle to where this 10-foot diameter platform would live. Now, the incoming vehicle would be berthed by these robotic arms that you see, and then the payloads are transferred to the habitat section. So once inside the habitat, I should say, there are bays on the exterior for hosting payloads in vacuum, but we also have an interior pressurized section, which is still unmanned. So once inside the habitat, the payloads would settle into their new home, and a robotic arm on the interior would be able to transfer payloads to whatever piece of permanent equipment is necessary for your process, ranging from bioprinters through to incubators, freezers, and so on. And then once your product has been created, it can then be packaged back into a capsule and delivered safely back to you via our return to Earth partner companies. Now, the key advantage with this type of approach is that because the habitat lives on orbit with the manufacturing equipment, up to 98% of up mass can be saved, since only the feedstock's going up and product returned. And this is coupled with the high throughput and lower costs that an unmanned system enables. So together, these really have the potential to greatly improve the commercial viability of biomanufacturing, or just bioresearch in general. And the idea is that we'd offer payloads, all the amenities they could want, like power, communications, or thermal control. And like any good innkeeper, we would welcome all payloads. For example, the slots on the exterior of the habitat can be used for other types of manufacturing, such as the semiconductor work you heard about just before. And eventually, the aim is to customize different habitats to each industry to their specifications. Next slide, please. Now, we've got funding from the NSF for a stabilization system designed for an artificial gravity centrifuge, initially for a much larger human habitat. But the great thing is this technology can be applied to much smaller systems like this robotic habitat, which means that one of the amenities we could offer payloads would be to access to an in-space 1G control for biological samples. And this is perfect for allowing researchers to isolate whether a given effect is because of microgravity or for some other reason. But this is only the first chapter, and I also want to share our vision for what comes later. So when in-space biomanufacturing is scaled up and generating significant revenue, it'll be obvious to everyone what the potential that this industry has. And this is the stage when humans in space actually become an economic necessity, because there'll be demand for researchers to stay in space and perform additional R&D on new in-space manufactured products. And even with reduced launch costs, the expense will mean that people will stay in orbit for 6 or more months. So what's needed is a lab where people can stay within an artificial gravity environment to maintain their health, but then travel within that same habitat to a microgravity area to conduct that research. And previously, this has been impossible, but with our disruptive approach to human habitats, we have a potential way to solve this. From the right, you can see a habitat designed to launch in the SpaceX Starship, 55 feet in diameter, and it would house a 12-meter diameter internal centrifuge that you can see on the left. And this is designed with the latest understanding and research of human reactions to the Coriolis effect, and where researchers could have access to a range of gravity levels. Next slide. So here you can see sort of some of the artist renditions of what we view life and living in this, working in this environment would be like. So, imagine that you'd be able to live and experience space without having to worry about bone loss or accelerated aging or any of these other challenges. So you could easily transition from the centrifuge to the microgravity areas where all of your biomanufacturing or research equipment is housed, allowing for rapid and disruptive innovation. So in summary, we see biomanufacturing and in-space manufacturing having a bright future on all of these upcoming platforms. And we can't wait to welcome you to LEO in the future. So we really want to help turn science fiction into a reality. I also want to say thanks to the organizers of today's events and to the NSF for helping support these goals.
Thanks so much, Lee. This is very exciting. And I'm just trying to help with some of the management in the background. And I saw, Rima, that Shane from Exonis, AXONIS, is traveling. So asked for the courtesy of us flipping to him. Would you mind doing a Control F Exonis? And then that'll get us directly to his first slide. Rima. I think if you hit Control F and then the company name Exonis, AXONIS, we'd be able to move to Shane, who it seems like is having some travel logistics issues. There we go. And then we'll get you back into the right place in the flow after this. Shane, are you ready?
Yes, I'm ready. Can you hear me on your side?
We can.
Hello?
Thank you.
Fantastic.
And I think, Rima, if you just hit that arrow like next to the spoke, you hit those. Yeah, there we go.
There's a little bit of a delay when I click on things. Sorry about that.
You're doing great. Thank you.
Thanks, Anna. Thanks, Rima. My name is Shane Hagerty. I'm the Chief Scientific Officer and co-founder of Exonis Therapeutics. And the lights in this foyer are on some auto dim system, so bear with me on that as well. We're a Boston-based CNS therapeutics company, developing first-in-class therapeutics for neurological disorders, and recently began our first clinical trial this month, actually, which we were very excited about. And this was also, in the recent months, enabled by our close of a Series A fundraise of $115 million to support these clinical programs, and that was led by Venn Bio and Cormorant. So it's very important to explain how the grant that we got from the ISSNL and Boeing through the Mass Challenge program really put Exonis on the map in terms of gaining traction very early on, when at the time, myself and my co-founder, Joanna Stanica, who's the CEO and president, we were pretty much still part of the lab, the academic lab from which we spun out these technologies. So this really gained traction with our first seed investors, and that was very important. And that was 4 years ago at this stage. But in recent years, we managed to complete our project on the ISSNL, and it really advanced one of our therapeutic programs, and for the first time showed what you can do in microgravity conditions, which is to rapidly self-assemble a mature model of the human brain, and that hadn't been done before. And we conceived this project because we wanted to advance a novel gene therapy for human disorders, and we wanted a human brain model to do this, and that was enabled by the Technology and Space Grant and our partners at the ISSNL and BioServe Space Technologies. And last year, we had our successful completion of that project, and it has really been fantastic to see the response from the community from this success. So we can move on to the next slide, please.
Did it work? Somehow the controls have The PowerPoint disappeared on my end. Can you guys still see it?
We can see it,
Yes,
but
we
it's
can.
not advancing.
Did I advance it?
No.
No. This is so bizarre.
For a purpose, I'm happy to speak to the project though, if that's if there's time limited for the whole group of speakers today.
Let me pull it up one more time. I'm just gonna start over. I
Appreciate
don't know
that.
what happened on my end. I can't see it anymore and couldn't tell where I was. Oh, there it is. Okay. All right. I found it. Let me get back. Okay. Am I
Thanks,
on the right
Rima.
slide?
So the next slide, please, if you don't mind. So as a company, and you'll see the initials of our Chief of Staff, Ayla Burlow, in the part of the Earth logo here. This was our Neuronics space mission supported by the ISSNL and BioServe. And what we had before the project was a vector that could target neurons and not astrocytes in the CNS. And that was very important for our neuroregeneration program. We wanted to restore a growth ability in the neurons, but not the astrocytes or any other part of the body. So to do that, we needed an AAV that could target the neurons directly. And we had shown that in mice, and that's what that image here depicts. But we hadn't shown it in human mature neurons or brain models, which is more important for translating into the clinic. And actually, the FDA has encouraged people to, where possible, use human models for developing their new therapeutics, particularly for the pharmacology package. So that's why we devised this project. When we were provided with this opportunity as Mass Challenge Startup Accelerator participants, we imagined what could we do in space that we can't do in the ground. And we wanted to push the boundaries of induced pluripotent stem cell derived brain models. Because on the ground, either they take many, many months to grow into a mature and 3D structure, and that can be limited in terms of the complexity of cell types that can be derived from this differentiation protocol, or alternatively, you can make it quite a mature cell type, but only really a single cell type of interest with directed reprogramming of iPSCs into neuronal subtypes. So then you get the maturity, but you use the complexity. And importantly, these cultures will only grow as monolayer 2D layers of cells on Matrigel. So what we had learned from studying some literature on liver cells is that in microgravity, these cells that also like to adhere to grow spontaneously assembled into a 3D structure. And we wanted to explore whether if we send mature human neurons and mature human astrocytes to the International Space Station, could the microgravity conditions rapidly enable assembly of these mature cell types into a human brain model? And what we devised was a 72-hour project to investigate this, which is obviously much quicker than the organoid protocols, which take many months on Earth. And it allows the opportunity to take many different cell types and assemble them together into a more disease-relevant model of the human brain. And in addition to this, we can send these cells cryopreserved to the space station rather than sending some of these pre-grown organoids up to space and they get affected by the launch process. So this was very interesting that we could send these cryopreserved cell types of interest and make the brain model on orbit in LEO. So if you proceed to the next slide, we can show you the outcome of that experiment where we wanted to test two things. We wanted to test, first of all, what I just mentioned. Can we make this mature assembloid model of the human brain, which we have here? We were able to visualize that on orbit because we used our AAV gene therapy that targets neurons only, human neurons. And by doing that, instead of delivering the therapeutic payload, we instead added a green fluorescent protein into this vector, so we could visualize the cells in real time on orbit. And you can see an image here of the astronaut using the BioCell technology from BioServe Space Technologies, and they were inoculating our cells and our viruses and other important things for the experiment. And in 72 hours, we have these brain assembloids coming together, and we can see that the gene therapy indeed was expressed in the neurons, which was very exciting for us. We both demonstrated that you can make these models on orbit, and we also showed for the first time that in human neurons, mature neurons, we can use our gene therapy effectively. So that was 2 very successful outcomes for a single experiment, and we're very excited about future applications of this technology, such as taking patient-derived iPSC neurons in astrocytes and making complex models on orbit and testing gene therapies like the one we designed for this project. So thank you all for your time. And again, thanks to ISSNL, Boeing, and Mass Challenge for enabling this project through the Technology in Space grant. And we're really, our minds were blown by what you can do in space in terms of pushing the boundary of science around precision neuroscience therapeutics.
Thanks so much, Shane. Much appreciated, and wishing you the best in your travels. Thanks for making the time. What I know is a really busy time of year for everybody, but certainly while traveling. And Rima, next we want to go up to, if you want to do a Control F for Redwire, that would get you back up to the next presentation. You just, yeah. All right, do we have Ken on? Yeah, I think you got it right there.
Hi, everyone. Hi. I'm Ken Saven. I'm the chief scientist at Redwire, and we have a number of projects on station now, a number of payloads, and we just returned 3 sets of experiments related to the project I'm going to describe today. It's PIL. It is we call it the Pharmaceutical in Space Laboratory, and it is a device that allows us to run several crystallizations of small, medium, and large molecule therapeutics or agrochemicals or cosmetic-related crystal products or food-related crystalline products. But it's a device for growing crystals. And what I've got here are 3 examples. Lysosome is a large molecule. It's a protein. It's a common protein to grow crystals of because it's pretty simple to grow. But when we grow them in space in this device, and the images that you see down the center line are images that were taken in orbit. Our box allows us to, has a microscope built into it so we can see what's happening in there. The crystals tend to be larger than what we get on the ground. The faces are perfect. They are mirror. As you can see on the far right, those were taken immediately upon return. The faces are perfectly clear, and the crystals tend to be fatter, so they're different. Now, there's 2 aspects of crystals that we have to pay attention to. One is the form, that is how the molecules or the atoms stack to form the crystal lattice for the crystalline structure. And then there's the habit. The habit is what it looks like when we see it on the macro scale. And on the macro scale, you can see that the crystals are fat by comparison. They are different. And both of those, the habit and the form, can lend themselves to improvements in the formulation of that product. So what we're looking at here would be the active pharmaceutical ingredient. That's the active molecule. But that then gets built up with other additives to be made into the form, or the formulation that is delivered to the patient. So we're thinking about both of those. And we're seeing that by growing crystals in space, they are different. Another good example is insulin, which has been done before. We did it again, this time with a little help from Eli Lilly and Company. They've been making and selling insulin commercially for over 100 years. And the crystals on the left in that smaller image are what we got on the ground. And in both these images, we just handed it over to Eli Lilly. They're the ones who took the images for us, opened the boxes and looked at them. The images on the right, you can see, are what we got in space, and they are very different. The same form, but the habit has changed. They're larger, and they're forming these large hexagonal or octagonal structures. There is a significant difference. And even though insulin is kind of a commodity product, there are opportunities if you were to, for example, come up with a form that did not need to be injected. There would be a significant benefit in adherence and financially, ultimately, in the market. On the right, far right, that is femoxidone. It is a small molecule. That is what we're really intending to go after with this effort. It turns out about 90% of all the small molecule products in the market, like Prozac and Viagra and Zyprexa and aspirin, they're about 90% of them are crystalline. And of those 90%, probably close to half are polyforms. They can form more than one type of crystal depending on the conditions. So we're targeting those examples and going in and seeing if we can make new crystals in space. Now, this last example here on the right isn't actually a pharmaceutical product. It is an agrochemical. It is spread on berry crops to prevent mold formation. It's an antifungal. Made by Corteva under the name Tanis. That's their brand name. You can see on the left in the black and white image, those are crystals that were grown on the ground. They tend to be fat little round crystals with little small little spikes heading in all directions. When we grow it in space, though, the habit has changed. They're now small, centered little cores with long tendrils going out in all directions. And again, that could have an impact on its ability to be formulated, in this case, to be spread as a powder on crops. Next slide. So what does it matter and what are we doing? In this last year, we have flown PIL 28 times with 17 different experiments being run. We're working on both small molecules like femoxidone that I showed there, carbamazepine and others, medium-sized compounds, those would be mid-range biologics like insulin, and then large proteins. We're starting to get into things like monoclonal antibodies and doing crystallizations of that. We're working with companies like Eli Lilly and Company, my alma mater, as well as Bristol Myers Squibb and XS Libero. Bristol Myers Squibb and XS Libero both flew on this last mission, and those samples being returned to our site at the Kennedy Space Center. By finding better or different crystals, we have an opportunity to improve the formulation of those products, the delivery of those products, and ultimately make a viable financial product, something that we can build a business off of. We are also looking at generating seed crystals. We don't need to make metric tons in space. All we need to do is make a thimbleful, bring it back, and expand that. And in fact, we have run studies this year to demonstrate that we're able to make forms in space that we could not make on the ground, and then use the seeds that we brought from space to make larger and larger batches. So those studies have been done, and we'll be publishing that work in the not too distant future. Next slide. The device is a modular device. The facility is on station currently. It's the ADSEP facility, and we build small cassettes that the experiments are running. Every cassette can run 4 experiments. It has a built-in microscope and video photo capability. We download those images and we can tell when the experiment is done or should continue. And ultimately, the seeds are different. That's what we're looking for. So different forms of different properties. And by making them in space, we see a huge advantage to making them on scale, but also just for seed production, essentially making sourdough starter in space, bringing it down, and then using that again and again. I'd like to thank you all for your kind attention. I'd like to thank the organizers for allowing us the time to speak. And if anybody would like to talk about this further, I'm sure you'll be able to get my contact information from the organizers or off the internet. Thank you.
Thank you so much, Ken. And Ken, we'd also reached out. We'd emailed Mike Gold on another segment later today. I don't know if you're on the email, but if he has an ability to stop in at any point in the day, definitely would love to hear on some of the areas he's given.
He saw it, and I saw some emails going around internally. I'll look into it and see if he's going to be able to
We'll work him in at any time. If he wants to come in at any time, we'll work him in verbally. And if not, we're very grateful for his work in really forwarding science, across all these fields. All right. So we want to keep racing through these because we've got some big segments, but Lynn, did you have anything that you wanted to say? I think Lynn Harper. We just need to keep it under a minute, Lynn. Okay, we might have a chance to pull her in.
So, I'm sorry, can you hear me? I'm in a location that's going to be a little acoustically live, so sorry about that. I think what I'd like to say is that as somebody who's followed this field for a number of years, we've
I'm
never
sorry, I have to interrupt, Lynn. You are not somebody who has followed this field for years. You are somebody who was best introduced to me when we first met as one of the founding mothers of in-space biology and astrobiology. So I apologize for interrupting, but yes.
Well, I am old. Thank you very much. I am old, but and I've been at this a long time, and I've never seen anything like what happened this year. It's not so much that any one of these has been successful in space in advancing the state of the art. It's that so many have, and they're relevant to diseases like breast cancer, ovarian cancer, colon cancer, Alzheimer's, ALS, Parkinson's, prefrontal dementia. It's been both the cancers as well as the neurodegenerative diseases. And then we saw the advances in the crystals all coming in the same year. And I think we're at a stage now where it's no longer ignorable. So thank you very much for the opportunity to comment, and apologies for the acoustic quality.
Great to see you, Lynn. Thank you so much. All right, National Stem Cell Foundation. Are you ready? You might be on mute. And then just afterwards, so everybody's tracking. So after National Stem Cell Foundation, we've got Saatchi Bio, then Lambda Vision, and then Encapsulate. All right, so if we don't have National Stem Cell Foundation, we might try to come back. Let's move on to the next presentation. We're gonna keep this running. We'll come back to them. So Rima, if you can forward to Saatchi Bio. You just go 3 slides down, I think, Rima. SACHI. Okay, Anushree, are you ready?
Yes, I am. I think you clicked our webpage, the QR code by mistake. So yeah. There you go. All right. Can you guys hear me? Okay.
We can, loud and clear.
Perfect.
Thank you.
All right. Well, good morning, everybody. Thanks for having us. We are Saatchi Bio. We discover and develop RNA therapeutics. I'm Anushree Chatterjee, co-founder and CEO of Saatchi Bio. At Saatchi Bio, we are developing a powerful RNA therapeutic modality called nanoligomers. Nanoligomers are molecules that can target disease-causing genes. What's shown in the schematic on the right is a simplified demonstration of how that works. So these molecules can target messenger RNAs expressed by these genes, and the result is that we can reduce or block expression of disease-causing proteins. Using this technology, our goal is to develop the best and first-in-class disease-modifying treatments for a range of neurodegenerative diseases. These include ALS, dementia, such as Alzheimer's disease, Parkinson's, multiple sclerosis, and glioblastoma. Next slide, please. So as a technology, Saatchi's nanoligomers are highly differentiated. So first and foremost, one of our biggest strengths is that these molecules can target genes on demand with high target affinity as well as specificity, comparable to those of antibodies. However, unlike antibodies, we can drug the undruggable. If you guys may know, 85% of the human proteome is not druggable. But this is not an issue for nanoligomers because we can target any gene of interest. The entire proteome opens up for us. So imagine what that means for drug discovery. Imagine a disease-causing gene network that has hundreds of genes, and now you can fearlessly target any of these genes to identify disease causality. This truly powers our ability to find better treatments for various diseases. The second major strength of nanoligomers is that we can deliver these to target organ of interest. Importantly, we can deliver this to the brain. As you may know, getting payload into the brain is no easy task in the field of medicine, let alone RNA therapy. Not only can we deliver to brain, we can deliver to the various brain sections as well, and using systemic administration, such as, a patient can take a pill with nanoligomers in it, or inhale them, or it can be injected or through IV. Third, and again, very important, do these molecules work? And the answer is convincing yes. We have tested the therapeutic efficacy of our lead molecules in a range of different models. These models vary from human organoid-based disease models, animal models of diseases including Alzheimer's, ALS, MS, and so on. We've also validated the safety and dosing regimen of these molecules in small and large animals. And I'm happy to share that we are advancing our lead molecules to the clinic the later part of next year. As a platform, Saatchi has demonstrated advanced manufacturing in two different ways. One is we can design and manufacture hundreds of molecules, hundreds of nanoligomers targeting hundreds of genes at scale. And secondly, we can also produce kilograms of a certain nanooligomer to advance to clinic. As a company, we are committed to validate our leads in patient populations. You see, your drugs can be very good in animal models, but they really need to translate well in human beings. As a result, we are highly invested in developing human disease organoids and validating our molecules in a large patient population to capture disease heterogeneity. Last but not the least, Saatchi has been lucky to be able to leverage microgravity as a platform in itself to be able to modify, accelerate, or decelerate, whichever way, disease pathology. Next slide, please. Next slide. Yeah. So this brings me to our vision with space. So Saatchi's goal is to develop effective and safe treatments for diseases on Earth. And space, to us, space offers this opportunity that will enable us to perform rapid and hopefully one day low-cost drug discovery. And the reason being, again, in space, we can, we have observed and other folks have observed in scientific literature, we can modify disease pathology. So for example, we can accelerate aging, accelerate neuropathology, which allows us to discover better and also, very importantly, validate the leads we have. So far, Saatchi has been able to participate in 2 space flights, SpaceX 29 and 31, wherein we have sent more than 650 donor-derived brain organoids to space. We have developed more than 1,000 here on Earth. We have screened hundreds of nanoligomers on Earth. We've screened 9 in space. These 9 target 5 different unmet diseases, including ALS, Alzheimer's, Parkinson's, PPM, primary progressive MS, and glioblastoma. And I'm excited to share we're advancing 2 leads, NI-112 and NI-113. These are molecules that target the inflammasome, specifically NF-kappa B and IL-6. Some of these are actually undruggable in the field. And we're advancing NI-112 to the clinic by the end of next year. And before I finish, I wanted to share one snapshot of why space and microgravity is important. In a paper we published earlier this year, and I provided a link here, you all are welcome to check it out. This particular paper focused on ALS and Alzheimer's. And I'm showing here one snapshot of data focusing on Alzheimer's disease. Herein we sent human brain organoids, donor-derived organoids, that are basically organoids replicating the prefrontal cortex area. And what you see in the figure on the left, if you just look at healthy organoids, you clearly see that disease biomarkers, in this example, phosphorylated tau, which many of you may know, is a very important diagnostic disease biomarker for Alzheimer's disease. We see that expression of this biomarker go up in space, and we've seen this across the board in other important biomarkers, which are provided in the paper itself. But exciting for us is that when we treat these disease organoids with our leads, we can reduce the expression of this biomarker back to the healthy levels, which helps us validate along with the other data we have and helps us move this forward with the FDA. So with that, I'd like to conclude that our vision with space is that the more and more we do this work, where we can screen more and more nanoligomers with greater number of patient populations and greater number of diseases, and with FDA's new Modernization Act, we believe that one day all of this will be hugely beneficial to move the needle forward and help us find better and more effective treatments for diseases on Earth. With
Thank you
that,
so
I'd like to
much.
thank you
This
all.
is very exciting, and we're getting tighter on time now, so I do want to move to actually, Rima, if you can pull down your slides. Heath from Rhodium is going to drive the slides from his computer, because I think we had one that wasn't in the. I feel like it's more dangerous for us to miss one that's not in the deck, so we'll come back to the presentation right afterwards, Rima. So Heath, are you able to present your slides?
I think so. I think
Okay,
maybe
great.
able to see them right now.
Okay, let's go.
All right. Thank you so much, Anna and Curtis and everybody associated with this to give us the opportunity to speak today about how Rhodium Scientific is really looking at ways and doing ways that are disrupting the overall space economy. From our standpoint, what we're looking at and what we want to talk about today over these next 5 minutes is really to understand how we can enable a lot of the amazing talks and amazing presentations that you're hearing today to actually get to space and do these amazing breakthroughs that everybody is talking about, actually enable them to do it. So at Rhodium Scientific, we are America's first true commercial space biotech company. We are a biotech company at heart. We were founded by Olivia Gomez-Holzhaus in 2014 as a terrestrial company that helped develop standard operating procedures, made laboratory practices more efficient. In the overall process, this was the business of science and looking at ways of not just doing a project, but putting together a product. And it was that drive that she initiated this company with that then carried over to the space industry. And in moving the company into the space industry around 2017, one of the first challenges that we received from the Department of Defense was, we appreciate going to space, we appreciate doing this work, but we need to do it with a high quality that terrestrial labs expect, but we also need to go quickly. We can't wait for 3 to 5 years to go to space. We must do it now. And so in that process, developed a quality industry compatible space process. And this allows us to monitor all the parameters of the mission, looking at ground controls to match up to the space flight conditions, doing everything possible to translate what happens at the benchtop to what happens in the space environment. And that process, and you see on the timeline below, has allowed us to repeatedly go to space within a year-long timeline, from development to the flight to the post-flight analytics, out to either the publications or patents within that 1-year process. And that is operating at the speed of business. And that is something that the industry was not seeing over the last several decades. Now, in doing this, we've been highly successful with a number of missions. We've been able to go in the last couple years over 25 different high quality, high throughput missions that you can see on the left side there, with representing over 17 different government agency missions, from DHHS to DARPA, NASA, Air Force OSR, DoD Space Test Program, NSF, and others. We have 3 missions currently on orbit, actually 1 now, 2 splashed down yesterday, and 7 missions planned for next year. So when we say that we're going and operating in space and we're enabling this amazing biotech ecosystem to get to space and do what you're seeing in a lot of these presentations, we're doing that. And we're doing that with a combination of that quality assurance, that rapid access, but also with, so we're scientists. My background's in molecular genetics. We have a full science team. We focus on the science first, but we do have developed a handful of hardware, but the hardware is designed for the high throughput. It's designed to look like what's in your lab currently. It's designed so that you can do the pre-flight optimization rapidly with the level of robustness, so that when you get to space, you're testing the space environment. You're not testing hardware. You're actually able to hold the spaceflight hardware in your lab and do the iterations necessary to optimize that science, so that when you get to space, again, you're testing that space environment. Now, some of the products that we've had over the last several years, one of those supported from the NSF is a space biobank. This is a way that we are getting these optimized samples available commercially so that other labs and other teams can go forward and test either on pre-optimized samples or spaceflight samples. You're ready to go straight to analytics post-flight phase. Talk to us. We have samples in reserve ready to go within the biobank. We also have multiple processes that have been vetted by DHHS through an OTA process that allows us to get regenerative medicine, stem cell technologies, biomanufacturing to space with those quality assurances with the timelines that your companies are expecting. And then with that, the biomanufacturing pipeline from DARPA, we've flown 4 missions in the last 2 years with DARPA to make sure that we can then test what is happening and in the biomanufacturing side and make that more efficient and going forward. So overall, then what is our path forward? How are we breaking models and going into the future? 2 sides on this with the biotech industry. You can see here, our main focuses are in biomanufacturing, regenerative medicine, pharmaceutical, drug discovery, drug development side, and the astrobotany. There's many different why space, why go to space in these areas. Partnering with us, working with us, teaming with us going forward, we can work with you on how to enhance your overall models with what you're doing in the terrestrial lab to add space. It shouldn't be or space, it should be and space. And that's what we're here to work with you on. The value to the space economy then becomes lowering those barriers to entry. We fly a lot of first-time flyers. We are breaking that barrier for these groups to do their first iterations in space and then set up that program where you test in space, you iterate, you build forward, and you go back and set up these programs. And in those, we're able to do the high throughput missions. We can do lunar gravity, Martian gravity, 0, 1G, looking at the full spectrum going forward because we know we are moving outward into the cosmos, but we're also back translating and must be able to develop those products to come back to Earth to disrupt the terrestrial markets, especially within the biotech sector. Contact information on the right, QR code gets straight to our email system to start a mission. Anna, everybody, thank you guys so much for this, and I look forward to any questions. Please email. Thank you very much. And actually, one more thing, Anna, real quick, and I do want to just call this out real fast. With the hardware that we developed, Olivia was awarded this past year the Johnson Space Center Director Innovation Award for the rhodium science chambers because they have also the high throughput side, but they're also configurable to fit a lot of science objectives and being able to do the numbers, the iterations, the overall quantity of samples at that quality level. And so she was here and awarded that by Vanessa Weiche here. So had to make sure I did that.
Really appreciate you bringing that up. And I remember that we brought the community together, well over 100 people virtually right before Christmas last year. And we were saying more shots on goal. How do we do it? And I remember you raising your hand, Heath, obviously your work with Olivia as founder, and you said, we're doing this already. And we, with your DARPA funded work. So we thought, it's a great example of just how so many of us can do, more to really try to onboard more participants, more builders in this ecosystem. All right, Let's go quickly, Rima. Let's jump to the next one. So if Rima can pull up the slides, I think we've now got Lambda Vision if Nicole's on, and then it's Encapsulate, which I think Lila is presenting for Encapsulate. And I'm going to go off because I'm going to get something ready for the next one.
All right. Well, thank you very much for having me here today. I'm Nicole Wagner. I'm the president and CEO of Lambda Vision. And Lambda Vision is a University of Connecticut spin-off company that is developing a protein-based artificial retina to help patients that are blinded by end-stage retinal degenerative diseases. So we will be targeting the orphan disease of retinitis pigmentosa first, and then follow on to that large market of macular degeneration, which is the leading cause of blindness in people that are 55 and older. Next slide, please. So the big question I often get as a vision company is why microgravity and why are we doing work in space? So the way that we manufacture our artificial retina is through a process called electrostatic layer by layer deposition. And so that's really just a bunch of fancy words that mean we have a protein that will bind to a scaffold through electrostatic interactions. And so you'll actually see an image of our dipping apparatus in the middle. And what we do is we take our scaffold and we float that scaffold on top of those beakers. So we go from beaker A to B to C to D, and we do that 200 times. And so this process is very much subject to the effects of gravity. So things like sedimentation, convection, surface tension, all will play a role in how that protein gets deposited to the scaffold. So in cases where you have, let's say, 10 to 20 layers, maybe not such a big deal, but we're doing this 200 times. So what this means is that any imperfection at layer 50 or 100 gets compounded by the time we get to layer 200. And so what this ultimately means for us in our thin films is that we have inefficient irregular protein deposition, and that will lead to less usable area for our preclinical and clinical trials, as well as the artificial retina performance, a decrease in performance. In a microgravity environment, you can see we get a much more ordered array. You'll see on the left-hand side, there's the molecules all over Earth, and then on the right-hand side, you have that structured orientation, which is what we expect. Next slide, please. So through our partnership with NASA and ISS National Labs, we have actually flown 9 missions to the International Space Station since 2018. It was actually our first flight, and you can see those missions listed below. We did this in collaboration with Space Tango as our implementation partner. And what you'll see here in some of these images is actually on-orbit images from our SpaceX 26 flight, where you'll see 200 layers of protein deposited onto our scaffold. And so through those 9 missions to the International Space Station, we have been able to demonstrate that we can manufacture these artificial retinas in a microgravity environment with good automation. We do have a lot of quality control metrics, imaging capabilities as well, that allow us to really look at what's going on inside of our cube labs. As we look forward, what our goals are is to really continue to manufacture on the space station and use this really ISS National Labs as a test platform as we start to transition from a public to these private space stations in capsules. And what's really cool and what we're doing here is that everything that we're doing in space is really enabling other opportunities for people to do research in space as well. So anything that could be using layer by layer or anything that is using protein deposition can also be done in space. Next slide, please. And so this is my last slide here. As I mentioned, everything that we're doing has much broader impacts. And so many of these applications that you'll see on the left-hand side leverage the protein that we use, bacteriorhodopsin, in various different device architectures. And so these opportunities here on the left-hand side that you'll see, the artificial retina, optical data storage, chemical toxin detection, these have been previously funded through, DoD, DARPA, the Defense Threat Reduction Agency. And so these all can leverage deposition of our protein onto various scaffolds. And then looking beyond the protein that we use, bacteriorhodopsin, this can be used for anything layer by layer. We're using biosensors, wound healing, anti-biofouling type applications, and then certainly anything that is going to require good manufacturing practices or GMP. So that's really any product that could be used in a person clinically. And so we are one of the first groups to really start to think about how we can do this in a microgravity environment. And so, of course, this will translate to other products that are under development as well. So thank you very much for your time. And I will drop my email in the chat if there's anybody who has any questions, and happy to follow up. Thank you very much.
Thank you. Excuse me. Thank you, Nicole. As we know, this is pretty incredible technology with the potential for impact. So we appreciate Lambda Vision and what you guys have been doing, and look forward to your animal trials and more successful microgravity demonstrations. Thank you.
Thank you, Curtis.
All right, Anna, are we converted? We're moving over to.
We've got encapsulate is we want to do a brief one with encapsulate, or do we already into the national? But yeah, we can move over to the to the EED side of things. Is
Well, we
Encapsulate
can
on?
also do national
Yeah,
stem
is
cell.
Encapsulate on?
Oh yeah,
Anna,
I'm here. Yeah.
Yeah, so let's go to Ayla, and then let's go to National Stem Cell
yeah,
Foundation.
okay. All right, good.
And we'll just need to go quickly.
Okay, I'll try to go quick.
Is this encapsulate? No, Excellus.
Yeah, the next one.
This one?
Yes. Okay, thank you. Hello, everyone. My name is Leila Danishmandi. I'm the co-founder and COO of Encapsulate. It's a medtech company in precision diagnostics for personalized cancer therapy. What we do is we have automated biochip systems that can grow cancer patient cells outside the body to determine the most effective chemotherapy treatment regimens for patients. What happens currently in clinic today is based on a trial and error method where the oncologist will choose a chemotherapy drug based on the type of cancer and what's worked well with previous patients that had that type of cancer. But this doesn't necessarily translate into good clinical outcomes. Most cycles of chemotherapy fail in the first time. And so what we do is we have a device where we can take a cancer patient's cells from the initial biopsy when they're first diagnosed with cancer. We take the piece of the biopsy, we grow it as microtumors in our biochip system, and we test all the possible chemotherapy drugs that the oncologist may want to try and tell them the most effective treatment regimen initially on a personalized basis. We give a report back to the oncologist as a consultation report. And so what really sets us apart, you could go to the next slide, please. What really sets us apart is the ability to run functional testing on microtumors from the patient themselves. So we're not really doing predictions based on databases or algorithms. We're taking a piece of the patient's biopsy tissue, the tumor, and testing them against any type of chemotherapy drug. We've done a couple of things that have really aligned our platform for clinical implementation and mass scaling. Apart from optimizing everything, such as the tumoroid environment, the hydrogels, the bioreactor, the microfluidics behind it, this is a layer by layer fabrication model that allows samples to be prepared in 10 minutes and tumoroid testing to be done after 2 hours. We can see results in 5 days and give reports back to the oncologist within that time frame. And so the space where the microtumors are grown is consistent in size and shape. We can grow 200 microtumors from a piece of a needle biopsy from patients. And this has helped with the automation of the system and the space studies, which I'll get to in a moment. We've also further clinically validated the technology with 60 cancer patients across colorectal and pancreatic. And we've shown that with these retrospective studies, these were patients from 5 to 10 years ago that had already undergone treatment with multiple rounds of chemotherapy. We were blind with the studies. We didn't know what had happened. But when we grew those patient samples in our biochips, and we tested all the different drugs that the oncologist would have wanted to try against the NCCN guidelines, we saw exact correlation with what we saw in our biochips and what had happened in the patients. And yes, unfortunately, there were patients that had responded to drugs in our system, but that hadn't been prescribed those drugs clinically and that they had unfortunately passed away. And so in the next slide, on the space studies, in March of this year, we launched the patient samples in our technology aboard SpaceX CRS-29 and 30 with 2 missions to the International Space Station. Could you please go to the next slide?
Do you see the changes?
I don't. It's still on the second one.
Oh.
It's not in full presenter mode. That may be why. Okay, yeah, perfect. I see it now. Thank you. The purpose of this mission was to investigate the impact of microgravity on cancer and also to build an automation system where we could remotely control all aspects of the experiment. So we did this with our implementation partner, Space Tango. And aside from it being an incredible moment, we saw that microgravity does alter how patients respond to chemotherapy. There was an exciting side note observation that we saw that microgravity helps us identify minor cellular motility and movements. And so this correlates with the metastatic potential of those cancers from those patients. So we can see a correlation with how cancer cells behave in space in terms of their metastasis and how those patients had metastasis on ground. And so we're developing new generations of biochips, hopefully more experiments in the future that will allow us to identify not only the most effective treatment treatments for patients, but also long-term consequences such as metastasis and resistance that can be predicted in advance. Thank you for the opportunity to speak here today. I know we're short on time, but I'll also put my email in the chat in case anyone has any questions. Thank you.
Thank you so much, Lila. Much appreciated. And I think we are going to roll over to the EED section. And I'm just getting somebody.
National Science Foundation.
You know, let's go into them. If they are they here? We missed them
Paula?
previously.
Yes, I'm here.
Great. Let's go back into that then first.
You see your slides?
I do see my slides. I don't see myself, but I see my slides now. I'm Paula Grisanti. I'm CEO of the National Stem Cell Foundation, a 501c3 nonprofit foundation headquartered in Louisville, Kentucky. Since 2019, we've been funding a study of neurodegeneration on the International Space Station using human brain organoids derived from the induced pluripotent stem cells of people with Parkinson's disease and primary progressive MS. We've flown to station 5 times with BioServe spaceflight provider costs covered by a grant from CASIS and the ISSNL for our last flight on SpaceX 30 and a recent NASA INSPA award that will cover additional ground research and another 3 flights through 2027. Over the 5 flights, this team has developed reproducible, well-characterized human organoid models of the parts of the brain specifically affected by these diseases that include specific types of neurons and microglia. These models can be used to advance biomarker discovery for improved diagnosis, provide insight on the effects of aging and neuroinflammation on the brain, accelerate drug discovery and development of neural organoids for preclinical toxicity testing, and identifying novel therapeutic targets for patients on Earth in addition to potential countermeasures for the effects of long-duration space travel on the brain. Upcoming flights will include organoids derived from the iPSCs of people with Alzheimer's disease, differentiated into the cells of the brain, especially impacted by Alzheimer's. The WHO estimates that over 65 million people worldwide suffer from neurodegenerative diseases, including various forms of dementia, with Alzheimer's being the most common, Parkinson's disease, and multiple sclerosis. According to a report from Alzheimer's Disease International, the number of people living with dementia alone is expected to double every 20 years, reaching 78 million in 2030 and 139 million in 2050. The cost of care for AD, PD, and MS in the United States is expected to reach well over $2 trillion over the next 2 decades and increase steadily as the population ages, underscoring the critical need for technologies that enable effective R&D to model, prevent, and treat these diseases. Our product is IP-protected technology for licensing to potential customers that include pharmaceutical companies, universities, and other academic institutions, biotechnology and contract manufacturing companies, disease-specific foundations, and government agencies. The market is worldwide. Commercial licensing opportunities will be evaluated more fully as we continue to study the system. But potential opportunities include licensing the technology to a single entity, licensing the model for specific indications, and licensing to individual customers and contract manufacturers as requested. Thank you very much. If you have questions, I will post my contact information.
We merged this deck at 3 a.m. last night because we were getting a lot of late-breaking content, so apologies that it looks like we might not have had everything in here. So BioServe, I think you've got your slides ready to pull up.
I sure
I think
do.
that's going to be it for the BIOS segment. All right, go right ahead, please.
Here we go. Yeah, hello. Thanks so much. You should be able to see and hear me.
We do. Thank you.
Great. Yeah, so this is BioServe Space Technologies. My name is Tobias Niederwieser. We are a center here within the University of Colorado in Boulder, and we are an implementation partner. So a couple of studies you have seen before is studies that we enabled on the space station. And so over the last 100 mission, we actually have our 100th mission coming up here with Crew 10 early next year. We really have built out a lot of the facilities that we currently have on the space station and can really use that as a lab. So you see things here like incubators, biocells, centrifuges, syringe pumps, but also the tools that directly touch the biology, like a petri dish version for space that is fully contained, or a test tube version for space. And we have literally conducted hundreds of experiments using those devices. And it's not just the devices, it's really also the procedures that we have spearheaded in the past. So things relating to cell culture, especially like seeding cells in space from a frozen vial into a cell culture. So it's only growing in space and not also on the ground. We can do things like media exchanges, in situ analysis with microscopes, including fluorescence microscopes, things like control rate freezing, or continuous perfusion that we had to develop to do organ on a chip models that we grew in space using kidney cell experiments that we flew twice successfully. And so all of these experiments, I want to pick one out where lots of these capabilities that we have developed over the years is important. And that is one that we are actually leading ourselves, not with outside researchers directly, but leading ourselves is in the domain of in-space manufacturing. And we are trying to produce induced pluripotent stem cells in space. And so on Earth, usually induced pluripotent stem cells are grown like in the left picture here, which is attached. So you're looking at the bottom of a petri dish here in a microscope, and they form these colonies on the bottom of the petri dish. And so that works great, except that in order to get enough cells for doing a therapy for a patient on Earth, you need a surface area that's bigger than a room. And so a lot of people have tried to put this in a 3D cell culture, and that looks like here on the right. Also works great on Earth, except the problem here is that a lot of these cells lose their stemness when you grow them in these 3D spheroids that you see here. And people have gone to great lengths to develop reactors on Earth to allow to keep those cells in suspension and not settle down to the ground. You see a couple here, like the vertical wheel bioreactor, a rocking motion bioreactor. So all of them keep them in suspension by some kind of mechanical force to keep them suspended. The benefit of space that we see here is that with microgravity, you don't need that mechanical force. You can just put the reactor up in space and they stay in suspension. And there's no shear forces, and hence the idea is that they keep their stemness while expanding those stem cells. And of course, stem cells are then good for a lot of therapies. You can literally make any cell in the body out of the stem cell. So the application of these stem cells is really endless. And we have, for this specific project, we have our first experiment coming up here in April 2025 on the SpaceX 32 mission. And so we are doing this work with funding from the NASA INSPA office with Kevin Engelbert, but also from the ISS National Lab from Davide Morata. And the idea really is here to send a few iPSCs up to the space station and expand them as much as possible in space. We are looking at a 100-fold expansion in space, and then bring that product back down to then use it for all the cell therapies that are currently in development and even in clinical studies and in FDA approval processes here on the ground, because there will be a big demand for all these iPSC cells for those therapies. And we have collected this team that is headed by BioServe It is also supported by Sierra Space to kind of look at the aspect of how to make those manufacturing processes in space FDA compliant and CGMP compliant. But then we're also working together with Elevate Bio, which is a biotech company that is actually developing and doing these clinical studies for cell and gene therapies. So really, we have this team together with expertise from the space station side, from the implementation side, but then also the biotech side. So if you have any questions on this project or as BioServe as an implementation partner in general, my contact information is there. And thanks very much for having me as a presenter here.
Thank you so much. And what an extraordinary group of presenters today. And the biotech was I believe, probably the largest section today. So we are running behind by about 15 minutes. I do not plan to cut that from the other segment. So we probably will stay behind 15 minutes, although if we catch up, that's great. Rima, is this the one that has Soul in it as well as SoCal, the one I just sent about 5 minutes ago? 5-10 minutes ago, Rima?
Yes.
You're on mute. Excellent. So just, do you mind pulling down the slides for a minute? Because I'm just going to give a verbal introduction. It's great to see you're here as well, Jonathan. So Jonathan, you're towards the end, as is Mark, some of the presentations that we just got in. So in terms of the ongoing discussion of anomalous phenomena and really advanced physics, quantum, just to kind of frame the discussion, many of you have been in the discussion with us for quite some time. Others you might be joining now. First, just want to say the conversations that we have are on the materials that are public, open, shareable. Just like everything else today, there's nothing that's classified. There's no CUI. So these are things that are in the public domain. So in terms of where we got interested or engaged in this type of forum with innovators, researchers on anomalous phenomena and UAPs. So we say anomalous phenomena, it can be a wide range of things. It used to previously be called UFOs, unidentified flying objects. They changed that to unidentified aerial phenomena because it's not flight characteristics. And then it got changed to anomalous phenomena because some of it is transmedium. It goes into the water. And to be frank, there's a wide range of other adjacent phenomena with regards to communications, with regards to energetic type phenomena such as orbs. So there are reasons that when we talk about anomalous phenomena more broadly, it both includes things that traditionally were UFOs. It also includes other things that are adjacent. So what we would say is there's a big shift for those who haven't been active in the space recently. It used to be that these technologies were not as discussed. There have been significant changes with regards to some of the recent declassifications and disclosures that have taken place, government, private sector information. But the reason that we pay attention to this, besides the fact that many of us have seen such ultra advanced technologies, as I have in my personal, and many of us see things in our personal and our professional capacity, what we find is that we're talking about well-documented cases of, regardless of the origin, be it terrestrial or extraterrestrial. So even without getting into the origin of it, when we see higher performing craft, we were expecting to have one of our colleagues in the innovation ecosystem, Ryan Graves, join this morning, who is one of the F-18 fighter pilots who gave congressional testimony on this space. We spoke to him about it, and we're saying, because we'll talk about the range of early stage and more developed technologies, but these are not TRL 1, 2, 3, 4. When people are recording them on radar, and other data acquiring systems, as we'll hear from some of the presenters today, this is what we called with Ryan operational. So there are operational technologies that, regardless of origin, are doing things like, as Ryan has shared many times, they are staying stationary in 100 knot winds. We hear other accounts that are 80,000 feet to surface. within seconds, and then transmedium travel into water without impact. There's a wide range of things that we pay attention to because there is no luxury when you are aiming to develop the most advanced propulsion and the most advanced communications. We just need to pay attention to anything that could be disruptive. So that's kind of, so as innovators, there's many free and open discussions. I know that NASA has put out some great materials on this. We also appreciated the congressional testimonies, including Mike Gold, who I don't know if he's going to be able to join us today, who spoke to the importance of the openness of science. Certainly, the NASA Administrator Nelson has spoken to the importance of inquiry and science in this field. And, as scientists, and as entrepreneurs, we really look to both what is known and acknowledged to be possible, and then what it is possible to build. We hear, publicly things like, we see that bipartisan leadership across Congress. We've heard some statements to expect more potentially from President Trump and the incoming administration and what has been publicly stated in some of his comments on that. So for those that are really seeking to advance the science and the technology that is possible, and obviously there's some parts that might be shareable and others in any field of technology that might be, closed for proprietary or other security reasons, there are many people that are eager and willing to help with that process. I've worked in deep technology for many years and funded hundreds of companies at the early stage. And I will say I have never seen such high levels of engagement in any field of technical interest as we have in the UAP and anomalous phenomena space. So tremendous, amazing capabilities across all fields of science, where experts are very eager to engage, learn more, and in many cases contribute their own experiences. People still don't always openly discuss what they've seen and what they've experienced, but we found that when we have an open conversation, in some cases, it's more in that 30 to 50% of innovators have actually experienced, some type of anomalous phenomena, advanced physics, quantum type phenomena. So with that, I know it's possible that Lou Elizondo is going to call in at some point over the course of the day. I think he had something come up, but I know we have Dylan on the line, and Dylan had very graciously offered to speak to a little bit of the context. Because there's the portions of this that there's been a lot of information on real technologies that have been released, videos that the DoD has shared publicly, with regards to the Tic Tac, the gimbal, and other type releases of very interesting technical information. Dylan, can we get you off of, and can we pull down the BioServe slide? Tobias, can we pull down that slide, please? Diane, are you able to pull down Tobias's slide? Great, okay. All right, so is Dylan on to make some comments, or we can potentially pull him in a little bit later? I think it's
How are you?
Dylan's on. Great to see you.
Everybody.
Thanks for offering to
I'm
share
not
your
sure
perspective.
if anyone can see my video or whether that capacity exists, but if not, I'll just leave it to your imagination as to, oh, here we go, what I look like, but now.
It's just a momentary drop while Dylan rejoins as a panelist.
Okay.
Hi, everyone. I'm back. Thank you for that. And thank you, Anna, for organizing this event. It's incredibly important. The UAP topic itself is enormously consequential for science, as I think you eloquently discussed in your remarks a few moments ago. And my background on this topic comes more from a legislative and legal one. I'm a corporate attorney in Washington, D.C. I advise both early stage technology companies as well as later stage companies on a broad range of corporate transactional and national security matters. I previously was an advisor on the Senate Foreign Relations Committee on a host of mostly European, but also national security related issues, and also was an advisor to then Senator John Kerry on the same basket of issues. So my background is not a scientific one, but a legal one. I think that perspective, though, is important given the work that Congress has done, often very quietly, on this topic. It is also, the Congress has been also quite outspoken in some ways on this topic. As Anna pointed out, Congress, for the first time in 50 years, has begun conducting oversight hearings on this matter. Somewhat more quietly, Congress has been legislating on this matter. Most people don't know, but Congress has been passing laws for the last 3 years and will be again this year in the form of the National Defense Authorization Act, which is the defense omnibus bill that must pass every year. And many people are surprised at that Congress is passing binding laws on the UAP topic and has been for the last 3 years and will be so again. And I would just like to talk briefly about what those laws are and what that might mean to all of you, both directly and indirectly, and somewhat specifically, but also more generally, that we may be seeing a sea change, at least in the legislature, and as Anna pointed out again, by the incoming administration, which might be historically poised to become the most transparent with respect to the UAP matter in history. How that remains to be, how that will play out, though, remains to be seen. But as far as the legislation is concerned, the first and perhaps the most critical feature of the legislation that Congress has been passing is definitional. Anna pointed out the various name changes, first from unidentified flying objects, then to unidentified aerial phenomena, and then lastly to the current statutory definition of unidentified anomalous phenomena. And these changes all represent important specifications by Congress to focus the executive branch on what Congress deems to be important. And Congress is obviously concerned not about prosaic phenomena, but anomalous phenomena. And what the characteristics of these anomalous phenomena are is somewhat debatable. But within Congress, Senator Schumer, for instance, has passed, at least through the Senate, legislation that would define what these anomalous characteristics are by a set of features known as the 5 and now 6 observables. And without getting over my skis into scientific territory, those observables are first, so-called anti-gravity or positive lift, what is known as the generation of lift, including to loiter for extended durations despite the absence of control surfaces like wings or ailerons. Or the generation.
Add to that can be over 24 hours from what our pilot colleagues have shared.
Yeah, I mean, this is like not even close to what known conventional capabilities are. And so that first observable already puts this anomalous set of objects in a league of their own. The second one of those observables is instantaneous acceleration. So this is exactly that. There is no 0 to 60 in 6.2 seconds like a Porsche. It's exactly that. It's instantaneous or near instantaneous. And then the speeds that are attained are easily hypersonic. There have been multiple sensor platforms, including by the US military and the intelligence community, observing UAP dropping from 80,000 feet to sea level in less than a second. And the only reason why that cabin of 80,000 feet is the one observed is simply because the sensor platform doing the observation was capped at 80,000 feet. We don't know if this particular UAP came in from an even higher altitude or from low Earth orbit for that matter. And then another one of these 6 observables is called transmedium travel. It is this ability for these truly anomalous objects to transition without any apparent substantive loss of these previously described performance characteristics. So UAP are also submersible. They can move through water, potentially space, without any apparent loss to these capabilities. A plane cannot do that. A plane can land on water, but it loses its velocity that it can obtain in the air. That's not so with UAP. The fifth observable is what is called low observability, something of a contradiction there, but we're referring to either active or passive low observable effects through cloaking or jamming. These UAP appear to interfere with some of these sensor systems. And then the sixth observable, the one that folks have not talked about so much because it raises some sensitive and frankly concerning issues, is what is called biological effects on close observers, people who near these craft or objects, whether those objects are stationed on the ground temporarily. There seem to be both a variety of cognitive and biological anomalous effects on the individuals themselves. And leading scientists such as Gary Nolan at Stanford Medical have talked about those issues. So Congress is trying to
Dylan, also Gary had some slides ready for today, so he was supposed to step in, but I think something came up, but we'll accommodate his schedule, if he joins us.
Okay, sounds good.
The way to pull him in.
And so Congress is focusing on these definitional matters so that the drones or other prosaic objects, things that are either temporarily attributed to being unidentified but later resolved, that's not what Congress is interested in. Sometimes there appears to be something of a shell game, either intentionally or unintentionally, frankly, by the executive branch. To say, oh,
Dylan, this is all very, very interesting. We're at 12:30, so I know we were running 15 minutes behind, and we're running more behind. It's just kind of like 30 seconds before we dive into our next presenters. Very grateful.
I'll wrap up here, Anna. Aside from definitional matters, Congress has created an office in the Defense Department called the All Domain Anomaly Resolution Office to resolve these anomalies as defined. The success of that office has frankly been mixed. Another avenue of legislation by Congress is to create at the National Archives a document repository to host declassified records within the various components of the government to publicize in some form what various agencies may know about these phenomena historically. And then another aspect would be Congress creating various mechanisms for persons either within the government or at a contractor, for instance, to come forward and either tell an agency inspector general or that new Pentagon office, AARO, or Congress itself directly about any activities that the U.S. government or these contractors may have been conducting with respect to UAP. And frankly, these involve allegations.
That's super helpful. And I guess I would just say before we move it, we do have somebody who's actually, the next presenter has previously served as a leader at in SkunkWorks at Lockheed Martin. And I would just say that one of the things that's been interesting for me to see is that it's hard to disintermediate the science side of this. So it's not a clear carve out of, oh, it's UAP, and then that's the UAP box. It's that you get into some of these areas of quantum or energy, advanced materials and propulsion, and you start to see that we're really just talking about advancing the state of a wide range of convergent technical fields. So it's interesting how there's some overlap in what the observational side of the UAP, or potentially the material side. I know Gary had some things to share on the material side because he's worked with some materials of provenance that are expected to be extra off-planet origin. So moving in, thank you so much, Dylan. Moving into Charles. Charles, are you ready to present? Charles Chase, you might be on mute, Charles.
Charles was in the attendees list. I've just promoted him to panelist.
Oh, sorry about that. Okay, good. And Zach, I'll put into the chat the list of the remaining folks so that you can pull them in for this segment as Charles presents. Hi, Charles. Great to see you.
Hi. Yeah, I guess I was on the wrong, I wasn't a panelist, so yeah.
That's okay. We were just teeing up the UAP topic, and then, we had, and then we talked about how, there's the advanced propulsion, and we referenced your work at Lockheed Martin SkunkWorks without going into any details.
Sure. Yeah, well, thank you for the opportunity to present some of my work. Let's see, I'm the founder of a company called Unlab, and we're developing a new type of propulsion that directs the flow of quantum fluctuations in a particular direction. And we do that by using nanostructures and diodes to make the quantum fluctuations propagate in a preferential direction to generate a force for propulsion. And if you can make something move, you can make a generator as well. And just, a little background, I had a long career at the Lockheed Martin Skunk Works, as Anna had mentioned, where I ran the Revolutionary Technology Programs Group. So we were all about developing really radical, disruptive breakthroughs that change the game. Think of moonshots, maybe even more so than like Google X always tried to do or is still trying to do. Things that can fundamentally change the game for Lockheed, it was for our defense, for our country, to help keep us safe, and I'd like to do that work now for helping, the entire planet, the biome, all people. And so, we coming from the aerospace industry and the space industry, we always wanted to make things fly like UFOs, or people said they saw UFOs fly like if that can be done, well, shoot, we can do that too. So, I've been after this kind of technology for a long time, both from my time at the Skunk Works and then after. And this is the approach that I think can really work. We've done the theoretical work based on just standard electromagnetics and quantum theory that show by generating an asymmetry in structure and in potentials, you can move these ever-present vacuum fluctuations that are around us all the time. They're required by quantum field theory to be there. We can move them in a preferential direction, generating a force. And I know this chart has been up for a little while, but let me just go over some of the breakthrough potential. This 9 newtons per kilogram, that's almost escape velocity for getting off the planet. And this little piece here, this 500 micron to 500 micron, this is an initial nanostructure that we've been making and measuring what's going on there. This would generate 3 millinewtons of force, which is plenty for a spacecraft reaction control thruster. So imagine a little chip-like device like that, providing directional control for spacecraft. And then as you scale it up and put it over, more surface area, being able to take off from the Earth. And then since it's propellantless and it's continually into moving these fluctuations, without any sort of dampener, you can get to light speed, of course, limited by the materials of whatever the thing is moving, and then eventually by vacuum friction. So we've calculated it would take 1.4 years to reach almost speed of light. And then, as I mentioned, a rotational device creates an electric generator. So, almost too good to be true, but, there's always, breakthroughs happen. And I think this really could be one. If you go to the next slide, please. Oh, and I just, we are seeking seed investment, and our first product is a spacecraft reaction control thruster. And just very quickly, here's a map of different sort of propulsion systems. This is adapted from a NASA report. And what we're plotting here is specific impulse, or the efficiency, how long thrust will be generated for a given propellant versus takeoff thrust to weight ratio. And you can see chemicals down here, lots of thrust to weight, but not very efficient. They don't run very long, whereas like a solar sail, not much force, but has infinite specific impulse. And so we're up here with very high thrust and almost infinite ISP as well. So this really changes the game for spacecraft and when we make that work. And here's just some more details of actual comparison to state of the art of some of these key factors, even as far as thrust density, like, how much thrust you get to over a certain area, we order of magnitude better than an electric thruster, like a Hall thruster. Next slide, please. So, I just wanted to take a step back and talk a little bit about the larger picture. And, in my work and when I look at things, there are so many fundamental questions that are remaining in physics. Things like, what is dark energy? The cosmological constant problem, et cetera. There's all sorts of observational data that we don't understand. So we don't know all of physics. And then there's also all the phenomena that people observe and experience, like Anna was talking about. There are other things as well that people experience that are just, we don't really understand. And to me, that means that there's a lot of hay to be made. And even if we look at some of the fundamental physics basis, things like energy conservation, energy conservation is sacrosanct, but it's a bookkeeping system. So anytime we find a new source of energy, we will add it to the list and we will bookkeep it and make sure that it's conserved. So we never, before we discovered fission, we never knew that that was a source of energy that we needed to conserve. So as soon as we find a new source, we'll conserve it. And then also, if we look at the models that we have, there's all sorts of things that based on observations we have that are in our models, in our theories, and that if the theory doesn't meet those constraints, those requirements, it's thrown out immediately. And are we missing things? I always wonder, are we missing things? Are we closing off some areas of inquiry because a model does not meet some of these fundamental baked-in observations? And I have some lists there of those. And then, the final thing I wanted to mention, and I've been a proponent for funding disruptive, unconventional technology development, seems like my whole life. And it's hard to get the funding consistent and enough for these sort of moonshot ideas that are really risky. And part of the reason is that breakthrough innovation follows a power law, just like any other natural phenomena that depends on the interaction of many things versus a single individual. Anything like that, like earthquakes, fire size, follows this power law. And so does innovation. So there'll be many, many incremental innovations, and once in a while there'll be a true breakthrough that changes everything, like electricity.
Charles, this is huge, and yes, with electricity, there must have been people who were experiencing static electricity and saying, "I think there's something here." And other people might have been saying, "Well, I haven't used it or observed it," but yeah, so. Definitely, both for this EED and UAP adjacent, which can be totally separate, they can overlap, and these other space technology areas, I think it's important to say there are extraordinary things that people are presenting today. There's exceptional progress that has been made, but in almost all of these cases, there's been very small amounts of capital. Now, whether that's the in-space bio, so many of these areas. So what we've developed is off of minimal resources, and it's like the $5 million answer looks very different from the $500 million answer versus the $50 billion answer. So with more resources, more work gets done. So next presentation, thank you so much, Charles.
Yeah, thank you.
Next, can you flip it? Thank you so much. So Enigma actually is a company that has data on UAP reporting. Enigma, could you share, please? Do we have the Enigma presenters on? Are they on mute?
Yeah.
Great. Hi, Alejandro. Thank you for joining.
Hello. Happy to be here. Thank you so much for including us.
A pleasure.
Should I take it away?
Yes, please do.
Okay, great. So my name is Alejandro Rojas. I'm coming at this from being a UFO researcher. So I've been doing that for over 20 years, writing and researching this topic. The majority of that time being paid to do that full time. So I'm kind of lucky in that way. And now I'm working with Enigma Labs. And essentially the problem that we're looking to solve is that NASA and the DoD have both mentioned that the biggest problem we have is a lack of data, like verifiable kind of sensor data. And that's true. We really don't have a case at this point that we can verify with sensor data was anomalous. And so then we also don't have much information about the nature of this anomalous phenomena. And that's a problem we're looking to solve. And what's a sensor system that we all carry around is our cell phone. So we're exploiting the cell phone to be able to crowdsource data to figure out more about this topic. So our mission is to advance the progress on UAP using cutting edge technology and social intelligence. Only through thoughtful, open-minded study of unidentified phenomena can we get answers. And our company was actually started by, we're a tech startup. It was started by other people who work in that space, who just thought, you know what, we can create an app and we can put some technology towards this to be able to help solve this problem. A little bit about us. We are neutral on the origins of UAP. So in other words, the U in UFO and in UAP means unidentified. We don't know what it is. We're trying to gather data to be able to figure that out. So we don't have a set conclusion. We're just following that data. Right now, we're gathering sightings data mostly through our mobile app. We've had the app up for about 1.5 years, and it's gone gangbusters. Right now, we're getting hundreds of sightings a week. In fact, right now, because of this New Jersey thing, we're getting hundreds a day in the last few days. So we're getting a lot of reports from the public. You can do that through the mobile app. I'll show you a little bit, as much as I can, of the app in just a second. But you can also
Alejandro,
submit
is
those
there
to the
something
website.
interesting that's shareable from those observations? I mean, obviously, there's not the ability to say what it is, what it isn't, or, the ability to test what people have actually sent into you.
You mean the nature, the trends of
Current
those sightings?
observations, or some of the things that you're seeing.
So that data includes data from historical organizations that have done it going back into the 70s. So there's hundreds of thousands of sightings in there. We've been collecting for about 1.5 years. So we have a few thousand from the last 1.5 years. I think we're over near 30,000. But to your point, what's interesting and why I mentioned that is that the data is pretty similar to historic and what Arrow has been getting in their statistics. So in other words, people are mostly seeing points of lights in the sky that are zigging and zagging around, or orbs. By far, those are the most common sightings. Also, the Southwest seems to have more sightings than the rest of the country. Most of us, I think, believe that's due to more clear skies and more warm weather to be outside and looking. The other thing is that sightings really do correlate with population. So wherever there's people, there's more sightings. That's why some of these media stories about where are there more sightings don't necessarily give you a lot of insight into where are the hot spots. Interestingly enough, we found New Mexico to have more sightings per population recently than other areas. So that's kind of something we're trying to get into. But another aspect that's really important is this next point is the online mobile community, because a lot of people, and maybe some of you can sympathize, have an experience. They see something, but they can't talk to anybody about it, or they try to talk to family and friends about it, and they get told, I don't want to talk about it, or they're even met aggressively, look, I don't want to talk about this. And so it creates these emotional problems. So they've really had an emotional kind of response to being able to report it somewhere and have a community to talk about what it is they might be dealing with. And then finally,
thank
the
you,
novel
Alejandro. And I think we've probably just got another minute or two to kind of get on the timeline. So I just want to make sure you cover, this is all very interesting.
Yeah. So the novel technology is what I'm going to get into next. And I cover that mostly on the next couple of slides. And that's how we're utilizing things like, in this case, AI. So we use AI quite a bit. That's a picture of the app. When you open it up, you see the planet and all of the sightings are listed. You can click on them and look at them. The app's just simply called Enigma. It's on the Apple Store. You can find it there. And then you'll be able to look at all of those sightings and get more information about historical sightings. What we do use AI for currently, we use it for screening our report. So it screens looks for foul language or personal identifying information, and make sure and scrub that. We don't want people's names and information getting out there. ingesting, this has been a big one for us, to scan and extract data. So in other words, we can take a paper handwritten historical report, ingest that, our AI will then go through and look for the characteristics of the objects in there. It can identify that this is a characteristic of the object that was the subject of what the person is talking about. And then it can fill out, in our structured data, things like what the color and the size and the shape was. So that's been extremely helpful. Report summaries, all of our reports have a title, and we use AI to create that. So the AI looks at the gist of the report and then will create a title for us. And also, this is in beta, and I think this is going to be really important for research, is scoring. So it can tell us how good the case is, how likely the object being described or in the media, video or pictures that have been given are truly anomalous and not something mundane. And then the
Thank you,
last page real
Alejandro.
quick.
This is very useful to have more tools. And I think your
Yeah.
presentation, we got to move into the next one, but I think your work shows that there's both access to insight and data from a variety of sources. And the private sector has the potential to generate information, as do public citizens. Private citizens, sorry.
Right. And that's a big key. Who has the sensors currently? The DoD has those sensors, but they're reticent for many reasons to be able to share that data. So we don't really have sensor data. We can crowdsource that, and I think that's the best thing we can do now. But really, until we get more data and analyze that data and take a hard look at it, we're not going to know much about the nature of this phenomena. Because right now we're just mostly dealing off of anecdotal information or debate information that's highly debatable. So, and some of, just so you know, to deconflict what's in the sky, we've got tools in there where people can look and see what satellites or cosmological thing might be in the sky, so they can then see, oh, that's just a satellite. I'm not looking at a UFO. Because especially like in New Jersey right now, we've got a real big problem with the majority of what's being seen being misidentified as something that's unusual when we're finding out it's not.
Thank you, Alejandro. And Rima, can you pull up the slides for field propulsion technologies? And then I think we'll go from field propulsion to morning bird space. Or actually, we'll go from field propulsion to Sol. And then we'll we'll see how we're doing on time. Because I know that we've got AI coming in the next one. So that'll be a good way for Ascendant and AI to kind of bridge the gap there.
Okay, thank you, Anna. You guys can hear me, right?
Yes, we can. Thank you.
We sure can. Yes.
All right. Yeah. Okay. Yeah, my name is Rich Van Durek. I'm the CEO of Field Propulsion Technologies. And Field Propulsion Technologies was created to build propulsion devices that don't need propellant. And I've been working on classified programs for about 20 years. And we've also worked on a number of different grants. Under a DARPA grant that I had before NSF, we tried to create some new metamaterials that would generate what they call ampere tension forces. And ampere tension forces are a longitudinal force that people have been reporting in conductors when they have a high current flowing through them. So one of the ways that ampere tension forces can be created is by breaking the electromagnetic gauges. And I guess what are the electromagnetic gauges? Maxwell's equations has a third equation that gets removed from electromagnetics because it causes the electric field and magnetic field equations to be unsolvable. So they use a mathematical construct called a gauge to remove it. But a number of people over the last 10 or 20 years have found different ways where they can, what they call break the electromagnetic gauges, which really means that this third equation starts generating forces that can't be described by regular electromagnetics. And so under our DARPA grant, we were tasked with determining what conditions could we generate ampere tension forces. And what we found out was we don't see ampere tension forces normally in electronics because conductors are conductive and they have an electric field inside of them always of zero by being a conductor. And that the electric current drift velocity is in millimeters per second. So we developed a composite material under DARPA that conducts electricity, but is not a conductor or a semiconductor. These materials are different, that they allow electric potentials to build up in them. And they also have an electric current drift velocity that's in the range of 1,000 meters per second. So that's 1,000,000 times greater than what we see in normal electronics. And because of that, we see a lot of forces that normally modern electronics can just remove. And so these materials, when you actually run an electric current through them, their properties actually change. So one of the things that these materials do is they generate a stress inside of them that's known as ampere tension forces. And normally these ampere tension forces are a tearing force inside these materials. And one of the things we looked at under NSF is to see if we could take that tearing force or stress force in the material and generate an external force from it. And we were able to do that on our phase 1, and we're continuing on our phase 2 to do that. And what's going on here is as the electric current flows through the material, potentials start to build up in the non-conductive portions of the material. So what happens is then the electric current starts seeing these potentials, and then the material that these potentials are in starts responding to the electric current. So what these ampere tension force does is it causes the material to feel a force that's in the opposite direction that the current's flowing. And so you could take the material, you could basically put the current through one way and get a force going the other direction, and then you could reverse the current. So you could actually create a small thruster that is bidirectional. And today we're able to make materials that you only need to apply maybe a few 100 milliamperes through. We get significant external forces inside these materials. So this is basically allowed us to try to build a propellantless propulsion device. And this device doesn't really violate Newton's laws, because what it's doing is it's taking an external force and converting it into a stress in the material. So it's basically the action force is the external force, and the reaction force is really stress in the material. So the material is actually looking like it's some kind of conversion factor going in there. And we go to the next slide. Okay, and then one of the things I bring up, I threw in there, people have been mentioning, is we have a lot of good pictures of whoever these other people's devices are that are running on propellantless propulsion. So that kind of gives us an idea that we should be able to do the same thing as they do. But some of the other applications that come out of this work that we're doing is that external force, what it does is it interacts with the material to actually generate the force, but that same force will also affect air that's near the surface of the material, or another material that's near it. So on the right side there, one of the applications that we talked to the military about is one of the things you could do is use this ampere tension forces to force the air or plasma away from the surface of the vehicle as it's re-entering the atmosphere or hypersonic vehicle. And one of the advantages you have there is all of a sudden now you don't have as much pressure on the air, so now the plasma won't necessarily form. But you could also do techniques like you could part the air in front of the vehicle, and so now the vehicle won't really see any air in front of it because it's going to have a little bit of a vacuum over the surface that could allow your vehicles to go through the air at almost unlimited speed without generating a sonic boom. And then in the middle panel there, you know, some of the things that we could also use with these ampere tension forces is we could use the ampere tension force to counteract a tension or compression force in the material. So you could take a relatively light material that doesn't have a lot of strength, but run an electric current through it, and then counteract all the stresses you would have in a vehicle of some kind, whether they're compression or tension, just by reversing the current. And then one of the other things you could do with the same material is you could actually put an outward force so you could deflect an impactor. So the way these materials would be on a vehicle is on the left panel. You show the green around the outside there. You know, the vehicle would be wrapped around in a little sheet of this material, and you would run the current either flowing out to the outside or from the outside to the inside. So if you were to flow it going to the outside, say on the right panel, you have an incoming projectile and you can see it, you know, by radar or something. And then so you could put an outward force right where the projectile is going to impact. So now you can counteract the energy of the impactor, and you're really using the energy inside the electric current to counteract it. So it could also be used as some kind of armor or shield. so that you could shield your vehicle from small impactors out in space. And we go to the next slide. So we have a partner that we're working with. They have a $1.5 billion loan guarantee from the US government, DOD mission. They're going to be putting together 10 megawatt spacecraft. And this picture is an old picture of the spacecraft. The spacecraft's going to look a lot different now that we've redesigned it. But they're looking to fly this mission by 2028. And what they want to do with the spacecraft is they want to be able to shuttle spacecraft from LEO to GEO using our type of propulsion system. And we're expecting we should be able to do multi-newtons type of forces, with 10 megawatts. And we're and some of the things we're going to try to showcase here on this mission is some of these other technologies for impact protection, and also basically lightweight members on the spacecraft. So this platform is also going to be reserved for some DoD applications the Defense Department wants to use. So while we think it is really hard to get funding in the spacecraft industry, especially if these new technologies, but I think the National Science Foundation and DARPA and the rest of these groups have really helped us along to try to get our technologies into space.
So thank you, Richard. And I know that we were running over 15 minutes from the bio segment, so we'll kind of make up some of it. But what I'd like to do is Chance on the line. Chance had previously offered. We've got some very strong EED, and also some UAP related content later in the day as well that can fit into the quantum energy at 5, and then also the 2 p.m. segment. So I'm hoping you can tell us in the chat if that's okay that we do action that as previously discussed. And I'd like to go.
I'm on the line.
Yeah, Chance, can we get you? Can you just tell us in the chat if you can join the 2 or the 5 p.m.? We'll follow up, and then can we move to Rima? Can we move to Seoul as the next one? And I'll coordinate in the chat with the presenters on the scheduling and the upcoming ones. Good to see you, Jonathan. Thank you.
Hi. Still not Seoul.
Hold on, let me find it.
I think it's the one before that, Rima. I think it's the one right before that.
It was, okay.
This is not Seoul. This is Mitch.
This was morning space.
Sorry, do you have your own, Jonathan? Can you just present your own slides? You have them open. We'll let you pull them up.
Yeah, I can. 1 second, and I have to.
I found it. Oh, here she's got it.
Oh, yeah.
She's got it right here.
Yeah. Okay, super. Good. Okay, so I'm Jonathan Birdie. I'm AI entrepreneur at RoboVision and director of technology at the Soul Foundation. It was founded by Gary Nolan, referenced a few moments ago. So we bring together experts from the industry, academia, and government to address multimodal issues with UAP disclosure being philosophical, policy, and scientific problems raised by the likely presence of UAP on Earth. And one of our projects, one that I want to talk about today, is the Soul AI project. It aims to bridge the history of UAP phenomena with the disruptive power of AI. And our aim is to uncover and link hard facts, mostly historical facts, that have been hidden for decades in a fog of stigma and secrecy. And we just organized last month our yearly conference, presenting and debating some of our insights and current UAP research. Next slide, please. So the US government has acknowledged that there are objects in the sky that do not behave according to our current understanding of physics and technology. That was already clear from previous decks. But what those objects are still up for debate. And also we take a neutral position at Sol about the true nature of who's behind those phenomena. And as an AI entrepreneur, I often ask myself, after reading some of these government reports, if our skies could already host forms of superintelligence, technology so advanced that it defies our current understanding of physics and universe, what if advanced general intelligence, AGI, isn't just something we're striving to create here on Earth with companies like Anthropic and OpenAI, but a reality that already exists somewhere out there in the cosmos? And what if in our quest to reach it, we're caught in some kind of an illusion while this intelligence is already interacting with us? It's like a fractal mind game on a truly cosmic scale. Let me tell you a quick story how I came in touch with this topic. In 2015, my team at RoboVision was asked to develop a drone detection system for European nuclear facilities after France and Belgium were hit by a wave of unexplained sightings above those installations. And what seemed straightforward revealed something unexpected: objects with no electromagnetic footprint and unexplainable autonomy in flight characteristics. So that experience still resonates a decade later. After several historical UAP flaps in the last decades, things have changed dramatically. Take, for instance, the current New Jersey flap. We've collected over 20 gigabytes of video footage in the 3 past weeks alone. A scale of data that would have been unimaginable only a decade ago. And this massive influx of information is a double-edged sword. On one hand, it offers unprecedented opportunities to analyze UAP behavior. On the other hand, it presents new challenges in noise versus signal detection. And there's a tricky part. The noise behaves differently with every UAP flap because social media behavior changes and there are new technologies. So 75 years ago, the signal was, for instance, much cleaner. And people often forget that we have very similar footage of the phenomenon decades ago, even from 1952. So how do we make sense of this data? At Sol, we apply what we call I-score principles to UAP research. Think of newspaper archives, university libraries, presidential records, and even national archives as snapshots of untainted facts, historical I-scores that haven't been modified or changed by potential misinformation stakeholders. When we combine this approach with AI, something powerful happens. We can cut through the noise, cross-reference claims across decades and data sets, and begin to identify consistent behavioral patterns that were otherwise invisible. And that's where the Sol approach truly stands out. We're pragmatic, systematic, and laser-focused. Using state-of-the-art AI, we've developed methodologies to process fragmented, potentially biased, and incomplete data. Our flagship in-house tool is what we call the Sol Claim-Based AI Knowledge Graph, a system that links together witness accounts, historical data points, and observations into a coherent web of trusted evidence. Imagine, for instance, a 1952 newspaper claim via clipping that we digitized or that newspapers.com digitized. We can now cross-reference that with publicly available military logs, weather records, and even astronomical observations, as Beatrice is doing in the Vasco project. What used to be isolated fragments suddenly start forming patterns, and at Sol we connect these dots. But we face a double challenge. AI systems like today's large language models struggle with hallucinations, and that's exactly what we do not want. We have enough noise, we have enough misinformation, and even at some points, mass hysteria. So without clean, curated data sets, distinguishing facts from fictions is incredibly difficult. So we have to come up with tricks with, for instance, competing AI models and that sort. So high quality data is scarce. And most UAP records, of course, are either controlled by government or remain anecdotal. But there is a reason for optimism. By blending AI with traditional research and new data sources, we're uncovering what I call informational I-scores, as previously mentioned. So pristine time capsules of facts, much like drilling into the Antarctic ice to study ancient climates. These untouched records give us a clarity in a world flooded with misinformation. And why does this matter? It's about driving potential breakthroughs, as was mentioned earlier, to reshape energy, materials, communication, and propulsion. And we want to really be a broker in this domain with Sol, even, for instance, facilitating research and investment in these topics.
Thank you so much, Jonathan, and really appreciate, both Sol and other groups, that are really trying to bring more people together to just, figure out what's possible, observations, science. We'll need to move into the next presentation. Ascendant So we're Ascendant AI is both bridging this advanced anomalous phenomena and also AI, so while it's on this deck REMA, that's a very good fit for actually being in our next segment, which is the AI, so artificial intelligence, NHI, non-human intelligence, and then also exceptional human capabilities, a wide range of advanced human performance. All right. So do we have Ascendant AI on the line?
Yeah, can you hear me?
Yes, thank you. Hi.
Hello. And I don't see my picture yet.
We see you. Yes, thanks.
Oh, you do? Okay.
Yes, we
I
do.
don't know if it's centered or anything, but there you go. Okay. And I'm
We
not
put it
I'm
up a
not
little bit. Your forehead's cut off. I'll tell you.
okay.
All
I'm
right,
not
perfect.
seeing
You're great.
I'm not seeing the slides, so I'm assuming you're on the slide one.
I can't find the slide. I'm sorry. I'm still looking.
It's called Operation Skywatch. It was really close.
Oh, got it. Okay.
Thanks, Rima.
Got it. Thank you.
Okay. Wait, is it up yet? There we go. I see it. Okay, my name is Mitch Randall. I'm talking to you today about Operation Skywatch, which is a nationwide citizen platform to confirm UFOs are real. So I'm using the word UFO because we are talking about, forget the U for right now, but we're talking about flying because we're looking in the sky, and we're talking about objects because we want to see them or bounce radar signals off them. So we can go to the next slide. So what the plan is this is a rare event. So we can make instruments that are high quality but never see an event, or we can make an instrument that's maybe not as high quality but just spread out everywhere so that when a rare event occurs, we can see it. This system that I'm talking about, Operation Skywatch, is built on 3 sensors. One of them is a video app where the idea is, well, let me back up 1 second. Someone earlier today talked about the 5 observables. In order to prove UFOs are real, we want to see the observables, but the one that this whole system is designed very specifically for is instantaneous acceleration, because it's pretty much, you know, if there's something that goes very fast, that doesn't prove it's ET technology. If there's something that has no control surfaces, that doesn't prove it's ET technology. But if you have something that does a right-hand turn, a right-angle turn at 600 miles an hour or Mach 3, that is evidence of something that we can't do. That's not in our envelope of performance for our inventory on Earth here that we know of. So in order to do that, we have 3 sensors. One of them is a video triangulation sensor. The point is, if you get more than one person that has a video of the same object, you have something to go on now because you can triangulate and get a point. Once you get a series of points in the sky, you can see those right-hand turns and you know the timing. So the video is not just a video, it's also tagged with the IMU information from the phone. So you know the pointing angle, you know the time, you know the location. And those are critical in order to figure out, where the object is in the sky as a function of time. That's called kinematic tracks. And this whole thing is about kinematic tracks. So the second sensor is NUFORC, the National UFO Reporting Center. So we want to get the provenance so that we don't just have, a fake video or something like that. We want to have, what were the circumstances of this particular event? We want to have all that recorded from the human standpoint and what the witnesses experienced and saw. So, but the kind of the big, the star of the show is really the passive radar. So passive radar turns out it's a technology that's been around for decades. It's not a new thing. It's never been proven or anything like that. It's a known working entity, but it's just never been applied to this problem. And the reason it's so important here is because it's a receive-only technology. It uses transmitters that are already out there. So like FM, we're using FM radio transmitters, which are all across the continental United States, which means we can have receivers all across the continental United States and get radar coverage of the entire entire continental United States. And then these three pieces of information can be displayed in real time, archived, and papers can be written about them to publish them. And the goal of the project is to bring the public on board. Public knows what UFOs are, but they don't know that they're real, and neither does the scientific community. They're not sure it's real. And the point of this project is to prove that they are real. So on the next slide, please. Our goal is to get 10,000 of these units out there by building a commercial product that citizens can actually purchase. And so citizens can deploy these throughout the country. Now this shows, in this image here, shows a grid that's perfectly spaced. That's not necessary. We just want a whole bunch of these out there because each one can detect a delay and a Doppler. But when you combine them together, you can triangulate to get a position and a velocity and then an acceleration. And the specs are, it can measure, and this is, all of these things I'm talking about are scientific instruments. So there'll be papers written about the performance of these things, and I'm talking about the radar, the video app, and the human intelligence. So we can characterize those and know how far to trust each one. The radar, people are so used to dealing with video information that they're not really totally up to speed on what radar can do. But that's why the military uses radar, because they don't have people with binoculars on their ships to figure out where everything is. They have radars because they work really, really well, and they're very quantitative and very accurate. So this will provide data that's just unprecedented. Just in the talk before, Jonathan was talking about separating signal to noise. This is a very strong signal compared to what you get with video or what you get with eyewitness reports. So that's the idea of what we're trying to put together. And on the last slide, the next slide, please. I just want to give you the big picture of what's going on for the project. So this is all a project for the public good. It's what we're going to do is raise $3.5 million as of basically philanthropy, because there's the return on investment here is that the world is going to know that these objects are real. That's what we're doing. We're trying to bring the knowledge of the public up. So it's a $3.5 million project, 24-month development cycle. At the end of that,
Thank you, Mitch. We really appreciate it. I'm sorry that we got to jump out because I think we're over the 5, but really appreciate you joining. And you're really kind of bridging both segments. So we've officially kicked off the AI digital assets portion of the next segment, which will be followed with the advanced human capabilities, which will include areas like remote viewing, precognition. So we've got a lot of good, we've actually got quite a robust segment coming up. Rima, do you have that deck to pull up? Or do we need to send it to you?
Which one are we going to now?
They're numbered. So this one is 5, and it says something like digital assets or DL, AI.
Got it.
NHI. Great. And thank you to Chance Glenn is going to be presenting later in the day. So we have some of this highly advanced energy, both with Morningbird Space and also with Falcon Space, that will be transitioning to a later period in the day. So we're working through those logistics. We're going to have similar content in the 2 p.m. and 5 p.m. slots with quantum energy, and also our energy technologies at 2. Quantum at 5. All right, Rima, do you have the deck? I think, is the first one the NDF, or is that Government Blockchain Association?
I have it coming up. Give me 1 second, just pulling it up.
So if Gerard and Kevin, are they both on?
I'm on.
Okay, great. I'm not sure if you're first or second. I can tell you in a minute, Gerard. I think it might, is Kevin on? I think we were having Kevin go first, but we can certainly go to GBA, or maybe you're up. All right, great. So let's get started. Kevin, great to have you. And you're so active. We know each other both in the blockchain, digital asset space, where you're involved with just probably, the numbers are right there. So know you through work in digital assets, but also increasingly in space. So grateful that you can join us. Could you share with us, in this 5 minute, because I know it's a brief presentation, but touching upon why digital assets is important for space and what you see happening as you go through your slides?
You got the GBA slides up. Do you want Kevin to go first, or do you want?
Well, is Kevin on? I mean, I think we've got the GBA slide, so let's roll right ahead with you.
Right, sounds good. Well, and Kevin and I work very closely together, so a lot of the stuff that we're talking about here, I think will dovetail into his talk very well. So thank you, everybody. My name is Gerard Daché. I'm the founder and executive director of the Government Blockchain Association. We are a nonprofit industry association. We have members. We have about 4,500 site users. We've got about 10,000 members in our meetup group. We have about 150,000 LinkedIn connections on our LinkedIn team. And our members are in the public sector and the private sector. Our public sector members work in about 500 government offices around the world at the local, state, national, and international level, and in virtually every industry, right? So my background is blockchain. There's an intersection with space, but blockchain really impacts every industry. So our government members are everything from DMVs to people in hospitals, supply chain, identity, all those different things. As a result, we have over 50 working groups. So there's a little picture down there in the bottom corner. I know you can't read any of them, but everything from aviation to quantum. And so what happens in these working groups is the public sector come and they say, here are the problems that we're trying to solve. And the private sector says, here's our solutions, here's our white papers, here's our demo. And it's an enormous network of people that again, connect, communicate, and collaborate to solve public sector problems. We were recognized by the United Nations. They have a group called the Internet Governance Forum. It's a group of folks like MIT, ICANN, Google, Microsoft, Meta, and they meet every year to govern the internet. They've got 31 different sort of subgroups on everything from digital health to identity to not digital assets. But they didn't have anything with digital assets and blockchain. So they came to the Government Blockchain Association and they asked us, and we said yes, to host the Dynamic Coalition on Blockchain Assurance and Standardization. In fact, this week we were hosting the main stage, a booth, and some other assets at the annual Internet Governance Forum. They bring together about 10,000 public and private sector people from around the world to, again, connect, communicate, and collaborate. So that's a big function of who we are and what we do. But like I said, we have 50 working groups. One of those is space. So if you go to the next slide. So I want to talk to you a little bit about the space working group. So the leader of the space working group, Javon Swint, is actually on the call. If we had time to take questions, I'm sure he'd be interested and available to answer them. But what the space working group is doing is they're exploring the integration of blockchain technology into space-related initiatives. And sorry about the background noise. I'll just do this quickly and then go on mute. But that includes the supply chain management of space-related assets. It includes the secure communication systems, improving data integrity for satellite operations, space exploration missions. And part of what this group is doing is they're prototyping a blockchain-based solution for the real-time identification, tracking, and management of space assets, giving confidence to all the stakeholders of the reliability and integrity of space-related data. And clearly from a defense, threat tracking, all kinds of stuff, information integrity is really a huge issue. There's a lot of concerns in terms of security. So as part of that, that's why the working group is collaborating with other GBA working groups, which includes our quantum working group. And the key thing that they're doing there is they want to make any solutions that we do in the future quantum proof. Our cybersecurity working group and our supply chain working group. So this group meets, Javon, I think you guys meet twice a month, and all members of the space community are invited to participate. It's just a phenomenal group of people that do a lot of mind share. If you go to the next slide, how can you get involved? Well, we've got a ton of free resources. If you go to YouTube and you just type in Government Blockchain Association, you'll find, 200 or 300 videos from some of the top people in blockchain. This includes the guy who invented blockchain in 1991. Scott Sternetta. They put the first blockchain in production. Co-founders of Ethereum, the founder of Cardano, the former chair of the US House Ways and Means Committee, people from the National Security Council. So all kinds of experts there. You can also join the GBA. It's free for civil servants. It's Government Blockchain Association. Join the Space Working Group and attend some of our courses and learn a little bit more about the blockchain maturity model. We're in the process of developing a space supplement to the blockchain maturity model. So with that, that ends my presentation, and thank you very much for giving me a chance to speak.
Thanks so much, Gerard. It's great to see you. And I think Kevin's next with the National DigiFoundry. Kevin, can you hear us? Do we know if he's on the line?
What's Kevin's last name?
Jackson.
Not seeing anybody in the attendees with that.
And I thought he had a parallel meeting going on this
It's at
afternoon.
3, is it right now? I think that is at 3. We can
Okay. All right.
anyways, let's
That could be that.
yeah, we can always see if we can loop back to him, but let's move on. So moving into the next section, and we can always loop back to Gerard, if you can try to get Kevin on, that would be great. But we'll move into the exceptional human.
You can make noise, yeah.
What's up? Yeah.
Oh, I'm sorry about that. I thought I was on mute. Yeah, I'm reaching him now.
Great. So we'll come back to Kevin, but let's get into the exceptional human capabilities part of this segment. And one of the areas that we'll have we've got precognition, we've got a wide range of advanced human capabilities. We're also going to be speaking to people who work with creativity. We'll also be speaking with some of the people who established the US government's remote viewing program. So I suspect that we'll have one of the founders, Dr. Hal Puthoff, a little bit later in the day. And I know we've got Paul Smith and a number of his close colleagues as well. But before we go into Paul Smith, Yana, MK, and others on the RV space, I think one of our colleagues, Sean Mahoney, is on the line because he has some insights to share on the remote viewing. And as context, that there were a number of remote viewing programs that were funded by a wide range of agencies. I have the list right next to me, but I don't have it open. But that included a number of entities in DoD, in space technology as well. Sean, are you able to speak?
I'm here, Anna. Thank you.
Hi, Sean. Great to see you. Thanks for
Good
joining.
to see you too. Yeah, thank you for hosting this and inviting me. This is really cool.
It's great to have those Air Force leaders on the line as well on the presenter side.
Thank you. I'll be quick. I don't have slides to share. Just wanted to touch on 2 quick things real quick. So for my day job, I am a civilian government employee at the Air Force Research Laboratory. And I work in strategic partnering where we host the regional networks for AFRL. And for a lot of the small businesses and startups that I've been seeing presentations for some of the really cool work you guys are doing. So this would be a funding resource for you guys to go after. So the Mid-Atlantic is hosted by Cornell University, and you could just Google search Mid-Atlantic Regional Network for AFRL. And they have 3 funding calls a year. And you have to have a sponsor at the research lab, but you could use Air Force Tech Connect, which you can get to through afresearchlab.com to find a partner for whatever research area you're doing. And then the Midwest Hub is hosted at Purdue. So for those of you guys doing, space research and stuff like that, the biotech stuff, that's a resource for funding. The other thing is, as Anna mentioned, I am in the remote viewing field as well as a side thing for my Air Force job, completely separate. I'm really happy that Paul and Hal are here to be talking later. Those guys are great guys, tons of great info. So I do work with the Future Forecasting Group, the guys that look into interesting topics, looking at cryptocurrency performance and stuff like that. It's a really cool experiment in remote viewing, just showing what is capable. In fact, the most recent project we did was looking into the new centrifuge in China that just opened up. That it goes up to its hypergravity. It's like 1900 times the Earth's gravity that they're doing experimentation with. And we did a blind project on that, and it's coming out this Friday. Lots of really cool stuff. So I don't really know what else. If there's anything,
Yes,
you think I
Sean,
should
you know,
touch
not
on?
that we're going to get into it in depth here,
Yeah.
but we've got like the upcoming speakers. The thing that's interesting to me is this is one of these areas that some people kind of are less familiar with, but there's so much data off of government funding in terms of research style papers that, there's hundreds of them that, there's books that it's like archives of lots of government sponsored scientific research and outcomes. So good to have you on the line. And let's move in next to who is next on the agenda here. I see we've got Paul Smith.
Anna,
Do we have
we do
Paul's
have
slides?
Kevin. And just to let
Oh,
you know, Kevin
let's pull
Jackson just
Kevin in
joined.
then. Yeah, it'd be great to pull Kevin in.
Hello, everyone.
Hi, Kevin.
Sorry, have back-to-back schedule today, going bouncing back to back. But thank you for the opportunity to present today. I've been asked to talk about the National DigiFoundry and the work that we're doing specifically around space and leveraging that technology, digital asset technology, to support the mission of low Earth orbit, of the new low Earth orbit economy. So if you're not aware, the National DigiFoundry was formed about a year and a half ago based upon a challenge that President Biden identified, which was a lack of a whole of government approach to addressing the risk and harnessing the benefits for digital assets across multiple industry verticals, not just finance. And there's a lot of misinformation and a lot of fear that's been placed across the marketplace based upon lack of understanding or lack of knowledge of these technologies. That resulted in the executive order for President Biden and drove the establishment of a digital asset R&D fast track action committee in the White House Office of Science and Technology, which in turn led to a grant that was offered by the National Science Foundation. Thank you very much, Anna, for your vision. And which was awarded to the University of Texas at San Antonio, which houses the National DigiFoundry. So essentially, we have multiple working groups that look at needs and requirements of the public sector, specifically U.S. federal government. And we do have a space working group. And within this, we have actually two working groups that have worked specifically on solutions that would support the low Earth orbit economy. One, the space working group, which is specifically leveraging digital assets to advance the space economy. And their project for the last 6 months, or first cycle, was looking at the use and maintenance of artificial intelligence models. Just about anything you do right now is organizations are sort of embedding artificial intelligence, sometimes good, sometimes bad. But one of the most important aspects of this is how do you keep track of the pedigree of these models, the training data that was used for these models, and to make sure it's still appropriate for the mission. And many low Earth orbit systems are getting artificial intelligence embedded into their operations. So we developed we did research into enhancing the governance of AI machine learning models and the training data so that we can ensure more reliable and robust on-orbit decision support systems and autonomous vehicle operations. Another sort of also important aspect is a secure information sharing. And this is required to increase the awareness and understanding of how Web3 solutions and services can improve poor information orchestration among any ecosystem, especially for low Earth orbit. So our secure information sharing working group actually developing industry best practices to leverage Web3 technology and blockchain in order to provide validated, secure information across an ecosystem. And this is based upon work that was done over the past 5 years with the United States Air Force and leveraging blockchain for managing information in the Civil Reserve Air Fleet. And so this secure information design guide has been completed and released. So if you're interested in learning more about the National DigiFoundry, please contact me, Kevin at digifoundry.org. We'll be more than happy to give you additional information. And we welcome membership so that you can participate in our ecosystem. Thank you.
Thank you so much, Kevin. Much appreciated. And have a great day. We're sorry that we're not able to participate in the NDF meetings as well. All right. So bringing in Paul Smith and his colleagues. Hi, Paul.
There we go. I was telling myself, you've got to unmute, and then I forgot to unmute. So thank you.
Good to see you. Thank you for making the time today.
I'm happy to do it. I appreciate the kind words from you and from Sean, and glad to see so many of colleagues and friends here.
Paul, would you mind just giving us, because I know many people are familiar with your work, but just kind of the 30-second, your leadership role in, Stargate and other programs?
So
I know what it is, because not everybody's grounded in what remote viewing is.
Yeah, gotcha. I don't see the countdown clock here, so I don't know how long I'm going to go. I spent 7 years in the Stargate program. The whole time I was a captain in the Army, I was in that program. I was a operational remote viewer, but I was also one of the main trainers there. I was also the security officer and the unit historian. Since that time, I've got my PhD, founded a company teaching remote viewing, also founded the nonprofit International Remote Viewing Association. And, the list goes on far longer than 5 minutes. So at any rate, I've got a long time grounding in the remote viewing space. My job today is to provide the context, the envelope, if you will, for the next two presenters, Yana and MK, Michelle. Just give you the context of remote viewing, what it is basically. Obviously, this is going to be very short. Basically, remote viewing is the use of one's mental powers to perceive distant targets through sensory means, impressions, concepts, and so on. It's a trainable skill, and it's based on a very widely distributed human ability. In fact, it's probable that everybody has the ability to a greater or lesser degree. This was established by Hal Puthoff and his colleagues at SRI International when they were researching this for the US government. I'm going to start off by saying what remote viewing is not, because there's a lot of confusion about this in the general remote viewing community. It is not channeling. It's not psychic reading. It's not fortune telling. It's not out-of-body experience. I'm passing no judgment on these things. You can form your own opinions about them, but remote viewing is a distinctly different discipline from these things, although it overlaps probably with all of them in some degree or other. Remote viewing results are concrete, they're objective. They involve sketching, verbal or written reporting, modeling, 3D modeling. In fact, if you've seen Close Encounters of the Third Kind, you've seen something similar to this. And it transcends space, time, and shielding. I'll talk a little more about that in a moment. The program got started in the early 70s. The very first remote viewing protocol was formulated by a parapsychology researcher named Ingo Swann, who was also an artist in New York at the time. And it got really kicked off by Hal Puthoff, whose name has come up a number of times here.
We're joining it too, I think. So speaking on something else.
Yes, speaking of something else. Hal and Ingo Swann getting together for an experiment that caught the attention of the CIA, who initially offered a contract in 1973 to research this, mainly because the Soviets had been spending literally hundreds of millions of dollars, not rubles, but dollars, researching this field. In 1975, the CIA released its interest in it. Essentially, the Air Force picked it up at Wright Pat Air Force Base, FTD, in fact, under a gentleman named Dale Graff. The Air Force pursued this until Graff moved on to DIA. The Army started a program in 1977. DIA had its own effort going in 1979, and they joined forces in that. DIA received the entire Army program in 1986, early 86, and it became known as Stargate in 1990. I should tell you, it is two words, Stargate, not one word, Stargate. Stargate is a book, a movie, and a TV series. Stargate is the remote viewing program. People get confused. The CIA obtained authority for it. Congress transferred that authority to the CIA in 1995. And the day the CIA got control of the program, it terminated the program. A lot of people, their knowledge of this is the report that the CIA commissioned that justified closing the program. What they don't know is that the CIA didn't even initiate that report, the research for that report, until the month after they had already closed the program down. So if there are any CIA folks on the feed here, my apologies to you guys, but the CIA was being duplicitous again, much to our surprise. So anyway, the declassification effort proceeded from 1995 to 2004. Next slide, please. Okay. So there are, of course, always pushback from the skeptical and mainstream science communities oftentimes. And there are three claims I'll address here just very briefly. First of all, the claim is from the skeptics that there's no evidence for remote viewing success. That has been demonstrated to be false, and I'll cover some of that evidence very briefly shortly. That any positive results that you get from remote viewing experimenting or operational use is either due to fraud or error. This has been proven to be false. There's a claim that our remote viewing was never used actually operationally or in decision-making in the military program. This is also demonstrably false. So if you have believed any of those things before, I'm happy to argue with you later on. So evidence, this is just a small snapshot of the evidence. Probably the most powerful piece here is Congress mandated a review of the remote viewing program in 1988. And at the time, Ed May, who was the director of the research part of the program at the time, dug into the archives, came up with almost 26,000 remote viewing trials, evaluated them, and came up with an astronomically high odds against chance figure, roughly 1 to 2 trillion odds against chance that this was accidental. It pretty much essentially establishing there's a real effect there. The PEAR Lab, Princeton Engineering Anomalies Research Lab, did some successful replications, although they did them precognitively. Again, no time to explain, but it was really quite a remarkable protocol that they used. And you can see they had a very high success rate as well. I include these last two because people are often saying, well, if you're psychic, why aren't you rich? Well, that is actually possible. Greg Kolodziejczyk ran a series for about 10 years, 50, almost 5,700 trials, had a very significant p-value. And the interesting thing here is that he netted, this is not the gross, this is the net. He netted $147,000 using remote viewing to predict futures contracts. At the University of Colorado, they ran a similar project, but using the Fortune 500. They had some seed money involved. They netted $16,000 on a $10,000 investment. So you can see there's some interesting results, and this is just a small fraction of the research that's actually been done on remote viewing. There's a claim that there was no peer review of the remote viewing program, and this is also false. In fact, here's a short list of the agencies and entities that were involved in tracking the research there to make sure it was legitimate and above board. Some of these involved, at the time, quite well-known and well-placed scientists and academics. So there was definitely oversight of this program. Next slide, please. Okay, so applications, again, just a snapshot of applications. This has been used, obviously, in intelligence collection. Forensics, there have been successful uses in police work, criminal investigations. Investing, predictive, of course, and particularly in the vesting space, which I just showed you, there's been quite a bit of involvement there. Sean actually told you about one of the projects out there in the predictive world using remote viewing to some success. It's been used in space exploration. I want to add a caveat here. This has got a bit of a checkered history. There are people who've used it to research UFO, UAP, extraterrestrial kinds of events. And in fact, some of that was pretty questionable. Some of that research was, in fact, very questionable. But there's been some legitimate work done as well. One interesting feature, in advance of a space probe that was due a flyby of Jupiter in the, I believe, it was mid-70s, Ingo Swann, again, the creator of remote viewing in the first place, remote viewed it in advance because they would get hard feedback when the space probe went by, identified rings around Jupiter, which at the time were believed to be totally fictional. He was roundly criticized for claiming there were rings around the planet Jupiter. But that space probe, in fact, identified that there were rings around Jupiter. So his information was confirmed. There are a couple of there are issues and strengths in remote viewing. First one, variable precision. Remote viewing isn't always precise. Sometimes it's very precise, sometimes not hardly precise at all, and sometimes you get no actual data. And that's
Paul, this is so interesting. It's such a rich presentation. I know that, normally
I'm running out of
we
time,
wanna
is
hear
what
an
you're
hour,
saying.
so we want to give you a minute to say, we want to hear an
Okay.
hour, but give you a minute.
Well, in fact, I think you can, well, I'll just hit a couple of things. Mental noise is an issue with remote viewing. We have to learn how to deal with that. I say poorly understood causality. We have no idea what makes this work in the physical world, if it is indeed physical in the first place. I'll leave the descriptive analytic question. The advantages are that there apparently is no shielding that can stop a remote viewer. That was one of the reasons for the high security classification of the program, is because the only way to stop a remote viewer from remote viewing is to take them out. And we did not want the KGB interfering with our lifespans. Distance is no factor, as has been demonstrated in a number of cases. And atemporal access. In other words, past, present, future are accessible through remote viewing. Precognitive future is a little bit iffier than doing the past or the present, but nonetheless, it is a valuable feature of this skill and discipline. Okay, with that, I'm going to end and pass it on to Jana
Paul?
Roca.
Rima,
you.
you want to bring us to the next slide? Or, I'm sorry, yes. And hi, Yana. Hi, MK.
Hi there. So this is MK's slide. Mine is probably behind it.
Yeah, Yana's is next.
Great.
Can you flip to Yana's slide? There.
No.
Nope, not that one.
I don't think we saw Yana's slide. Because we
No, no. Did you lose my slides?
yeah, I don't think we saw it. So we were emailing about that last night. But so if you have it to present, you can. And that was one of the things we were emailing about.
Mm-hmm. Do
And
you want me
actually,
to?
maybe while she does that, I can do my slide because it's quick and I have to jump to a board call. So Yana can tie the nice bow on this. But what Paul is explaining is the application of remote viewing, and what I, as MK from MK Advisors, wanted to do with a for-profit business. And you can put up my slide. It's the singular slide that was right after Paul's. So my company's interest is on advanced technology. It's how I discovered remote viewing. I actually discovered remote viewing and studying Dr. Hal Puthoff's work in advanced energy, and then tried to figure out what was he doing before this that made him go into advanced energy. What was it he quote unquote saw? In that discovery and talking to Hal since 2017, I started getting projects that were really forward looking for our traditional everyday customers, Department of Defense, OSD, research laboratories, et cetera. On one side of the house, that's where we focus our research and development to outline strategic roadmaps for things like 2D materials, graphene, with the goal of reducing and or limiting or eliminating lithium and other rare earths from our energy platforms. That's a directive coming down from OSD. We then activate a team and then put together a roadmap and then become part of the program team to execute that roadmap. We don't make products. I don't have an interest in making products. I have interest in seeing the US industrial base expand and be autonomous, not reliant on foreign supply chains as heavily as we are. We are looking at technology development in ammonia and hydrogen platforms using plastic waste to create those, with byproducts being black carbon, which can be used to turn into what we would term electronic grade graphene as an example. Why those projects on the left turned into research on the right is because if I have a 2050 mandate to reduce carbon emissions to 0%, how do I determine what the roadmap's going to look like in 2050 when I can't see into the future, quote unquote, couldn't see or thought I couldn't see, to determine maybe some data points that could be accessible, retrievable, and relevant for our research. So we do traditional research, but we use non-traditional tools in the background, and remote viewing is one of them. Yana and Paul has been mentoring Yana for years. Yana leads my work on the remote viewing as we invest. I'm not a remote viewer, and I'm not a remote viewing expert. I am a for-profit company who incubates other companies and other processes and technologies to get to scale. Using remote viewing and looking into a future state to get data that could help inform what we decide now is useful in any situation, even if it comes in a dream. And we've had a lot of those precognitive dreams in our team. So those were some indicators that these are things that maybe there's a process. Remote viewing has created the scientific method, or applied the scientific method to utilizing the unobservable observed, right? So what you can't see with your eyes, but you can access in terms of data. So that's MK Advisors and the work that we're doing here. We're looking at future state, and just to put a bow on this for us, in the study that Yana has led in a year, has assembled close to 1,200 samples of remote viewing targets to identify how timely or how accurate future targets can be. So before the time arrives, can we get good information ahead of the event happening? And we're testing that in a multi-year process. So thank you, Anna, for letting us share, and I'll turn it over to Yana.
Okay, so I've sent the PDF again, Anna. I can
If you
also
want to
put
just
it on my
present it, why
screen.
don't you just present it from your side?
Yeah, okay, I share my screen then. Okay, let's see how this works.
Yeah.
Are you able to see it?
And then next up, we have Julia Mossbridge, and then Entangled after her. We see it. Thank you.
You see it. Okay, good. Okay, short introduction of myself. Jana Rogge is my name. I'm joining from Germany, presenting in my capacity today as the director of SciVision Institute. I'm also working with Paul presented before me, and then MK advisors, of course. And thanks to Paul, I don't have to explain remote viewing in general. So even if remote viewing was originally developed in an intelligence environment, we're not doing spy work anymore, at least we don't do it. And what I'm talking about today is where remote viewing is a useful application for the research and development sector. The graphics on this slide are an excerpt of a recent study that we did in 2023, investigating the accuracy of CRV, controlled remote viewing, which is one specific remote viewing method. And each of the green circles represents a single remote viewing session, in this case from the same viewer. And the green color indicates the correctness of the data divided into the different perception channels. And in the left chart, you see measurements of several of these series with an average score. And you can see that the quality is not consistent throughout the sessions. We have very good hits, so very green circles, and we also have not so good sessions. But the average score, the average accuracy of the data throughout all throughout all sessions is 84%. And with the absolute correct data, what? I heard somebody, with the absolute correct data, about 68%. This is what we call a relevance score. That means the data that is helpful for solving a question. Next slide. Oh, I don't have to call the next slide. Of course, I can do it myself. So, remote viewing is a trainable skill. So we are working with larger teams of trained remote viewers for both the scientific studies and the applied projects. And the key element is the blinding protocol. That means the viewer only sees this number, what we call a tasking number over here, and that stands in for the target. So they don't know whether the target would be a place, an object, an event, technical process, whatever. The client always only talks to the project manager. So in this case, that would be me. And the project manager acts as the interface to the viewers, tasker, analyst, etc. In many cases, also, we keep the tasker and the analysts at least semi-blind to the project question and background. What we do is a consensus analysis, and this means if the majority of the viewers report the same data element, we have a high probability that this piece of data is correct. On the right side, there's an example of a project that we did in the past in reconstructing a past event. In this one, we were asked to locate the highest left behind item of a 1924 Mount Everest expedition. So this was 100 years ago. The remote viewers in this project were able to identify the object as an oxygen bottle and narrow down the searching area to the size of, I would say, size of a football field, which is pretty small compared to the entire summit area of this mountain. So we do a lot of work, or we have done several projects in the field of archaeology and anthropology. This one
And I
is.
think we're getting close on time, so just want to give you that 30 seconds to close out, please. Thank you.
Yep. Okay. Current project for NASA. We are exploring moon pits. What we found is that the temperature measurement indicates that there are possibly tunnels or cave connected to these pits, and we don't see them because they're in the shadow. And what we can do is we send remote viewers out mentally, of course, to explore the dimensional features up there on the surface. And if we find something, then the client can decide to further investigate the area with conventional means, of course. So last thing, what I want to mention is that we also do projects in supporting research in advanced materials and future energy tech and so on. We can, of course, not just look into the future, take notes and pull it into today's reality, but what we can do is support or develop supporting data that helps to identify the probability of different options that we can look into. Okay, I could talk for hours.
Okay, Jana, I understand. Much appreciated. I know you're very active in this space, so appreciate you sharing your expertise today. We now have Julia Mossbridge, who I'm seeing on the chat. So hi, Julia. Thank you for making the time to join us today. And Reem, I think if you can move to Julia's presentation, that would be appreciated.
This has been really fun so far. It's it just feels like here we go. So hello everyone. You might wonder why I don't know. Should I wait until the slides are up? I'll start talking.
You can start talking while
So-
Rima pulls it.
Yeah, you might wonder why people are starting.
Is this the right slide?
No, this is the prior,
Oh, this
or
is-
no, this is yours. Yeah, this is yours. Good.
You might wonder how exceptional human performance actually relates to the space economy, and I just want to say two things about that. One is, as was mentioned earlier, the seventh observable. You can actually observe by talking to reputable people about their experiences with UAP. You can observe that people are having cognitive impacts. The other reason is because if we're going to actually colonize space and get off planet, anytime soon, we're going to have to really improve and take care of our cognitive infrastructure in this country. So when people talk about cognitive warfare, try to keep in mind that what they're talking about is a violation of cognitive infrastructure. And so we have to know what that is. So I'll just briefly do a little education on that. There are 4 C's. I think of them as the 4 limbs, 2 legs, 2 arms: compassion, creativity, curiosity, and critical thinking. And there are 2 I's: intuition and insight. And today I'll be talking about exceptional human performance in the area of conscious precognition. And that weaves together both intuition and insight, which are both crucially important, especially in the world where we're working with AI as a teaming partner. We need to make sure that our insight and intuition are still on board and in fact developed more than they have been. I'm going to go ahead. Oh, the timer has not started, so I got away with that whole minute without the timer starting. So I just want to point that out. Thanks, there we go. So yeah, no problem. I just wanted to point out also that it is really easy to test conscious precognition. This is not something that's hard. This is something that's super simple. And I'm showing you right on the screen how you do it. You have some kind of an experience, whether you put a participant in a place where they can dream or where they can meditate or move into some kind of state where they're ready, like maybe it's a remote viewing session. You record that experience. Let's say that person thinks, oh, there's like a moon and a star, and that was the experience I had. You wait for a period of time that can vary, could be weeks, could be years, could be days, could be seconds. You randomize, this is just to test it. This is not an application, this is to test it. You randomize a pool of, over on here, I have a pool of potential targets. Then you choose which target, use the random number generator to choose which target to present. So in this case, it's the moon. And then you use independent judges to independently score. I've recently been working with Damon Abraham on actually using AI to independently score the likeness between the intended target and the experience that was recorded over here. You can read reviews and relevant papers about precognition at the bottom. I'm not trying to prove to you it's real. It's been shown to be real. And the US intelligence community has declared that it is real in 1995 in that same report that killed Stargate that Paul was mentioning. So you can go to that link and learn more. Next slide, please. So what I've been doing for about 15 to 20 years is trying to understand how precognition works and showing it in different systems and different types of precognition. And what I ended up doing is getting into the world of photonics, because it turns out photons behave similarly to the human mind. I'm very interested in the idea that there's some kind of relationship between photons and consciousness, but that's a tangential. Photons also seem to be impacted by things that happen in the future. So leaving that aside, there's an upcoming paper I'm working on about that. I did a year-long gathering of photons via a friend at the Advanced Physics Lab at Berkeley, and he was replicating some of my work. So for a year, he gathered a lot of photons. And on the right-hand side, when I went and I took the data, and this is just how many photons were absorbed, and I sorted it by moon phase, and I'll explain why I'm doing that in a second. I'm sort of going backwards as usual here. You can see that there's big variations in the number of photons absorbed by moon phase. Why I did that is because I'm very curious about this relationship between precognition and photons, or insight, intuition, and photons, or extended human capacities, or consciousness and photons, however you'd like to talk about that. So and I knew that I had data showing on the left that a group of people who had in the blue for 1 year and in the green for another year had done a bunch of online precognition tests where there was a right answer and a wrong answer. And there was this pattern in how many tests they decided to perform in each of the phases of the moon. Interestingly, I'm not showing it here, but their accuracy levels tended to follow. So low accuracy with full moon, best accuracy with third quarter, low again, or sort of it's not clear in the new moon, and then dropping down again in the first quarter. So this is very interesting to me. Next slide, please. What it tells us is there might be geomagnetic effects, because the new moon and the full moon actually change the magnetosphere just a little bit, but there also might be gravitational effects because the full and the new moon obviously have gravitational impacts, like for instance the tides. But those might be effects on photons and bosonic particles. That's the photonic results. And there seem to be parallel effects on human exceptional performance. So what does this have to do with space? The application I keep thinking about is synchronizing astronaut intuition sessions. So in the future, of course, people will know that intuition and insight are key components of cognitive infrastructure in my worldview. And astronauts will be having intuition sessions when they'll be making decisions about important things, or they'll be working on creative solutions to problems, or trying to get the answer to the problem from the future. And they will time these to either gravitational, geomagnetic, or bosonic levels. Another application, ignoring the precognition stuff, is to use photonics, or just how much light is absorbed, as a way to look at subtle fluctuations in gravitation, which is what I think it's really responding to. So these are
Thank you, Julia. Much appreciated. And I know we're over time, but we had started the clock a little bit later, I think. Want to get Entangled an opportunity to make their presentation, and then we're going to roll into the energy resources, moon infrastructure segment shortly. Welcome, Entangled. I see your slides. Hi.
Great. Well, thank you so much. This is super exciting. Very pleased to be able to present here. And it's also really interesting to see topics such as anomalous cognition kind of being presented in a public sphere. So very excited about that as well. My name's Damon Abraham. I am a principal researcher at Entangled Labs. I work with my partner, Adam Curry, who is the founder of Entangled.
Damon, sorry, your camera is, it looks like it's looking up at a light or something, which if that's intention, then that's fine.
Is that better?
That's better, yeah.
Thank you for the nod. So I work with Adam Curry at Entangled Labs, and we are essentially trying to bring some of this sphere of human consciousness into application. And so on the topic of how we can use these kind of expanded human capacities to accelerate discovery, first kind of like considering like AI and modern states of advanced supercomputing. These are obviously really powerful catalysts for discovery. The ability to sift through very complicated data sets, finding like previously hidden structures, even deriving insights from what was previously disparate or isolated knowledge spheres has been really, really productive and powerful. But where we see kind of a fundamental limitation in these systems is that they are inherently tethered to historical data. So the ability to, while we can draw kind of predictions about the future, essentially we are trying to predict the future by looking at the past, and this can be problematic. On the other hand, what we've seen with this discussion on remote viewing so far is that there's potentially the possibility of human consciousness to access information non-locally. Research in the parapsychological field, including remote viewing, kind of points to a non-local aspect of human consciousness and its operation. On the one hand, we have aspects of non-local action through like psychokinesis or the ability to influence events or activities through a distance. And then we have non-local perception through studies on such like remote viewing, which are apprehending targets that are not only displaced in space, but also, as already discussed, displaced in time. Next slide, please. So what we're building at Entangled is a mobile application that's connected to a random number generator, so a quantum-based random number generator. And this RNG interfaces with a global network of users. And essentially the premise of this technology is that randomness is actually subject to the influence of human consciousness. What we're building on is actually pioneered by decades of research from organizations such as PAIR, which was mentioned earlier, the Princeton Engineering and Anomalous Research Lab, the Institute of Noetic Sciences, for example, as well as the Global Consciousness Project. And what this research points to is that the behavior of these so-called random systems tends to statistically skew away from randomness during periods of intense focused intention, meaning that when you get participants in a focused state of awareness, they can actually bias the behavior of these devices without any physical mechanistic perturbation. Also, the behavior of these systems tends to be affected by peak states of consciousness and strong, powerful emotions. And in particular, when you see a synchrony of group emotions. And so evidenced by the Global Consciousness Project, you see that major world events, cataclysmic types of events, things like 9/11, are also associated with large departures from randomness and kind of synchronization across these globally placed devices. So really, really interesting non-local effects there. So by putting this into kind of an application form, at the individual level, what we're able to do is notify users when their personal data shows a departure from randomness that's statistically significant. And what we find is that this often aligns with subjective phenomena, such as perceived heightened states, et cetera. And so what we're essentially doing is facilitating a form of synchronicity or meaningful coincidence for the individual user. But more pertinent to the present discussion is that at the collective level, the network of subconscious minds essentially can be harnessed to make predictions. And so to give an example, one current experiment is that we are attempting to essentially predict the location and time of large seismic events. We are assigning kind of distinct channels within the network's data to specific global regions to track deviations of potential or deviations from randomness as potentially indicating an impending earthquake. And
Thank you for sharing that. And I know there's probably a lot of other interesting work. I realize we got to try to keep these on 5 minutes, and I know we're over. Thank you. Moving into what a segment on data, AI, advanced human capabilities, and a wide range of tools and techniques that, as our presenters have shared, have been used to outcomes in a wide range of environments. So moving into advanced energy, moon infrastructure, and resources. So this is something that'll include, a range of asteroid mining, how to work with regolith, how to work with building things off planet, different materials, habitats, and then also certainly some of that more advanced energy, which will form that bridge. I think in terms of that bridge from some of these other techniques and approaches on the advanced energy, do we have Hal on the line for the first one in that segment? Is Hal on yet?
I don't see him in our guest list.
No, I
and
don't
then
think he's on yet.
Larry, would you be ready to go? Rima, can you? We might need to let Hal in later in the segment after he's pinging us back and forth, but we'll just need to get him in. Larry, if you could make your presentation, that would be very helpful.
I can do it.
Thank you.
Which one is yours, Larry?
Lattice
Probably
confinement
the
fusion.
first one, yeah.
It was the first one?
This is in the next deck, which is the deck 6, the Moonfra energy.
Got it. Pulling it up now.
Moonfra as in moon infrastructure. And so Larry has worked both for NASA, Glenn, for many years, and is also active with a number of startups. So Larry, would you want to start with your introduction as the slides come up?
Sure. So I'm Larry Forsley, and with my colleagues, Dr. Pamela Mosier-Boss and Dr. Teresa Benyo, we've been working on lattice confinement fusion fast fission. This has been funded initially. Some of this work was funded under a CRADA with the US Navy. Then we picked this up with a series of Space Act agreements and contracts with NASA Glenn Research Center for over a decade. And we are now funded in part through the National Science Foundation. Next slide. So the real question is, what is lattice confinement fusion? And over on the right-hand side, you can see green metal. In this case, could be erbium, could be titanium. The red dots are deuterium, which is our nuclear fuel. And we published papers in PhysRev-C back in 2020 that showed we could induce fusion in that case by making use of gamma rays from Bremsstrahlung irradiation. And the reason this works is rather than having to use large magnets to confine a hot plasma, hundreds of millions of degrees, or large lasers, we make use of the natural electron screening in most materials, in particular metals. And we refer to the effect that we get out of this as being locally hot but globally cold. And what, to our great surprise and delight, a company by the name of Astral Systems in the UK took this idea after reading our papers and increased the neutron output of their neutron generator using inertial electrostatic confinement by over 50 times, where 99% of the neutrons no longer come from the plasma inside the tube, but in fact comes from the walls, which are in fact lattice confinement fusion. Now, what we've done is, and we are currently running experiments now, is using these neutrons within a deuterated, depleted uranium, and therefore we can fission uranium out of the ground. We can fission spent fuel rods, and we can also fission thorium. And we've demonstrated this both with the US Navy and in our Global Energy Corporation labs. We're currently doing this for the second round out at NASA Glenn Research Center. And the applications are basically low Earth orbit and deep space power, as well as terrestrial power. And over on the right-hand side bottom, you can see an example where a fusion reaction produces a neutron. This happens to be a DT, but we typically use DD. The energy of the neutron, 14.1 MeV for the tritium, but for DD fusion, it's only 2.5, But that's sufficient energy to fission a target nucleus of uranium or thorium or other actinides. Next slide, please. So applications, deep space power. We're currently on a NASA NIAC proposal to melt through 45 kilometers, 25 miles of the icy shells of icy worlds, like the Jovian moon Europa and the Saturnian moon Enceladus. It can also be used for nuclear electric propulsion and for planetary surface power, for example, 10 to 100 kilowatts electric lunar and Mars power. In particular, I refer to this as living off the land, where we can fabricate fuel rods in situ. We've located from previous satellites around the moon where thorium and uranium deposits are. And so now, instead of having to haul, for example, uranium, enriched uranium from Earth to the moon, we can actually build fuel rods out of the uranium and or thorium on the moon, and we don't have to enrich it, simplifying the entire process. Terrestrially, we've already been looking at, for the Department of Defense, operational energy with 1 megawatt electric, and also looking at small modular reactors, in particular for data centers with over 1 megawatt electric. And then going forward, as I mentioned, the NASA Innovative Advanced Concepts supported us doing Los Alamos MCMP modeling, nuclear modeling. We finished that in support of the Icy Worlds project. And as a consequence, as a follow-on to our stage 2, phase 2 NIAC, we're also now doing the NSF-supported scaling of this work at NASA Glenn Research Center. Over on the right-hand side, what people always forget about is that if you've got a nuclear reactor, on average, 70% of the heat is wasted as heat. It's not going into power. And in fact, eventually, even as you use the power, it'll all become heat. It's very difficult to get rid of heat in space. And over on the right-hand side, you see some work from a colleague of mine, Lee Mason, looking at a 300 kilowatt nuclear electric power system, propulsion system, as compared to 300 kilowatts we currently use for doing the same thing with solar electric power. And you can see the size of the solar panels compared to the size of the heat dissipation. So even though it's vastly smaller, they're still there, and you have to take it into account. And the last thing is, as I've made the point, if what we're doing is safe enough to launch from Florida into space, it's safe enough to use in Florida. So thank you
Larry.
all.
And you got done right in time. And I know you've been very active in some of these other technology areas, and as we're bridging kind of these concepts that span across fields of technology, did you want to weigh in on EED or any of these other ones?
Sure. So extended electrodynamics, which was briefly mentioned earlier by Charles, looks at pieces that were left out of the Maxwell's equations when Lord Heaviside refactored them. And it was in the 1950s that it was realized that one could have what we call a potential without a field. So no electromagnetic field, but you can have the potential which you can sense. And others have begun to exploit that. We've incorporated EED into the modeling we've done using density functional theory modeling, in particular, Luda Chero working with us from the Navy. And we find that it makes a difference in how we drive these lattice confinement fusion reactions, or at least how we model them. In turn, if that modeling is correct, it will change the way in which we drive them in reality.
Thank you. Yeah. You've spoken at some meetings where, all these things come play together. So that's always helpful to hear.
Hey, just a quick comment, Anna, before we move to the next one. Larry, that's an excellent job. It's quite compelling technology, actually. You're in a phase 2 NIAC right now, is that right?
No, we're on a phase 1. We delayed it a year to go for phase 2 to take the data from the NSF-funded portion of it.
Okay.
We are scaling it right now. We've scaled it by a factor of 20 times what we originally did with the Navy.
Okay. All right. Sounds good. Thank you.
Thank you. All right. Next presentation, please. Rima. AFWERX.
Hello.
Bill.
Cool. Hi, everyone. My name is Jose Kane, co-founder and CTO of AFWERX. First, I wanted to say thanks for having AFWERX at this event.
Sorry, Jose, we'll try to rename you. You've got somebody else's name on your computer somehow.
I saw that, but my name is
Sorry.
Bill. I can't pronounce that last name, so
That's okay.
but my name is Jose. I just wanted to say we're grateful to be in company with such innovative companies. So thanks for having us. I know we're a part of the Moon for section, but our mission actually extends well past the lunar and cislunar space. AFWERX was founded in January of 2022, located in Seal Beach, California, with our main mission being to extract critical resources from near-Earth asteroids for use on Earth. So as a general ConOps, our ConOps is to use rideshare on high-energy launches, like launches going to the moon, separate from the launch vehicle, and then our spacecraft then maneuvers to our target asteroid, which takes roughly 6 months. We dock to the asteroid and process on site for 3 months, and takes about a year to return back directly to Earth. Next slide.
You have it, Rima?
Cool. So I talked about our ConOps, and there's many pieces required to do that. But the key innovation that we've developed at AFWERX in order to enable our mission is really that refinery technology. Our low power, purely electric technology has gone through many iterations and uses a combination of continuous wave lasers and fast pulsed femtosecond lasers to extract. The continuous wave laser melts the surface, while the fast pulsed femtosecond lasers act as a hammer to generate nanoparticles. Once those nanoparticles are generated, we're able to separate out the material using its magnetic properties and sort out the ones that we want to keep and keep that's only valuable. And in the near-term case for us, that's the platinum group metals, a few of which are on the Department of Energy's critical materials list. With the help of NSF and NASA Phase 1 SBIRs, we've been able to prove out our refining tech at our facilities, and we're currently working to productionalize that refinery and qualify it for space flight. The second major thing we've developed as a company is a low-cost radiation-tolerant deep space vehicle for a much lower cost than the standard model. We've built that spacecraft, for example, in 4 months. So this one is launching on Intuitive Machines Launch 2 in February of next year. And if successful, that'll be the first commercial deep space mission. Part of developing that spacecraft is developing some of the internal avionics. So we've developed some low-cost, high-resolution imagers. These are 20 megapixel monochromatic CMOS imagers that will be used to take images of the asteroid surface to look for landing sites and prepare for our upcoming missions, as well as used to help with our navigation that we've also developed in-house. We've developed flight computers with high processing power to run vision processing that enables us to detect dim moving objects in order to correct for navigation. So next slide. So why is this important? So the technology really enables all of these things. Our mining tech is a lower cost, faster return, and cleaner, more sustainable process than the current mining process. Combined with our spacecraft, it allows us to gain access to these higher concentrations asteroids of these critical minerals in space for use on Earth. The refinery has applications in the terrestrial market as well. The refinery unlocks access to lower, harder to access mines and is able to process tailings generated by current mining process to get the remaining valuable material that's unable to be retrieved or not cost effective to retrieve with the current processes. On the spacecraft side, our vehicle, like I said, is significantly lower cost. We've developed a 100-kilogram vehicle for less than $5 million. That's rated for deep space. That, like I said, will be launched this upcoming February, and will be the first commercial mission to deep space in history. It really allows for low-cost access to high energy orbits and enables more science to be done, in deep space and cislunar space. And that's it. Thank you.
Thank you, Jose. This is it's really exciting, and the potential of resource exploitation off planet, is something that do you find people are very, very interested and open to that?
Absolutely. Yeah, I think this has kind of been this holy grail in space, finding the next big thing, and this really enables us to continue as a civilization here on Earth.
Thank you. Well, really appreciate your taking the time today. And I guess our next presentation, I believe, is to Planet.
Unmute. Okay. Okay, I'm up. Good afternoon. A nice job from Jose Acan. Okay, jumping into me and staying under 5 minutes. Starting next month, the federal government will have a new focus on direct-to-Mars exploration. I want to go direct to Mars, and today I'm asking and answering the question of how do you radically lower the costs of exploring Mars? Well, everyone knows that the reusability and size of SpaceX Starships will be a huge step forward. Almost nobody knows that the cost-lowering advantages of Starships can be multiplied by another order of magnitude or more. Yes, another order of magnitude. We can build a science station on Mars with budgets so low that the public will be amazed and inspired by NASA and the US space industry. How can this happen? One breathtakingly practical way to do this is to make use of superb local iron ore resources, and with these to manufacture and construct new electricity power plants, and then with the additional power, to set off a period of exponential growth in both local manufacturing and power generation. This, in short form, is the Ironbury Plan. The Ironbury Plan is, of course, contingent on there existing a superb Martian iron ore resource. So, boo, lo and behold, here is the needed, truly superb resource. And we can be sure from these pictures, it's shown right here in these pictures. And we can be sure these pictures show us a superb iron resource. These are NASA photographs and two photographs out of thousands taken by the rover Opportunity. This ore is made up of small near-spherical balls that are now called Ironburys and were informally called Martian blueberries 20 years ago. Most Ironburys are embedded in sedimentary rock. A few are half embedded in the walls of craters like these shown in the right image, and a great many are lying loose on top of soil like these on the left image. The left image shows, it's a false color image, shows an Opportunity rover sampling that has an Ironbury surface density most near the average across 45 samples taken. The point here is that the average density is extremely high. This photograph was taken of Ironburys lying on smooth sheet bed forms. The flat smoothness of smooth sheet bed forms is remarkable and practically important. Ironburys on smooth sheets can simply be swept off the surface with a rotating brush. Once on Mars, mining these loose Ironburys will be easier than harvesting fields of wheat with a combine harvester. Of course, Opportunity did more than take pictures. It also collected compositional data. To read about the composition of Ironburys, I recommend you read the paper given this QR code. And if you cannot QR fast enough, email at the address at the bottom of the next slide. The key compositional point is that the Ironburys are mostly made up of the iron ore mineral called hematite. The composition of Ironburys is very close to the composition of highly processed iron ore pellets, like the shown in the, should we best back on the first slide? We're on the second slide here. Can we get back? Yeah. In the middle here is a little ball of industrial iron ore pellets. The Ironburys in planet Mars are basically the same composition. So please grasp the following. Ironburys can be simply swept off the surface of smooth sheet bed forms and input to a reduction furnace to produce industrial grade sponge iron. With this industrial grade sponge iron, we have just jumped over an enormous barrier into the land of practicality. Next slide, please. And yes, there are ways with the aid of robots to turn this sponge iron into forms of steel that can be readily manufactured into the vast majority of parts needed to construct concentrated solar power plants on Mars. These intermediate forms are sheet steel and powder steel. The diagram on the left gives a process to produce sheet steel. And importantly, it has zero hard-to-obtain consumables. You can read more about how this is done in the paper at the bottom of the slide. It's called the Ironbury Plan, an electric and steel-making way to build a science station on Mars. The two QR codes have locations where you can download the paper. And finally, a third slide. Oh, there's water there, plenty of it. Ironburys sit on an enormous hydrated rock resource, and excess heat from electricity generation can liberate plenty of water from this rock. Okay, that's me done.
Thanks so much. I definitely did not want to cut off the water on Mars point. It's very, appreciate you bringing forth all of this. Great to see you.
All right.
Thank you.
Okay.
All right, so the next presentation I think we have up is Cislunar Industries. All right, are we ready to go?
Great, we're ready to go. Can everybody see me?
Are these the correct slides?
No.
Uh-oh.
Oh no, that's we want to go to Cislunar next.
Great. Assuming everyone can see me, I am Joe Pawelski, co-founder and CTO of Cislunar Industries. Cislunar Industries is an in-space manufacturing company, but we are truly an industrial space company. So our primary focus is industrial space. It is built on the belief that there are abundant resources off-world, and the best way to promote and sustain humanity on Earth is by having abundance of off-world resources. The most obvious resources would be energy, communications, compute, things like that. So these are things that can be brought back to Earth that don't necessarily have mass that we can really enable with a thriving cislunar economy. We started out with some NASA funding, a NASA SBIR for what we call modular space foundry. There's a picture of that to the left. We found that we could, it was based on a concept of debris to delta V. So that was capturing debris. Mostly this debris is aluminum, and then using that in a vacuum arc thruster to provide thrust for station keeping and orbital salvage operations. The foundry is also designed to make parts for in-space manufacturing. So we developed a continuous casting version of modular space foundry. That's it pictured on a parabolic flight. The Modular Space Foundry is also scheduled to fly on the International Space Station next year, where we will be doing some of the largest melts and the first continuous casting experiment. There's also a 3D steer where we are contactlessly manipulating and moving molten metal around to feed that into the furnace. What we realized as we were building this is that without the ability to get to debris and to move around, propulsion, power, these are some significant gaps for the industrial space. We're an industrial company. So we quickly realized that some of our near-term technology that we developed was a commercial opportunity for power management and distribution systems. Pictured in the middle is a 20,000 volt power supply that we actually, one of our partners, Think Orbital, used. I don't know if they'll be speaking later today. They're a fascinating company. That has flown. We flew that earlier this year, and they successfully did some welds. There's another flight of that later, actually this weekend coming up. Finally, this has led us into high power propulsion, electric propulsion. That's a picture of me installing Safran PPS 5000 in the vacuum chamber at Georgia Tech. We completed a very successful coupling test on that, and is very, very exciting. Next slide, please. Are you able to do this? Okay. So anyway, so what we realized here is that we have this big picture industrial space, again, creating resource or providing resources off world to really provide the industrial foundations for a space economy. But what we realized, the timeline on that requires several major gaps to be solved. And again, I mentioned propulsion. I also mentioned power management and distribution. We found that there is a very near-term opportunity in satellite constellations. So SDA has several tranches. The power level on those is increasing, and there is currently 60 to 100 week lead time on many of the critical power systems, specifically power processing units for electric propulsion systems that go on these constellations. Quickly following that, we have LEO space stations and servicing. The need to refuel, to service, to remove things from orbit, to have options for salvage other than deorbit are coming. We see these space stations as being logistics hubs and the servicers as being great ways to either refuel, refurbish, replenish, and truly provide that sustainable economy in space that's resilient. Now that's going to also a big shift that we see here is Starship. I don't think there's anybody expects that Starship is not going to play a major role in shifting the paradigm here. It's going to get lots of mass to orbit. But what we see is everything in between the hubs created by Starship will need to be accessed by space stations and by probably electric powered spacecraft that are moving in between there, that are providing the delivery, that are the trucks, the buses, etc. So those will all need power management and distribution. And then finally, Starship, to really be economical, needs to be refueled. Right now, the plan, one of the most compelling plans is to refuel off the lunar surface. There's probably many companies here that will speak about producing oxygen for refueling. Producing oxygen takes a tremendous amount of electricity, and power management distribution, which is, again, hardware that we are building right now. We are on the Space Power Propulsion Advanced Research Project, where we are building nuclear electric propulsion type systems and other gen sets that are 100 kilowatts and above. This is exactly the type of power levels that we'll be looking at for lunar surface to produce that oxygen to refuel starships. What's really interesting about this is the byproduct of reducing regolith to create oxygen is metal. In most places, in most lunar regolith contains metal. So we'll be creating stockpiles of metal, which just gets us back to our whole big picture of being the industrial suppliers and actually being able to build things off-world, like space power beaming, for example, which would get power back to the Earth and enable lots of other future concepts. So next slide, please. And again, just wanted to wrap it up. We do have current commercial products. We have customers that are buying power processing units for electric space propulsion. And we've found by focusing on terrestrial technologies and electric vehicles and other high efficiency power processing, we've been able to reduce the size, weight, and efficiency of the current PPUs that are flying by about 50%. So happy to, if you guys want to contact me later, but that's the high level, working on now opportunities for industrial space and building the foundation for the future of industrial space. Thank you.
Thank you, Joe. And this is one of these areas that we speak so much about, which is the need to really be able to build and scale infrastructure. So whether it's bringing significantly more power, going forward, and then also bringing the capital to finance this in-space infrastructure. And it was nice to see that overarching map that you offered. Curtis, I see you came on camera. You're on mute, Curtis. You're still on
Sorry,
mute.
I guess I should unmute. Joe and I have worked together with NASA and Cislunar for a while now. I just want to congratulate him for this good work and look forward. This infrastructure impact is significant, and so we're looking forward to this work.
Thank you, Curtis. And it's good to see so many friendly faces here, friends of mine.
Great. Well, thank you. And Reema, if you can help us move over to off-planet research, that would be great. And then after that, we're going to be bringing on Hal Putoff with Earth Tech International. And then we might have some time to get back into some of our energy presentations.
Sorry, I'm having some technical difficulty. I think I'm in the wrong place. Let's see. No, why isn't it working? Oh, I'm at the end. There we are. Thank you.
Morning, everybody.
Good morning, Vince.
Hi.
And good
My
afternoon.
name is Vince. Sorry, go ahead.
I say good morning and good afternoon, depending on the time zone. Great to see you.
Yeah, that's true. Okay, so my name is Vince Rue. I'm one of the founders and lead researchers at Off Planet Research. We're located in Everett, Washington. Off Planet Research simulates or recreates extraterrestrial environments for testing spacecraft and landed technology with a current focus on the lunar environment. As engineers, we know testing and good testing materials are important for increasing mission assurance, cost effectiveness, and to speed the development of space-based technologies. We've developed icy lunar regolith simulants. We provide consulting expertise on working with lunar regolith and conducting component testing, and we also develop our own technology, such as wheels attachment methods and dust covers and seals. Next slide, please. Volatiles, in this case, refers to frozen components that have been discovered in lunar ice. In 2009, the LCROSS mission, NASA crashed a satellite into the South Pole and discovered water, carbon dioxide, ammonia, and methane, to name a few, in the ejecta plume. With one data point of ground truth, there are many unknowns for these volatiles. they have revolutionized how lunar resources can be used. What makes the ice in the permanently shadowed regions attractive is that even with limited ground truth, there's believed to be about 5% water ice plus other ice constituents mixed in, which is about 15 gallons of water per ton of lunar regolith. This makes mining polar moon ice so attractive. Laboratory research with realistic icy regolith simulants can begin to answer some questions about lunar icy regoliths. Since it's anticipated that the chemical composition, physical structure, and concentrations of ice will vary, studying the many possible variations of ice that we may find on the moon will be important. In one application, as seen in the photos on the right, 2 different mixtures of icy regolith were created to demonstrate the ability of the instrument to detect the different chemical compositions. The graph on the right shows the results compared with the data from the LCROSS mission. Under a Phase 2 NSF SBIR, we are continuing to expand our capabilities in producing icy regolith simulants with a variety of volatile components at ultra-cold temperatures, as well as different methods of supplying these cryogenic and sometimes quite corrosive test materials. There are also implications for Mars, cometary ice, and other icy worlds in this research. Next slide, please. Lunar resources can help address the business case of how we can afford a sustained space presence. When it comes to millions or billions of dollars to get something to the moon, it would be too expensive to bring everything from Earth for a lunar settlement. Science and research goals can only fund so many missions, and governments can only fund so many missions. It would be hard to make the case for a long-term presence without being able to show the financials of why we need to go to the moon, not just why we want to go. This is where lunar resources come into play. We need to be able to use the resources on the moon, Mars, and asteroids to literally propel ourselves into deeper space. This all starts with the idea of in situ resource utilization, or ISRU. And ISRU is the idea of living off the land and using the resources around you. Luckily, there are many resources that can be extracted from the regolith and used on the lunar surface. Lunar regolith is at least 40% oxygen by mass. There are a variety of metals and crete components, such as potassium, rare earth elements, and phosphorus in the regolith as well. And of high interest is the water the LCROSS mission found during its mission to the permanently shadowed regions. Icy lunar volatiles can be used in rocket fuel, breathable air, drinking water, and in architecture.
Okay.
The remnants of lunar regolith that has already been extracted can be used in sintering 3D printed applications to make tools, construct buildings, and protective thermal and impact shields, as well as roads. We look forward to continuing to support the research being done in these areas, and we thank you for your time.
Thank you so much. And this emphasis for in situ resource utilization is definitely a major area of drive right now and going forward. So I'm thinking that next we go to Hal Puthoff, and then do we have Red House on the line as well? Diane, maybe you can check in if we have Red House.
Yeah, I'm here.
Yes,
Okay, great.
we do.
And Chris,
Yeah.
so I guess we just figure out after Hal if we've got or Hal, do you have a few minutes if it might be a more natural flow to go into Red House next. Would you have a few extra minutes, Hal?
Yeah, that's fine.
Okay.
Yeah.
So because Chris, would you be ready to go? Because this whole building using resources off planet, that really reminds us of your work as well. Are you ready to go?
Absolutely. Yeah.
Okay. Can you pull up your slides or?
Oh, sure. Yep.
Thank you. So we haven't directly funded Red House, but we have worked with a number of other companies at NSF in alternative proteins. So really looking forward to you sharing with us about how mycelium and other types of agricultural or biologics can be used for shielding and for protein and other uses.
Okay. Are you seeing my screen now?
Yep, looks great.
Wonderful. Okay. So hi everybody, my name is Chris Maurer. I'm an architect. I'm founder of Red House Studio. We're an R&D firm that works with a lot of different biomaterial technologies, and we're currently working on a NIAC Phase 3 project with Dr. Lynn Rothschild at NASA Ames, where the concept is actually to grow buildings off planet. And I'll start this animation here to the right. You can see some of our project partners at the bottom there. But our goal is to actually be able to take a building off planet that's an inflatable structure, and then the outer shell of that would grow with living organisms within it to produce some of the materials that would be biologically performative in aspects of insulation and radiation protection. And so we do this by using fungal mycelium, which is an organism that from the fungal kingdom that is commonly produces mushrooms. And so that's how most people are familiar with it. But the mycelium part of the organism is actually the base part of the organism, and the mushrooms are the fruiting bodies. There were some research that showed that some fungi that produce melanin have the ability to actually protect from space radiation. And so that's part of what we're discovering here is can we actually leverage the growth of that organism to block from space radiation, use the material for insulation, because we can leverage the inflatables for things like the structural capabilities of the buildings. You see a few different archetypes that we have there. We're working with Dr. Jim Head at Brown University, and Jim trained a lot of the Apollo astronauts. And during Apollo 17, they wrote a 500-day mission with Commander Dave Scott, and now we're reprising that for a proposal to Artemis. And so here are some of the archetypes, including landing pads, initial base structures, and even things like rover garages, because the lunar night is so toxic that it even kills robots. So you have to have warmed garages to keep the robots alive throughout the lunar night. The first part of how this phase 3 is going to play out is we're working with Starlab at Ohio State University, and that's a broad consortium that includes Hilton Hotels and Voyager, and several other industrial components, including Airbus. And they're looking to launch a commercial space station in 2028, 2029, that will include some of our materials. We're not sure exactly how that plays out yet, but since Hilton Hotels is one of the partners in this, we think that their beds probably won't be as simple as the ISS, where they're just a sleeping bag strapped to the wall. So we're developing some concepts for low Earth orbit that actually keep people in place. And if that animation's playing at your end, you might be seeing a bed that's actually holding the folks there, the astronauts, stationary, because that's a problem in space. You also notice that a lot of the materials that are here have a black color to it, and that's because we're using the fungi to produce melanin as an extra radiation shield. And so this is something that can be done in situ, including low Earth orbit or at destination, where we have hydrogels that can be transported very cheaply, easily, in very small amounts of mass, and then able to grow these organisms that then produce the bioperformative materials like melanin to shield from radiation. And then the last part of what we're going to do with this NIAC 3 is work with the Commercial Lunar Payload Services group at NASA. And we're going to send a model of our structure to Mars. You saw on that first slide the concept for the building. Here are some pretty simple models. We call these sketch models in the architectural world, where if the napkin sketch is what the architect eventually builds the building from, these sketch models that include Lego toys are our concept for what we're going to send as part of this CLIPS mission. That would be these inflatable structures that would have these different cells that would fill with the materials, and we'll actually send those with radiation sensors and thermometers, cameras that will come back to us with the data of these building models that are growing on a moon lander. So it'll actually be growing on the surface of the moon. So again, this is the NIAC phase 3 with Dr. Lynn Rothschild. We're currently working with Starlab at Ohio State, and then we'll be moving on to a CLIPS mission to do our model before we take this on to to the moon for real with a larger building after series of funding. So I'll leave it there. Thank you.
Thank you, Chris. Really appreciate you sharing your work.
Thanks.
Just some of the efficiencies of this type of approach are really very compelling. So Hal, I think we have Hal Puthoff on the line. Thank you for joining, Hal.
I'm here, and I guess somebody else has my slides there.
Oh, yes. And Reem, I don't know if you have them or if you want me to open them up, the ones that, and then I think we've also got time afterwards. We could go into if Chance, are Chance and Mark still on the line? All right, your
Yes, I'm
slides are
here,
up.
Anna.
Okay.
Okay, I'll start right in. I'm Hal Puthoff. I'm Chief Technology Officer and CEO of EarthTech International in Austin, Texas. We work on energy, propulsion, and communication for spaceflight. So today I'd like to address two particular areas of interest of ours that I think are really advancing technologies for the space stage. The first one is advanced space-time metric propulsion technologies based on the Defense Intelligence Agency investigation of UAPs, so-called unidentified aerial phenomena. That was a highly classified program begun some years ago, and I was a senior advisor and contractor in the program called AWSAP, Advanced Aerospace Weapons Systems Application Program, and ATIP, Advanced Aerospace Threat Identification Program. The DIA and the rest of the Pentagon were concerned about potential adversaries, say the Russians or Chinese, achieving breakthroughs based on evaluations of their UAP phenomena from sensor data or crash retrieved materials. And that was the concern that set up the program. And then the second area I want to address is
Al, I won't take away from your time, but I know everything's moving so fast here. Just to highlight that this OSAP and this ATIP, these are, publicly visible, the main DoD programs on UAP technology. So for those that aren't as familiar with the acronyms, these were the main DoD recent programs. So please continue.
Okay, and much of the material from those programs has now been made available through FOIA. The second area is in advanced communication technologies, and I and several other researchers are pursuing based on what we call EED, extended electrodynamics, involving quantum phase communication that has particular attributes useful for spaceflight. Next slide, please. So, can the reported anomalies of UAP be accounted for on the basis of known physics? Well, we talk to the pilots and they say, oh my gosh, they're dropping from space to the surface of the Earth in a few seconds, and then they make right angle turns at Mach 10, and this is way beyond our physics. The truth of the matter is that it's actually, from our standpoint, investigating it, not beyond our physics, but it's certainly beyond our engineering. And so we can address issues such as, can you reduce inertial mass? Can you beat the velocity of light constraint and so on? Well, the way to answer that is to take an engineering approach to general relativity. Of course, much of our technology today is based on electromagnetism, which we know all comes out of Maxwell's equations. With Einstein's equations, we have what's called space-time metric. And of course, that's used by astrophysicists to calculate black hole attributes and star mergers and so on. But from our standpoint, we said, okay, made up a sheet of paper where on the left-hand side of the piece of paper, we listed all of the unbelievable observations we had seen with UAP. And then the right-hand side of the page lists, well, suppose you could engineer Einstein's equations like we engineer Maxwell's equations. What results would you expect to see? And it turns out you get a match, hand in glove. So you might ask, well, why aren't we doing that then? Well, it turns out that from our present understanding of Einstein's equations, the enormous energy densities that would be required, we're just not there yet. Now, maybe there's some workaround we haven't discovered, so that's a possibility. Next slide, please. And in the advanced communication technologies arena, it's EM without EM. What do I mean by that? Of course, our standard EM communication is based on electromagnetic fields, E and B. But the advanced extend electrodynamic technology is based on the use of vector and scalar potentials, A and phi, which of course we're familiar with in EM theory as well, but under the special circumstances that the EM fields themselves are suppressed. So it turns out that with specialized antenna geometries, you can generate radiation of vector and scalar potentials, but with no associated EM fields. Well, that's important because A and phi, unlike the case with E and B, are penetrating and non-shieldable. Now, how is that the case? Well, when an electromagnetic wave gets to, let's say, a conductive shield, the reason it doesn't penetrate it is because it generates, the electric magnetic fields generate charge distributions and current distributions that end up preventing the signal from getting through. But if E and B are stripped out and you only have A and phi, well, then they can go right through that kind of an environment. And so, of course, for space applications, you have non-interference by dust or plasma, water. We're looking into the use of this technology for communicating with submarines through the conductive seawater. Now, it turns out that the standard EM potentials A phi are quite stealthy because they're undetectable by ordinary EM detectors, which of course rely on electric and magnetic fields for detection. So therefore, quantum detectors are required. This work is moving forward. Patents have been issued. I've got 4 of them in my own organization. We're in early stage development, and the technology is well worth R&D development for use in space applications. Thank you.
Well, thank you so much, Hal. You know, certainly a tremendous body of work that you have across these UAP, EED, you know, and advanced communications, yeah, and also the remote viewing as well. So really appreciate you taking the time today. And some of your other research collaborators will also be speaking in the quantum segment later on today at 5 p.m. So, you know, there's more interesting overlap in this EED, UAP, and other areas of advanced technology, and including communications. There'll be a communications talk on that as well. So I'd like to give the opportunity, thank you, Chance, and then after Chance, Mark, you know, to go into your presentations.
Okay, do you all have my slides you can put up there?
Are we going
I
into
don't have-
the space?
Sorry,
launch?
we're going
Morning
back
Bird
to the
space.
EED. So if we go back, yeah, the Morning Bird space, this is deck number 4.
Yeah. Well, good afternoon, everybody. As they're getting those slides together, I want to say how fascinating this has been all day. And I also wanted to state that hopefully you'll see as I get through my stuff that the application of this to all of these different areas, particularly like semiconductors and the biomedical applications that were talked about earlier, could be very much relevant when we're talking about manipulating gravitational fields and waves. So are the slides ready?
Do you have them on your end, Chance? If I guess I think Rima's very close. I think she's very close right now.
She's
So
close,
if you just,
because UN Lab was close to mine.
yeah, if you look up Morning Bird here, Control F Morning Bird.
So much fun jumping between all these slides.
It's been amazing, Rima, and we stayed up till 3 a.m. kind of putting
I
these
know.
together to try to make
That's
it
why I'm
smooth.
paying my dues now. I didn't stay up till
And you're doing an amazing job for this whole presentation of the day. So thank you all for this. I'm foregoing my video. I'm actually sitting outside of a Starbucks waiting for another thing, but that's me there working on the interferometer. What I want to talk about is the production, I believe, of gravitational waves in a laboratory setting. Now, this is very significant. And the key to it is not just the high level of energy density that's formulated, but the rapid formation of these high energy density regions. The spark gap is used because you can put a significantly high amount of energy, the power times the current, or the power times the time, or the voltage times the current times the time. But the formation of it quickly is what I've been viewing the movement of these interference fringes. So if you go to the next slide, you will see that I'm using an interferometer very much like what LIGO used to detect the gravitational waves from the merger of two black holes. But on this small scale, what I'm been able to induce is movement of the fringes by the formation of this high energy spark. I'm getting energy density levels on the order of 10 to the 12th, which is literature has shown this is a level that would begin to see these kind of reactions. But again, the rapid change. What you see in the picture are the measures of the peaks of the formation of those fringes and the movement therewith, and being able to not only modulate the production of the spark to give them a pulse repetition rate, but then also to show the magnitude of their movement.